Your lecturer is Professor James A. Sellers. Dr. Sellers is Professor of Mathematics and Director of Undergraduate Mathematics at the Pennsylvania State University. His engaging teaching style has earned him a wealth of honors and distinctions. These include the Mathematical Association of America's Allegheny Mountain Section Award for Distinguished Teaching and Penn State's Mary Lister McCammon Award for Distinguished Undergraduate Teaching.
Greetings and welcome to the Teaching Company's Algebra I course. My name is James Sellers and I'll be your Algebra I instructor. My hope is that you find this course challenging, enlightening, and enjoyable. As we begin this course together in today's lesson, I'd like to do a number of things. I'd like to introduce myself to you. I'd like to introduce you to the general topics and themes for this course so you have a feel for the mathematics we're going to look at. I'd like to share a number of other thoughts about things like graphing calculators and how to use the materials in this course. And then I'd like to start our mathematical conversation with a review of sign numbers and operations. I think it's important that we actually do at least a little bit of mathematics together today. So let me begin by sharing a few details about me. I received my PhD in mathematics from the Pennsylvania State University, which is otherwise known as Penn State University, in 1992. I also met my wife, Mary, while we were both students at Penn State. We actually got married while we were there. And in 1992, I began to teach at a school called Cedarville College. It's actually called Cedarville University now, in Ohio. I stayed there until 2001, when I came back to Penn State. And I'm now there at Penn State as the Director of Undergraduate Mathematics. I've been so since 2001. Mary and I have 5 kids. 2 of them are in high school, 2 of them are in middle school, and 1 is in elementary school at this time. We've homeschooled our children for many years. Now some of them are what we call dual enrolled, which means they do homeschool part of the time and they do their local school, their public school, part of the time as well. And we've really enjoyed the experience of being able to homeschool our kids, but we've also enjoyed seeing them go into the schools and enjoy the classes they take there as well as their extracurricular activities as well. I love teaching. I've been doing it for a long time, and I hope that as we go through this course together, you'll notice that I love to teach. And my hope is that as we work through the material together, that love for teaching this material will translate into at least an enjoyment for you of the material. Maybe not a love, but how about a strong liking of the material for you? I've also had the privilege of writing secondary level textbooks in mathematics for a variety of publishers. Probably the best known one is Saxon Publishers. Now, that's enough about me. I'd like to start talking about this course, this Algebra I course, and what it is we're going to do together as we walk through the course. Basically, the course is going to include a number of topics from what you might think of as a traditional high school Algebra I course. But it's important that you notice that it can't cover all the topics that would be covered in 1 year of Algebra I at a high school. After all, we really only have about 18 hours of lecture time together. So the course is going to cover a lot of topics that you would see in that traditional Algebra I year at a school, but it's not going to be able to cover everything, at least not in the depth that you would see at such a school. But it will cover a lot of general topics that you would see, and I'd like to tell you what those are going to be at this time. First of all, we're going to spend a few lessons talking about some pre-algebra basics, things like order of operations, decimals, percents, variables, operations on algebraic expressions, especially when exponents are involved, and the principles of graphing in the Cartesian plane. I think it's very important that we take a few lessons together just to make sure that those pieces of information, are nailed down so that when we move on to the algebra material, you're ready to go. So we'll spend a few lessons on that kind of material. And then we'll transition to what is probably one of the best known topics of any Algebra I course, and that's linear equations, linear functions, and graphs of linear functions, which of course are lines. That's where the word linear comes from. And that really will be a major part of this course. And we'll spend a lot of time talking from different angles about linear equations and their graphs. Then we'll transition a bit and we'll talk about quadratic polynomials, quadratic functions. Now, sounds like some big words, sounds like some scary words, but all it means is that we'll be looking at polynomials or functions of the form ax squared plus bx plus c, where a, b, and c are just some numbers. So something like 7x squared plus 5x plus 2. And we'll talk about solving equations that have those kinds of terms in them, and also graphing what those look like as well. And they look very different from lines. They're very, very cool. So we'll talk about quadratics after we talk about the material on linear equations. And then from there, we'll talk about polynomials in general, which are basically just an extension of talking about the linear and the quadratic material. So we'll just kind of take that a little further. And then we'll move on to something called rational expressions, rational functions. And all a rational expression is a ratio, it's the first 5 letters of rational, ratio of two functions which are polynomials. So that's kind of a natural progression. After we've talked about these polynomials, we'll talk about these ratios of polynomials, which are called rational expressions. And we'll talk about their graphs as well. And then we'll talk about radical expressions or radical functions. And radical really just refers to roots, most particularly square roots. And we'll talk about what functions look like when you have square roots involved. And we'll look at their graphs as well, and we'll look at solving equations with square roots in them, and so on. And then at the end of our course, we'll shift gears pretty dramatically, and we'll talk about sequences and pattern recognition. And this is basically just looking at lists of numbers and trying to see if we can pick out the pattern which was used to build that list of numbers. It'll be a nice way to close out our course together. Now, within each of the general topics that I just mentioned, like linear stuff and quadratic material and so on, we're going to concentrate on several strands or themes that will really go throughout the course. So we'll see these same sorts of themes popping up every time we introduce a new basic topic. So here are what these strands or themes are going to look like. First of all, I'm going to emphasize every time we come to a new set of material that we need to master the basics. I'm going to try to highlight why it is we're studying this. What are the key ideas, the key concepts, the key rules? And in fact, I'll even point out, while we're mastering these basics, what are the key things you've got to watch for as you do this material? What are some of the pitfalls or the errors that are common when students are learning this material? So we'll really try to nail things down in not so much in the theoretical sense, but in the sense that we can understand the bigger picture as we're walking through these materials. I'll also focus a lot on visualizing the graphs of each of these kinds of functions. I think it's very important, especially if you're a visual learner, that you see what the algebra looks like. Often people think that algebra is just about manipulating symbols, moving x's and y's around on a piece of paper. Well, there is a part of algebra that is all about manipulating symbols and solving equations and so on. That's very important, and I will emphasize that as we go through the course. But I also want to emphasize this visual idea. So we'll talk about graphs a lot, and we'll work through a lot of graphs, in fact, by the time this course is over. I'm also going to try to emphasize real-world examples and applying algebra to real-world examples throughout the course. So again, it's not just going to be one lesson on real-world examples. We'll mention real-world examples over and over as we walk through this course. And I think it's very important that you and I learn how to translate word problems, which always seem to scare students in mathematics. We need to be able to translate word problems into algebra and then use algebra to solve those. So we'll try to spend time over and over again looking at real-world problems, or what some people would call word problems. And then one other strand that we'll look at in this course as we walk through the course together is we'll try to do some critical thinking as we're dealing with the solutions that we come up with. You know, Often in math, you get an answer to a problem and then you don't know really what to do with that, or you just kind of move on to the next problem, or maybe some homework in a different course. But it's very important, once you get a solution or you get an answer, to think critically, even if it's just for a few seconds. Does that answer make sense? If the problem asked for someone's age and we come up with an answer of -12 years, well, that doesn't make a whole lot of sense. So we're going to want to critically think about answers to especially word problems to make sure we haven't done something silly, something wrong in our calculations. So that'll be another strand as we walk through this course together. Now, we're starting out with this Algebra I course. We're in our first lesson. I think it's important to actually try to answer the why question. That is, why should I study algebra, or why is algebra important really? Well, I'm going to give you several answers to that question. I think it's good to hear these answers. Maybe one of them will be one that you really like. Maybe all of them will be answers you really like. But I think it's important to see the answers to why algebra is important from a lot of different angles. So, first of all, the first year of high school algebra is the prerequisite, or the math course that you need to take before you take lots of other higher level math courses, whether it be Algebra II, whose name implies that you need Algebra I first, or it be geometry or trigonometry or even calculus. According to several studies that have been conducted in recent years, students who master Algebra I, geometry, and Algebra II in high school are much more likely to succeed in college-level math. In fact, they're much more likely to succeed in college in general. So it's very important that we lay a strong foundation in the Algebra I course, and that's what we're going to do together as we walk through this course. But why is algebra important in its own right? I mean, the answer I just gave you is really more about a bigger picture of a student wanting to be successful later on in high school or maybe even in college. But why is algebra important? Well, I could actually share a lot of answers. First of all, algebra is important just in problem-solving situations. To be able to go from just arithmetic, where you add up numbers or subtract numbers, multiply numbers, and move to equations that have variables in them, that allows us to solve lots of real-world word problems. So that abstraction, to use a big word, allows us to move into these kinds of problems. And these real-world problems cross over many different disciplines. In fact, algebra underlies all the technology that we enjoy, and it's needed in all of the sciences. Imagine all the formulas that you've probably seen in classes like physics, biology, and chemistry. A lot of those are based on algebra, and we would need that algebra then to go study these other sciences. But let me try to speak more practically about this question of why algebra can be useful or why it's important. Take the fairly well-known equation d equals rt, d equals r times t, where d is distance, r is rate, and t is time. You may not have known it as d equals rt, but I can almost be certain that many of you, most of you, maybe all of you, have used this equation sometime in your life. It can be used in a variety of circumstances to determine unknown quantities. For example, let's say I'm driving for 5 hours at a rate of 60 miles per hour. That means t equals 5 and r equals 60. I can substitute those numbers in. And the question is, how many miles will I drive? Well, the answer is simple. If I use d equals r times t, I'm going to drive d equals 60 for r times 5 for t, and 60 times 5 is 300 miles. It's that simple. I know that by the end of that trip, I will have driven 300 miles. Now, okay, that was a really simple example, but I just used algebra to solve that problem because I used that equation, d equals rt. In fact, if we had been given any two pieces of information, d and r or d and t or r and t, we could have solved for or figured out the other or third quantity. We would have used some algebra to do so. And that's just one little example. Let me give you some other examples where you really could use some algebra even if you didn't realize that that's what you were doing. So let me give you a few examples. Let's say you're out one Saturday night and you want to stop at your favorite fast food place and buy some food and a drink, okay? But you realize that you have almost no money. In fact, you're scrounging through your car for change just to get enough money to buy something. Now you know that there's a certain classmate of yours, pretty cute classmate in fact, who's working at that restaurant tonight. And to be honest, that's probably really your motivation for stopping, but you don't want to be completely embarrassed that you don't have enough money in your hand to order exactly the food you want. In other words, you don't want to order too much food and then not be able to pay for it. And you also remember that there's some sales tax that's going to be added to your meal cost. So you're staring up at this menu trying to keep all of that in mind. Can I buy that burger? Can I get some fries with it? A large drink instead of a small drink? And you've got to keep in mind that all you have in your hand is maybe $3 in change that you scrounged out of your car, and you know that there's sales tax of 6%. How much stuff can you order so that you don't overspend and embarrass yourself in front of this really cute classmate? Well, guess what? You could actually write down an algebraic equation to tell you how much money you could spend on the food up on the menu in order to make sure you keep everything below $3 once the sales tax is added in. That would actually be algebra. You may not think of it that way, but it really would be algebra because of the equation that you'd be using. Here's another example. Your school, actually my children's schools, the middle school and the high school that they attend, they give 4 grades at the end of each of the 4 marking periods. In other words, they cut the year into 4 big segments, and at the end of each of those 4 marking periods, my kids get a grade. Let's say a grade in math and a grade in science and a grade in history and so on. Now, let's say that you've made a deal with your parents that you get a new cool thing, maybe a new iPod or a new cell phone or a new something, as long as your end of the course grade in math is an A. We all want grades of A in math, I hope we do anyway. And your end of course grade, in other words, the year-end grade in math, is exactly the average of the 4 grades that you're going to get, one at the end of each marking period. So let's say you're coming towards the end of the school year, and you got a 92 at the end of the first marking period in math, and in math at the end of the second marking period you had an 89, and then you had a 95 at the end of the third marking period. Now, you've made this deal that as long as the average of those 4 grades at the end of the 4 marking periods are at least an A, you'll get this nice thing, whatever it is. Here's the question. What's the smallest grade you can get at the end of the 4th marking period to guarantee that you get an A for the whole course? Well, you could actually write down an equation to answer this question, and you'd solve it using a little bit of algebra. Oh, you're just doing an average basically, but there's an equation that we could write down easily to solve that and to answer the question. That would be algebra. What about this? You're working over the summer for a carpenter, and tomorrow you're going to go to some work at a new house that it's being built. And you have to make sure that the carpenter's ladder, let's say it's 10 feet long, will fit into a certain space so that you can reach the top of an 8-foot wall, but at the same time not go out too far from the base of the wall because the space is actually in a small hallway. How far out from the base of the wall will you need to place the foot of the ladder so that you get up against the wall just right? Well, to answer that, you would actually use a very well-known formula, which is known as the Pythagorean theorem. And it turns out that it's a quadratic equation. I mentioned we're going to study quadratics in this course. That would be algebra to figure out whether you could really put that ladder in that hallway for the carpenter to keep on doing that work on that house. And lastly, let's say you like to build rockets, or just on a personal note, my boys like to build something called potato cannons. In fact, we have at least 2 different potato cannons at our house right now. They're very cool contraptions, by the way. Now, let's say you're going to fire off one of these rockets or potato cannons straight into the air, right above your head. And you're going to have this rocket then, or maybe a potato, going up in the air vertically. If you ignored any sort of wind resistance or any effect from the wind, here's a question. How long would you have before the rocket, or maybe the potato, comes straight back down and hits you in the head? Or another question, how high will the object go in the air? You know, it's good to know how long it's going to take before it comes back down because it tells you how long you've got to move out of the way. Figuring out the answers to these kinds of questions involves algebra. Well, also, what if you took this thing and fired it at an angle instead of straight in the air? You sort of fired it out at some angle. And you want to make sure that you're not going to actually hit your neighbor's house in doing so. Figuring out how far that rocket or potato or other projectile would go is all about algebra. You'd use some formulas, in fact, to figure out the answers. And there's lots of other formulas in algebra that we often use. Think about this. A equals pi r squared. I bet many of you know that that's the area of a circle with radius r. And there's others. Things like V equals pi r cubed, which is the volume of a sphere of radius r. Or V equals pi r squared h, where V is the volume of a cylinder, and the radius of the cylinder is r, and the height of the cylinder is h. Or things like C equals 2.54i, which helps you convert from inches to centimeters. There are tons more of these equations out there, and they're all about algebra. And you know, without algebra, there would be no calculus. And without calculus, much of what is done in physics and all sorts of areas of engineering could not be done. Whether it's designing machinery or designing electrical circuits, you wouldn't be able to do it without calculus, and therefore you wouldn't be able to do it without algebra. Well, you probably have lots of questions that we should ask and answer before we begin really doing the math together. So let me try to talk about some of those now. Let me just ask a few questions that might be on your mind. First of all, will this course require a certain calculator? Well, I'd like to actually answer that question first by sharing a little bit of my view on calculators in general. I believe calculators can be useful, but unfortunately I think some students sometimes use them too much. They rely on them too much to do basic calculations. And because of this, I'm not going to focus on using calculators every time we're doing every calculation in every lesson. We will use one from time to time, and especially later on in the course when we're doing square roots and so on, I'll suggest that you pull out a calculator. But it's not going to be a critical part of this course. And I'm definitely not going to suggest any one particular brand or style of calculator. So if you already have one, feel free to use it. But please don't rely on it too much. It's important that we be able to do some arithmetic in our heads and not just use a calculator. And while I'm talking about tools that we need for this course, let me point out right now that we're going to use graph paper a lot. I talked about how we're going to visualize the graphs. You're going to want to sketch graphs using graph paper quite often. And so if you don't have any graph paper yet, you might want to grab some before we get on to some of the later lessons in this course. Okay, next question that might come to your mind. What's the textbook for this course? Well, that's a good question. I don't actually have a particular textbook to suggest to you for this course. There are lots of Algebra I textbooks on the market, and I'd encourage you to supplement the work in this course with that kind of a text. Or maybe you're in a course already in your high school, for example, that has a book. Fine. You don't need to get a different book for our work together in this course. The workbook that will accompany these lectures is meant to serve as a beginning guide, and I'd strongly encourage you to use it. But otherwise, don't go get a book just for our course here. Okay, how about this question? How should I use the workbook with the DVDs? And I think that's a good question. Knowing how to use the DVDs and the workbook that have come to you is very, very useful. I would suggest that every time you prepare to do a new lesson, that you briefly read over the material in the workbook before you watch the lesson. I would then go back to the workbook and reread that material a second time after you watch the lesson, and then work through the exercises for that lesson that are there at the end of the section of the workbook. So read the workbook briefly first, watch the lesson on DVD, go back to the workbook a second time, look over that material again, and then look at the exercises for that lesson and complete them at that time. By the way, while you're watching a lesson, if you'd like more of a challenge, you might want to actually pause a lesson at some point and try to finish one or two of the examples that I share with you before I show you how to do them. I will walk through every example step by step. But if you'd just like to see if you're ahead of me at that point, you might pause the DVD, you might do the example yourself, and then turn the DVD back on and watch me go through the example. It'd be a great way to confirm that you understand the material if you and I end up with the same answer. Okay, I think it's important for us to do at least a little bit of mathematics together before we close this lesson today. So I'd like to talk briefly with you about signed numbers and operations with signed numbers. And I hope this is really review for you, but if not, you may want to spend more time on this topic on your own before you move into the next lesson in this Algebra I course. So what do I mean by signed numbers? Well, let's start by remembering the set of integers. The set of integers, or whole numbers, is the set of natural numbers, or counting numbers, 1, 2, 3, 4, 5, and so on, combined with their negative counterparts, -1, -2, -3, -4, -5, and so on. And then the special number 0, which we often write in between the first two sets that I mentioned. One of the easiest ways to visualize the set of counting numbers, or actually the set of integers, is via a number line. And you may have seen a number line before. I hope you have. So you can write your number line with 0 in the middle and then the positive integers 1, 2, 3, 4, 5 to its right, and then -1, -2, -3, -4, -5 to the left. And from the number line, we can see how the numbers relate in terms of size, relative size with one another. We know from previous experience, for example, that 3 is less than 7. Well, you know 3 is less than 7 anyway. If I've got 3 apples and you've got 7 apples, then I have fewer apples than you. But 3 is less than 7 because on the number line, 3 is to the left of 7. So actually, that's how we might define 3 being less than 7. Also, 0 is less than 5 because 0 is to the left of 5 on the number line. And -4 is less than 3 because -4 is to the left of 3 on the number line. I realize that 4 is bigger than 3, but -4 is less than 3 because the -4 is on the left of 3. And that reminds us then of a function called the absolute value of a number. It's often denoted with two small vertical lines around the number. And one way to think of the absolute value is that it's simply the distance from the number you're looking at to the origin being the 0 on the number line. So for example, absolute value of 3 is 3, because 3 is exactly 3 units from the 0. Absolute value of 0 is 0, because 0 is 0 units from the origin. It doesn't move anywhere to get to itself. And the absolute value of -4 is 4, because -4 is 4 units away from the origin, from 0. So there we see a way to look at absolute values using signed numbers. And from here, we can ask several things. For example, how do you add signed numbers? And how do you multiply two signed numbers? Well, hopefully you've seen this before, but I just want to remind you of it because we will be doing it a lot throughout the course. First of all, the addition of two signed numbers, I think, is best described on a number line. For example, what if you wanted to find 4 plus -3? Well, if you're doing that with a number line, you start at the 4 on the number line, and then you want to add -3 units. Adding -3 units means you want to move to the left 3 units. So from the 4, you come backwards, or to the left 3 units. Where are you now? Well, you're on 1. And therefore, 4 plus -3 is 1. That's actually a way to define how to add signed numbers using this number line. Let's try a second example. What if you wanted to do -5 plus 8? Well, now you want to start on the number line at -5, and you want to add 8 units. So now you're going to move to the right 8 units. And when you do so, moving 8 units over, you're going to land at 3, +3. And so -5 plus 8 is 3. Let's try one more. What if you wanted to do -6 plus 2? Well, again, on the number line, you start at -6, and now you want to add 2 units. So I'm at -6, I'm going to move to the right 2 units because I'm adding 2. And if I do that, I go from -6 to -5, and then -4. And so, since that's my last number I've landed on, -6 plus 2 is -4. And that's a way to see how to add and subtract signed numbers using a number line. Well, what if you wanted to do multiplication and division? Turns out with signed numbers, multiplication and division are even easier. Here's the rule. If the two signs of the numbers you're looking at are the same, then the outcome is going to be positive. But if the signs are different, then the outcome will be negative. That's it. That's the whole rule. So let's do a few examples. 4 times 3, we already know is 12. But that's the product of, or the multiplication of, two positive numbers. The answer comes out to be positive 12. What if you do -4 times -5? Well, 4 times 5 is 20. But will the sign of the answer be positive or negative? Well, since I'm multiplying a negative with a negative, the rule says that since the signs are the same, the answer is positive. So -4 times -5 is positive 20. What about -2 times 7? Well, 2 times 7 is 14, but will the final answer be positive or negative? Well, I have a negative number, negative 2, being multiplied with a positive number, positive 7. When I have two different signs being multiplied together that way, the answer is negative every time. So negative 2 times 7 is negative 14. What about some division? Let's try a few divisions. What about negative 6 divided by negative 3? Well, 6 divided by 3 is 2, so the answer is going to be something like 2. But is it positive 2 or is it negative 2? Well, negative 6 divided by negative 3, I've got the same signs on top and bottom, and therefore the final answer is positive. So the answer is going to be positive 2. What if I had something like 42 divided by negative 7? Well, 42 divided by 7 is 6, that much we know, but now is it positive or negative 6? 42 on top is positive, negative 7 on bottom is negative, different signs on top and bottom, and therefore the final answer is negative, and so I get an answer of negative 6. And these are just some of the basics on which we'll build as we move through this Algebra I course together. There will be some other things that we'll talk about in terms of arithmetic basics that we'll have to walk through, maybe things involving fractions, for example, operations on fractions. You may have seen how to add and subtract, multiply and divide fractions in the past. And we'll also talk about a lot of other small things with arithmetic, which is what we've been doing here, adding, subtracting, multiplying, dividing numbers. But we'll use those, we'll see those as we march through the lessons together. I just wanted today to sort of get our feet wet and do at least a little bit of mathematics today before we closed out our lesson. Well, in today's lesson, we've talked about a number of things with regard to this course. We talked about the basic structure of the course, my philosophy on the Algebra I course, and we've started our mathematical walk together with the discussion of signed numbers and operations on signed numbers. Next time, we're going to talk about order of operations, including powers and parentheses. I look forward to seeing you then. As we prepare for our study of algebra, it's extremely important to understand some basic facts about order of operations. In today's examples, I'll focus on some challenges with order of operations in arithmetic, adding, subtracting, multiplying, and dividing numbers, as well as raising numbers to various powers. These concepts will also be important when we begin to simplify algebraic expressions later on. So let's get started with an example which you might not consider an order of operations problem, but which is, in my opinion, very important. So here's the example. I want us to compute 7 plus 2 plus 5 plus 3 plus 5 plus 9 plus 8. Now on the face of it, this looks straightforward enough, especially since the only operation involved is addition. One way to complete this problem is to simply start at the left with the 7, and then add that to 2, and then add in the 5, and so on. And here's what we would have then. 7 plus 2 is 9, and then 9 plus 5 is 14. 14 plus 3 then would be 17. 17 plus the 5 would be 22. 22 plus the 9 would be 31. And finally, 31 plus 8 would be 39. And that would be our final sum, 39. And that's the right answer. But I believe there's a second way to complete this problem, which is just as appropriate. And this approach relies on the fact that when you're adding or summing a long list of numbers, the order in which you sum them does not matter. Now, it's very important to understand that this is not true for other operations like subtraction or division. But it is true for addition. The order in which you add the terms does not matter. So I'd like to suggest an alternate way to solve this problem. And here's how. Notice that there's a 7 and a 3 in the original sum. I would suggest that we choose those two numbers and add them together to give us 10. Then there's also a 5 and a 5, and I'd like to add those two together as well to give us another 10. And then the 2 plus the 8, if we choose to put those two together, we'll also get 10. And of course, adding to 10 is a pretty natural thing to do. So our original problem could be seen as the following. Take the 7 plus the 3 and group them together with a pair of parentheses, mostly so that we can just see that we've grouped them together. And then do the same thing with the 2 plus the 8, and the same thing with the 5 plus the 5. At that point then we'll have 10 plus 10 plus 10 plus 9, and that's easily summed. It's equal to 39. And in my opinion, that's much simpler. Maybe you'll find the first way of doing the problem just as easy. That's fine, you can do it that way. But I think watching for those kinds of clues, hints, to make the arithmetic easier on us is a very wise thing to do. As I said a moment ago, the trick doesn't work for subtraction, and so I'd like to show you an example which proves that. So let's compute the following. I'd like to take 10 minus 5 minus 3. Now here's the right way to do it. It's always good to try to do the right way first just to make sure it makes sense. The right way is just to go left to right, starting on the left with the 10 and moving to the 5 and then the 3. So that would be the following. 10 minus the 5. I'm going to put those in parentheses just so I can see that first. 10 minus 5 is just 5. And now I would subtract the 3 from the 5, and I would have 5 minus 3, which is 2. In fact, we could even see that on a number line. So I'd like to do that now, just so you can see how these positive and negative numbers interact on the number line. 10 minus 5 minus 3 would be the following. You draw your number line, and you start at the 10, positive 10, which would be on your number line. Minus 5 means that you want to move to the left 5 units. So you start at 10 and you go 9, 8, 7, 6, 5. Now you want to subtract 3 more, which means you want to move to the left again 3 more units, and you would get 4, 3, and 2. And that is the correct answer, which is excellent. So 10 minus 5 minus 3 is 2. Now let me show you the wrong way, or a wrong way, to do this problem to illustrate order of operations. I could have grouped the 5 minus 3 on the end of the expression first and done 10 minus the quantity 5 minus 3. And that would have given me 10 minus 2, and of course that's 8. Well, obviously that's wrong. The right answer is 2. So we have to be careful when we're dealing with operations like subtraction and in fact division as well. The moral of the story is when you're adding and subtracting numbers, when there's some mixing of the operations going on, go left to right. It's the safest way to complete those problems. Well, let's try another example where there's a lot of mixing between addition and subtraction. So let's do the following. Let's take 10 plus 7 minus 5 plus 3 minus 18 plus 25. Lots of mixing between the additions and the subtractions. That's excellent. With all of that mixing thrown in, we would be very wise now to simply start at the left and move our way to the right. So here we go. We start at the 10 and we add the 7, we get 17. Then 17 minus the 5 is equal to 12. 12 then added to the next number, which is 3, is 15. 15 minus 18, that's negative 3. And then negative 3 plus 25 is equal to 22. The right answer is 22. Now, you might have stopped and said, I think I'm safe to do the arithmetic just a little bit differently. And you might have said to yourself, okay, I could have started with the 10 added to the 7, added to the 3, added to the 25. So basically all of the positive numbers there added together. That would have given us 45 if you add 10 plus 7 plus 3 plus 25. Then from there, with your 45, you could have subtracted the 5 to get 40, and then you could do 40 minus 18 to get 22. And that works. The final answer here was 22, but I just want to warn you that when the problems get more complicated later, when there are different operations floating around besides addition and subtraction, you're going to want to be careful about the order in which you perform your calculations. Okay, so we've seen some addition and subtraction in action. What other operations are there? Well, the next ones that come to my mind are multiplication and division. So I'd like to look now at some examples that have some multiplication and division mixed in. Let's start with just a multiplication problem. Let's just compute 3 times 4 times 5 times 5. So I'm just multiplying 3 times 4 times 5 times 5. Notice it's all multiplication. And an interesting property of multiplication is that just as with addition, it doesn't matter what order you multiply the numbers together. So just like addition, I can do the multiplication in any order I want. So I'm going to choose the following. First, I'm going to take the 4 and multiply it with the 5, and I'm going to get 20. And that's easy enough. And then 20 times the other 5 is 100. That's also pretty straightforward. And that leaves me multiplying 3 times 100, and the final answer then is 300. Now you might wonder why I chose the 4 times the 5 as opposed to doing the 3 times the 4 first. Well, the answer in my mind is pretty simple. I chose 4 times 5 first because it equals 20, and that ends in a 0. And of course, once you're multiplying numbers that end in 0, their products are pretty easy to take because you just keep tacking zeros on at the end. Well, we could have multiplied that problem from left to right, and it would have been fine. Let's do that real quickly to make sure we got the right answer. I would take from left to right 3 times the 4, and if I group those with parentheses, I can see that first. I'll have a 12. So now I have 12 times 5 times 5. And now I could just take the 12 with the 5 and multiply those together. 12 times 5 is 60, and that leaves me 60 times 5, and that, of course, is equal to 300. Well, that was our right answer, so that works perfectly well. But I just wanted to show you that with multiplication and only multiplication involved, you could reorder the terms. I think it's very important to watch for that as we move forward in this course. Anytime you can simplify your work in a legal way from a mathematical perspective, you should do so. And with addition and multiplication, you can. Okay, so let's move to another example now that mixes multiplication and division. So here's the problem. I want to compute 7 times 4 divided by 2 times 3 divided by 6. Now this has got a mix of multiplication and division throughout. And as with the example we did with the addition and subtraction mix, we have to be very careful here. And so the safest bet is just to go from left to right in this problem. So that's what I'm going to do here. Let's walk through the steps together to see what our final answer is going to be. So we started with 7 times 4 divided by 2 times 3 divided by 6. I'm going to group the 7 times 4 on the left with some parentheses. Again, I'm just trying to identify that that's what I want to work on first. And 7 times 4 is 28. So now I have 28 divided by 2 times 3 divided by 6. Now, moving left to right some more, I'm going to take the 28 divided by 2 and work on it next. And 28 divided by 2 is 14. So I now have 14 times 3 divided by 6. Again, we're just walking left to right through the problem. And now I have 14 times 3 divided by 6. 14 times 3 is 42. And I need to divide that by 6. 42 divided by 6 is 7. And that would be our final answer. Well, so far so good. Let's try a bit more complicated problem now and look at an example where we mix additions, subtractions, multiplications, and divisions. And the question we need to ask is, which operations get to go first? So for example, let's say you were doing 10 divided by 2 minus 3 times 5 plus 7 times 2. That's a pretty complicated mixture of addition, subtraction, multiplication, and division. So the question we need to ask ourselves is, do we just start on the left and work our way to the right? And the answer is definitely no. So here's a rule that we now need to keep in mind for order of operations. Multiplications and divisions take priority over additions and subtractions. Let me say it a slightly different way. Multiplications and divisions need to be done first before we ever do any additions and subtractions in a problem like this one. So for example, again, if I had 10 divided by 2 minus 3 times 5 plus 7 times 2, I would start left to right, but I would only do the multiplications and the divisions first. I'm going to skip the subtractions and the additions as I go and wait to do those in some sense at a second level. So let's start with the problem, working left to right, and only do the multiplications and divisions first. Well, I see that the first operation I meet is a division operation because it's got 10 divided by 2 at the beginning. So I'm going to do the 10 divided by 2, and that's going to give me 5. And so I'll be left now with 5 minus 3 times 5 plus 7 times 2. Now, walking left to right, I first see a 5 minus a 3. I don't want to deal with that. So the next thing I'm going to do is group the 3 times the 5, the multiplication involving the 3 and the 5. So now I have 5 minus 15 plus 7 times 2. Where did the 15 come from? It comes from the 3 times the 5. Excellent. Now I have 5 minus 15 plus 7 times 2. Well, reading left to right, I see a minus sign, then I see a plus sign. I need to ignore those at first. Then I see a multiplication, 7 times 2. That's what I want to do next. So I have 5 minus 15 plus 14, and the 14 comes from 7 times 2. Now notice what's happened. We've done all the multiplications and divisions. We now only have a subtraction and an addition to do. And so to complete the problem, I simply now go back to the front, to the left, and work my way to the right. So 5 minus 15, I do that first. That's negative 10. 5 minus 15 is negative 10 plus the 14 at the end, and negative 10 plus 14 is exactly 4. So the final answer for that long problem we began with is exactly 4. Well, let's do one more example of this type. I think it's important to have the practice. So let's do one more. Let's do 10 minus 5 times 8 divided by 2 plus 17 minus 13 times 2. That's a mouthful, I know, and you probably are thinking, I am never going to see a problem this complicated. Well, maybe, maybe not. But the point is, if we can do a problem this complicated, we can probably handle all the problems that are going to come our way at some point. So let's start. We have additions, subtractions, multiplications, and divisions mixed. Our rule says we must do the multiplications and divisions first. So as I start from left to right, I'm going to skip the subtraction that I see at the beginning, and the first thing I'm going to do is multiply the 5 with the 8. And when I do so, 5 times 8 gives me a 40. So I now have 10 minus 40 divided by 2 plus 17 minus 13 times 2. At that point, the first thing I then see is a division, 40 divided by 2. And if I compute that, I get 20. So I now have 10 minus 20 plus 17 minus 13 times 2. Notice that almost all the operations now are additions and subtractions, but there's that one multiplication at the end, the 13 times the 2. And it needs to be done first. And so we do it first. 13 times 2 is 26. And now we have 10 minus 20 plus 17 minus 26. Everything now is an addition or a subtraction. And that means I can start at the beginning on the left and now just march my way through left to right. So 10 minus 20 is negative 10, and then negative 10 plus 17 is 7, and 7 minus 26 is negative 19. And my final answer then is negative 19. Well, as I said, that was a very complicated problem, and you may have had to work through that in little bits and pieces, but that's okay. We're learning how to do this. We're practicing on some pretty complicated problems just to make sure we have these things down. Well, we've done addition, we've done subtraction, we've done multiplication, we've done division. Are there any other operations that we can consider that we can do on numbers? And the answer is yes. There is one more that comes to my mind at least, and that's exponentiation, or raising a number to a power. Now remember, in its most basic form, exponentiation is just repeated multiplication. So you should think of things like 3 raised to the 2 as just 3 times 3, which is 9. Or you could take a slightly more complicated example like 2 raised to the 5th power. That's just 2 times 2 times 2 times 2 times 2. Or 2 multiplied with itself 5 times. And that's equal to 32. So I want to work now with exponentiation as well as addition, subtraction, multiplication, and division. And the first question I've got to ask is, well, what are the order of the operations? How will these different operations be done, and in what order will they be done? And here's the new rule now as we introduce exponentiation. Exponentiation gets priority over multiplication and division. So exponentiation gets done before any multiplication and division. And remember, multiplication and division get done before addition and subtraction. It's a lot of words to say, and there are lots of big words, but it's okay. We'll have these rules down pretty soon. So let's look at a quick example. Here's one that involves addition, multiplication, and exponentiation. And let's see how the order of operations works out. Here's the problem. Let's do 5 plus 3 times 4 raised to the 2nd power. Some people would say 4 squared. So we have 5 plus 3 times 4 to the 2nd. Okay, remember the rule now. Exponentiation gets to go first over the multiplication and over the addition symbol. So the first thing we have to do is 4 to the 2nd power. Well, 4 to the 2nd power is 4 times 4. 4 times 4, 16. So we now have 5 plus 3 times 16. Well, we're down to an addition and a multiplication now. Do you remember which one gets to go first now? That's right, it's the multiplication. So it's not going left to right. We actually see the multiplication first. We have 5 plus 3 times 16, and 3 times 16 is 48. And that leaves us with 5 plus 48. We now get to do that. It's the last operation anyway. 5 plus 48 is 53. And that would be our final answer. Well, I'd like to look at one more example in a similar way. It also has an addition, a multiplication, and an exponentiation. And I'd like us just to practice knowing which of these operations we should do first. So here's the example. I want to do 6 times 8 plus 9 raised to the 2nd power. Or, as some people like to say, 6 times 8 plus 9 squared. Okay, I've got an addition, I've got a multiplication, and an exponentiation. If I start the problem going left to right, I'll definitely make mistakes. So I want to go by my order of operations rules. Let me do that first. Which operation goes first? In the operations that are here, exponentiation takes priority. It gets to go first. So I want to look at the 9 raised to the 2nd power. And when I do, I know that that's the same as 9 times 9. 9 times 9 is 81. So now I have 6 times 8 plus 81. Now, which one goes first now, a multiplication or an addition? Well, it's the multiplication. So notice here, for example, it would be wrong for us to do the 8 plus the 81 because we would be skipping over the multiplication to do 8 plus 81. I promise you'll get the wrong answer if you do that. So with 6 times 8 plus 81, I need to do the multiplication first. 6 times 8, well, that's equal to 48. And now I have 48 plus 81. And now I get to do that addition that I wanted to do. 48 plus 81, do a little bit of work there. We're going to get 129. So our final answer to that problem is 129. Well, there's one last thing that we really should consider with order of operations, and that is the idea of using parentheses. I've already hinted at how important they are, and we've used them a little bit today to help us isolate which part of the problem we should do first. So let's look at a quick example with parentheses just to see how the order of operations works there. So here's the example. 7 times the quantity 5 plus 3 and then minus 2. Now notice the parentheses have been put in here for us, and in fact, they enclose an addition symbol. And so now the question is, what do we do first? And here's the new rule that we need to keep in mind. When parentheses have been inserted in an expression like this, the parentheses get done first. So they get done before exponentiation, and they get done before multiplication and division, and they get done before addition and subtraction. So let's go through this example quickly now. We have 7 times the quantity 5 plus 3, then minus 2. The first thing we do is the 5 plus 3, and that's going to give us 8. So now we have 7 times 8 minus 2. At that point, we do the multiplication next. 7 times 8, that would be 56. And then we'll just have 56 minus 2, which is exactly 54. So that quantity is equal to 54. Now I'd like to show you very quickly, before we move to another example, what happens when you ignore those parentheses. Let's say that you just said, well, I'll just do the 7 times the 5 first. I'm just going to ignore those parentheses. At that point, you'd have 7 times 5, which is 35. Then you would add the 3 to get 38, and then you would subtract the 2 to get 36. And that's nowhere near the right answer that we wanted of 54. So when you see those parentheses, they must be done first, and then all the other rules we've talked about follow from there. Well, you know, we haven't done much with anything other than positive integers in this lesson, so I'd like us to look at an example now that involves fractions. And a little bit of a reminder of how we do operations with fractions certainly won't hurt us. So let's look at the following example. I want us to compute 1/2 plus 3/4 times 5/3 minus 1/4 squared, or 1/4 raised to the second power. Well, I see an addition symbol, I see a multiplication symbol, I see a subtraction symbol, and an exponentiation. So we need to use the order of operations rules that we've already seen. And what I'd like to do as we go through this example is just give you a quick reminder of how these different operations work with fractions. A little bit of a review won't hurt us. So, even with fractions, the order of operations rules are the same. The exponentiation gets to go first. And so that means I need to do the 1/4 raised to the second power. Now remember what that means. When you raise something to the second power, it simply means that you multiply it with itself. So 1/4 raised to the second power is 1/4 times 1/4. That's straightforward enough. In fact, I would write it down on my paper that way, 1/4 times 1/4, until you get comfortable with this. Well, how do you then multiply 1/4 with another 1/4? How do you do that product? Well, remember what happens when you multiply two fractions. Very important rule. When you multiply two fractions, you basically just multiply the numerators and multiply the denominators, and that becomes your new fraction. So in the case of 1/4 times 1/4, the answer's numerator, top part, is going to be 1 times 1. That's just 1. And by the way, that's an easy thing to forget as well. I've seen a lot of students tell me that 1 times 1 is 2. But remember, 1 times 1 is 1. So the new numerator is going to be 1. What about the denominator? Well, you have a 4 times a 4. You multiply those two together, you get 16. So the 1/4 raised to the second power is going to be 1/16, or 1 over 16. Well, now I have an addition, I have a multiplication, and I have a subtraction. Which one do I do next? I do the multiplication. So I have 3/4 times 5/3 right in the middle of the problem. I want to multiply those two together. Well, remember, we just talked about what you do. You multiply the numerators together and you multiply the denominators together, and that gives you the new result. So let's do that here as well. The numerator 3 with the numerator 5 multiplied together gives you 15. That's the new numerator. And then the denominator 4 and the denominator 3 get multiplied together, and that's 12. So that quantity, 3/4 times 5/3, is actually 15 divided by 12. Now here's an important point to make. That fraction is not in lowest terms. It's not reduced. 15 divided by 12, both the 15 and the 12 have a 3 in them, which could actually be factored out and canceled. And once you do that, that quantity will actually just be 5/4. In fact, you might have seen that you could cancel the 3 in the numerator of the first fraction and the 3 in the denominator of the second fraction, and you would have had 5/4 as a result. The point is that quantity is 5/4. So what do you have? You now have 1/2 plus 5/4 minus 1/16. And so now you need to add 1/2, 5/4, and then subtract 1/16. Well, how does one add 1/2 and 5/4? Remember what you have to do? You have to get what's called a common denominator. So you have 1/2 plus 5/4. What's the common denominator there? Well, it's going to be a 4. And so you have 1/2 plus 5/4. 1/2 is the same as 2/4 by multiplying the top and bottom by 2. So you really have 2/4 plus 5/4, which is 7/4. That's the front part of the problem. And now you have only one operation to go. 7/4 minus 1/16. Wow, so now I need a common denominator between 7/4 and 1/16. Well, that common denominator is also going to be the 16 that you have in the second fraction. 7/4, when you move it to a denominator of 16, requires you to multiply the numerator and denominator by 4. And that means that 7/4 would be the same thing as 28 over 16. Where does the 28 come from? It's the 7 times the 4. So what you really have now is 28 over 16 minus 1 over 16. And how does one subtract? Once you have the common denominator, you simply subtract the numerators and keep the same denominator. 28 over 16 minus 1 over 16 is 27 over 16. And that fraction is in reduced terms. You can't do anything else with it, so your final answer for that problem is 27 over 16. Now keep in mind, even with fractions, it's extremely important that you go through the order of operations carefully. You can't ignore those rules of exponentiation first, then the multiplication and division, then the addition and subtraction. Well, in this lesson, we've seen lots of examples of order of operations with addition, subtraction, multiplication, division, exponentiation, and the use of parentheses. These are going to be extremely important as we talk about simplifying algebraic expressions in future lessons. Next time, we'll talk about converting between fractions, decimals, and percents. I'd like to continue our discussion of math fundamentals today by taking a look at percents, decimals, and fractions. In all my years of teaching, I've noticed that many students struggle with converting between percents, decimals, and fractions. But it isn't something to worry about. I'd like you to think of it this way. It's about seeing things from different angles. For example, you might watch the same movie at a theater, and then on your laptop, and maybe later on a television. It's the same movie, but a different experience because you're seeing it in different perspectives. The same is true of percents, decimals, and fractions. It's the same math information, but in different forms. So today, let's take some time to refresh our memories on this important topic. First, before we get to the actual mathematics, let me take a moment to talk about why this topic is so important. I want you to think about some examples in real life where percents, decimals, and fractions arise. For example, when you have to look at sales tax or similar taxes, they're often computed as a percentage of the amount spent. Or let's say you're saving for a new kind of cell phone, and after months of working a part-time job, you come up with the exact dollar amount for the phone. You walk into the store with your money, you pick out the phone of your dreams, and you find out that you need $18.34 more because of the sales tax on top of the cost. Well, tips to waiters and waitresses at restaurants are given as a percent as well, sometimes 15%, 18%, 20%. So being able to calculate or at least estimate these kinds of percentages is very important. A lot of high school and college students earn their living waiting tables. So you may be in a situation where you want to know what you could be earning. Also, if you start off as a busboy or a dishwasher, you'll be getting about 5% of everyone's tips. You'd need to know how to figure that out to set your fair share. Lots of statistics are given as either percents, decimals, or fractions as well. 73% of the people surveyed said this, or 4/5 of the dentists in the US say, or the pitcher's earned run average is 1.632. So we need to be able to translate between percents, decimals, and fractions in order to make sense of this kind of information. Well, let's get to the nuts and bolts of converting these three types of numerical representations now. Let's start with percents. The word percent actually comes from a Latin phrase, per centum, which means by the hundred. So think of the word century, for example, which also starts with CENT, and it means 100. In the case of century, it's 100 years. So in a nutshell, a percent is just telling us what part of 100 is represented. For example, 75% means 75 per 100. So if you put it as a fraction, it's 75 divided by 100. You can read the line per if it makes better sense, but you can also think of it as division, 75 divided by 100. Converting from percents to fractions is pretty straightforward, at least for some basic cases. So what I'd like to do now is move into some examples where we convert percents to a fraction. The process of converting from percents to fractions is this. You use the percent amount that's given to you as the numerator or the top number of your fraction. And then the denominator of your fraction is always 100. Once you have your fraction written down, numerator over denominator, you simplify the fraction if possible, and you're done. So with these steps in mind, let's go to the following example. Let's convert 25% to a fraction. Well, given the rule I just shared with you a moment ago, you're going to use the 25 as the numerator of the fraction that you're going to get, and the denominator is going to be 100. Remember, the denominator is always going to be 100 when you convert from a percent to a fraction. So you have the fraction now, 25 over 100. You could stop there, but you don't really want to stop there because you should always reduce your fractions when you can. So let's do that now with 25 over 100. Notice, for example, that 25 has a factor of 5 in it, and 100 has a factor of 5 in it. So you can factor the 25 as 5 times 5, and you can factor the 100 as 20 times 5, and you can cancel one of the 5's from the top with one of the 5's from the bottom. That's going to leave you with the fraction 5 over 20. Now you could stop there, but again, you're not in completely reduced form. Notice that 5 also divides 20. 20 is equal to 5 times 4. And of course, the numerator can be written as 5 times 1. So you can cancel another 5 now from both the numerator and the denominator. Once you've done that, you're going to be left with 1 over 4. And that means that the percent 25% equals 1/4. There you go. You've just converted a percent to a fraction. So let's look at a second example now, where we convert a percent to a fraction. Let's convert 40% to a fraction. So the 40 has been given to us as a percent, and now we want to write it as a fraction. Well, the rule says we take that 40 from the percent, and we make that the numerator of our fraction. And what's the denominator? It's always 100. So you now have the fraction 40 over 100. Now, some folks, when they see a fraction like that, will very quickly cancel the 0 on top, or in the numerator, with the last 0 in the denominator. And that will give them 4 over 10. That's actually correct mathematically, but I'd like to make sure we understand why that's correct. So let me walk you through why 40 over 100 is actually 4/10. Well, 40 has a 10 in it, obviously, and 40 equals 4 times 10. 100 also has a 10 in it, and that's equal to 10 times 10. Now notice the factor of 10 in both the numerator as well as the denominator. Those two factors of 10, the one in the numerator, the one in the denominator, can be canceled. What does that leave you? It leaves you a 4 on top and a 10 on the bottom. And that's why 40 over 100 equals 4/10. Now we could stop there, but again, that fraction is not reduced. First of all, I see that the 4 is even and the 10 is even. That means they both have a 2 as a factor. And therefore, I want to factor a 2 out. So 4 is 2 times 2, and 10 is 5 times 2. And now I see the common 2's. I cancel them out of the numerator and the denominator, and what am I left with? 2 over 5, 2/5. 2/5 is reduced. I can't cancel anything more, and so I know my final answer. 40% equals 2/5. Well, I'd like to look at one more example of converting a percent to a fraction. And this example I actually do very importantly because I think students struggle with single-digit percentages, like 5%. But if we follow the process that I've laid out for you, we'll be fine. So here we go. 5% converted to a fraction means I take my numerator and make it 5. That's exactly what the rule tells me. And the denominator has to be 100. Again, that's exactly what the rule says. If I follow the rules of mathematics, it'll all work out. Now, 5 over 100. Is that in reduced form? Well, not exactly, because 100 has a factor of 5 in it. And of course, the numerator is 5. So I need to factor out the 5 from the 100, and that's equal to 20 times 5. And so here's what I have. I have 5 times 1 on top. I have 20 times 5 on the bottom. I can cancel those 5's. And when I do, I'm left with 1 divided by 20. And of course, that's in reduced form because of the 1 in the numerator. And therefore, 5% is exactly 1 over 20. Now, some students will actually tell me, well, 5% they think is 1/2 instead of 1 over 20. And that's because they'll incorrectly write 5 over 10 instead of 5 over 100 in replacement of 5%. The key here is not to write 5/10, but to write 5 100ths, because that is the process we were given. As long as we follow that process, we won't make a mistake. I want to look at one last example now of converting a percent to a fraction. I think it's very important to see an example like this, and I want us to make sure we follow our process. So here it is. I want to convert 100% to a fraction. Okay, now, a percentage with 3 digits like that, a 100, that sometimes throws people off. Don't fret over it. Let's just do what we're told to do with our process. So here we go. We take the number we were given in the percentage, that was 100, we make that our numerator. We then make our denominator 100, always 100, that's the rule. And so we have the fraction 100 divided by 100. Of course, a fraction where the numerator and the denominator are exactly the same is exactly 1. In essence, I can cancel the 100s from the top and the bottom, and I'm left with 1. So in this case, the fraction that I have left is 1. If you want to see it as a fraction, you could write it as 1 over 1, but ultimately it's just 1. So 100% is exactly 1. Well, let's talk about converting percentages to decimals now for just a moment. This is actually even more straightforward than the process for converting percentages to fractions. So here's the rule now for converting a percent to a decimal. You're going to take the percent amount that was given to you in the problem, and you want to move the decimal point 2 places to the left, and then remove or erase the percent sign. That's the whole rule. So, with that in mind, let's move to an example. I'd like to convert 25% to a decimal number. And the key here is to recognize where the decimal point is, given that it's not actually in the original problem. If you look at that problem carefully, you won't see a decimal point inside 25%. Of course, where is the decimal point? It's right after the 5. So, in order to follow my rule, 25% becomes 0.25, and the percent sign gets moved away. Why is it 0.25? Because I started with the decimal point on the right of the 5, I moved it one place between the 2 and the 5, and then a second place in front of the 2, and by moving it in those two ways to the left, I convert 25% to 0.25. So the decimal equivalent of 25% is 0.25. Let's look at a second example of converting a percent to a decimal, which has a little bit of complication to it, but we'll follow our rule and everything will be fine. I want us to convert 8% to a decimal. Now, the complication here, which isn't too bad, is that 8% is just a single digit, 8. There aren't two digits there like there was with 25%. So the question is, where does the decimal point go when I do this conversion from percents to decimals? Okay, in 8%, the decimal is just to the right of the 8. I now need to move it 2 decimal places to the left. Well, I start that process, I move the decimal place over once, just in front of the 8, and now where does the decimal point go if I need to move it a second time? Well, the answer is I could have put a 0 in front of the 8. That would have been perfectly legal. And when I put that 0 in front of the 8, it gives the decimal point a second place to go, if you will, once it's moved to the left. And that means that 8% is equal to 0.08. Remember, that extra 0 to the left of the 8 is perfectly legal. Now, you might have thought the answer was going to be 0.8 when I started that example of converting 8% to a decimal. But if you think about the rule that we were given, we were told that we had to move the decimal point 2 places to the left. And of course, 0.8 just moves the decimal place 1 place. And therefore, 8%, which is 8% or 8 out of 100, has to be 0.08. Remember, 0.08 is 8 hundredths, and that's why that 8 needs to be in the hundredths place. So 8% is 0.08. Keep in mind that 80% is 0.8. Let's do another example now of converting a percent to a decimal, and this time we'll go from having just 1 digit in the percent to having 3 digits in the percent. So here's the example. Let's convert 243% to a decimal. Now, first of all, don't be thrown off by the fact that 243 is bigger than 100. For some students, it feels a bit unnatural to have a percent larger than 100, but it can happen. For example, if you scored, say, 30 on your first algebra test, and then you scored 90 on your next algebra test, then the percentage increase in your course grade would actually be bigger than 100%. So it really is okay to have a percent bigger than 100. It doesn't happen as often as you see other percents, but it does happen. So I want us to get comfortable with that idea. Now, back to the problem we were doing. 243% converted to a decimal. Well, where's the decimal point in 243%? It's just to the right of the 3, just after the 3. So when you get ready to move your decimal point, you're going to move it 1 to the left between the 4 and the 3, and then once more to the left between the 2 and the 4, and that's moving your decimal place 2 places to the left. What does that give us? 2.43. So 243 as a percent, 243% is exactly 2.43. Okay, let's look at a quick word problem that involves percentages and decimals as well. Let's say Michael takes the astronomy club, which has 10 people in it, to lunch one day. Because of the size of their group, their tip percentage is required to be at least 18%. If the total bill for the food was $120, what does Michael have to pay as the tip? Well, the first thing to do is to convert 18% to a decimal, or a fraction, but I'm going to do it as a decimal right now because that's actually easier to work with. So let's start by converting 18% to a decimal. Well, the first thing I have to do is take my decimal point and move it 2 places to the left. When I do that, 18% becomes 0.18. Okay, that's nice enough, but now what? Well, the tip would have to be 18% of 120. Here's a question. What does the word of usually mean in word problems? Well, the answer is, and it's going to be the answer almost the whole way through this course, is that of means multiplication. So what Michael has to do is multiply the $120 for the bill by 18%, which is the same as multiplying 120 times 0.18. Well, that just leads us to a multiplication problem, which is going to need a few steps, but we can walk through it pretty straightforwardly. Let me do it with you this time. 120 times 0.18. We're going to start with the 8, start on our right of that number, and we're going to multiply the 8 into the 120, and that's going to give us 960. Now, we move away from that 8, and we move to the 1 that's in front of the 8. When we do that, we have to remember that whatever we write down next, below the 960, needs to be shifted to the left by 1 digit. And now we multiply that 1 into the 120, or multiply it with the 120. And of course, 120 times 1 is 120. That 120 goes below the 960, but again shifted 1 unit to the left. Of course, multiplying by the 0 in front of the 0.18 does nothing. So we're done with the multiplication part, and now we need to add the 960 and the 120, which have been put in the appropriate columns. When we do that, we're going to get 2160. Now, don't lose this point. The tip can't be $2,160. The meal was only $120. It doesn't make sense for the tip to be that large. So what happened? Well, we have to find where our decimal point goes. Notice that the decimal point in 0.18 was 2 to the left, and therefore in 2160 we need to move the decimal place over 2 to the left as well. And in the process, instead of $2,160, we're just going to have $21.60. And that makes a lot better sense for a meal of $120. Well, let's shift gears a bit and talk about conversions between fractions and decimals. First, the conversion from fractions to decimals is relatively straightforward. You simply have to do long division by dividing the denominator into the numerator. That's what I meant earlier when I said you can also read the fraction bar as a division line. So let's do the following example. Let's convert 3/4 to a decimal number. Well, I just want to divide the 4 into the 3. So I start by writing down a division symbol. I'm going to write the 4 on the outside of it. I'm going to put the 3 inside that division symbol. And now I have to do something very important, which we really should do right now. Once we've written in the 3 and the 4, we should explicitly note where the decimal point is after that 3. We write that in, and then we're actually allowed to add a few zeros after that. 3 is the same as 3.00 in this example. So now what I should have is my division symbol. I should have 4 written on the outside and something like 3.00, or maybe even 3.0000 on the inside of that division symbol. Once I've done that, I want to now write the decimal point above that division symbol, lining up with the decimal point inside the 3.00. That's where the decimal point is going to be in my final answer. So now I have a lone decimal point, if you will, by itself on top of my division symbol. But that's very important. It acts like an anchor almost to tell me where my answer is going to be. That alignment of those two decimal points is critical. We can't be careless with where we put that decimal point. Now, at this point, we can basically just divide as usual. Divide the 4 into the 3. Of course, 4 does not go into 3. 3 is too small. So now we ask, can 4 go into 30? Yes. 4 goes into 30 7 times. 7 times 4 is 28. 30 minus 28 is 2. And now we drop the other 0 and make that 2 into a 20. 4 goes into 20 5 times. And that means our answer is 0.75. So 3/4 is 0.75. By the way, why did we stop with the 0.75? Why didn't we go on? Well, because the remainders were all 0 after that. And it would have just been a waste of time to keep dividing 4 into 0. So 3/4 is 0.75. Let's try a second example where we convert a fraction to a decimal number. Let's convert 22 divided by 5, 22 over 5, to a decimal number. Well, let's do the same process we did earlier. We're going to take our division symbol. We're going to write the 5 on the outside. We're going to write the 22 on the inside, or underneath, as some people like to say. And I'm again going to put my decimal point at the end of the 22, and then I'm going to add some zeros to the right. Again, 22 is the same as 22.0, it's the same as 22.00, and so on. There's no need to write 10 or 12 zeros at the end. A couple will probably do here. Once I have that decimal point, 22.00, I make sure I write that decimal point above the division symbol as well, vertically aligning them. And now I start the division. 5 goes into 22, exactly 4 times. 5 times 4 is 20, and then 22 minus 20 is exactly 2. I then drop another 0, and 5 goes into that 20 now, exactly 4 times. No more remainder. And therefore, my answer is going to be 4.4. Let me point out that I needed that answer to be 4.4 and not 44 or 0.44. And the only way to ensure that that answer was right was to make sure my decimal points lined up in the appropriate way from the beginning. So make sure you're careful about where you put those decimal points when you do those conversions. Now, with that said, I want to show you another example of converting a fraction to a decimal number. And this time I want to convert 2/3 to a decimal number. So we're going to walk through the same process again, using 2/3 as my fraction. I'm going to draw my division symbol. The 3 goes on the outside because it's the denominator. The 2 goes on the inside or underneath the division symbol. I'm going to write my decimal point after the 2. I'm going to then write the decimal point just above that, above the division symbol. Now let's start the division. 3 goes into 2, no times. 3 goes into 20, 6 times. 6 times 3 is 18. 20 minus 18 is 2. I then drop a 0, and now I'm putting 3 into 20 again. Of course, 3 goes into 20 6 times again. 6 times 3 is 18. 20 minus 18 is 2. I drop another 0. 3 goes into 20 again. Oh my word, I'm caught in a vicious cycle. I can't get out of this. I just keep getting 6 after 6 after 6 after 6. It turns out that that's actually correct though, because the decimal equivalent of 2/3 is 0.666666 repeating forever. Some people would say it's just 0.6 repeating. This is an example of an infinite repeating decimal number. Sometimes it's written as 0.6 with a little bar over the 6. And that bar over the 6 means that you just repeat the 6 over and over again. So in fact, the conversion of 2/3 to a decimal is exactly 0.6 with a bar over it, or 0.66666, etc. You might say, well, why couldn't we just replace that 0.6 with a bar over the 6 with something like 0.7? I know about rounding. Why isn't 2/3 just 0.67? Well, 2/3 is close to 0.67, but it's not equal to 0.67. If you want equality, then you have to write 2/3 equals 0.67. 66666 forever. And that's the only way you can get an equals. Okay, what if we wanted to convert a decimal number to a fraction, which is the opposite process of what we wanted to do before? Well, let's do a few examples to demonstrate. Let's convert 0.42 to a fraction in reduced terms. Well, 0.42 is the same as 42 hundredths because the 2 is in the hundredths place. Remember, tenths and hundredths and thousandths and so on to the right of the decimal point. So that means that 0.42 is the same as 42 divided by 100, or 42 hundredths. Well, what that means is the conversion of 0.42 into a fraction must give us 42 over 100. If we simplify 42 over 100 a bit, we'll actually get our answer. Notice that 42 is even and 100 is even, so they must both have a 2 in them. And if you divide out the 2 from 42 and divide out the 2 from 100, you'll be left with the fraction 21 over 50. And that's the answer. 0.42 equals 21 over 50. Let's convert another decimal. How about something like 5.6 to a fraction in reduced terms? So let's begin by focusing our attention on the 0.6. Notice that 0.6 is the same as 6 tenths because the 6 is in the tenths place. And that means 0.6 is 6 tenths. Then I can write 5.6 as 5 and 6 tenths as a mixed number. And of course 6 tenths is the same as 3/5. So 5.6 is the same as 5 and 3/5. And that's the conversion. Simple as that. Now that mixed number could be written in another way, but for now I think we're going to leave it there. Now you might be thinking, how do I go from a fraction to a percent? That's a great question actually. Well, in fact, it turns out you can do it pretty straightforwardly in 2 steps. First, you take your fraction to a decimal. We've talked about that earlier in the lesson. And then you take that decimal to a percent. And once you've done those 2 steps, you've taken your fraction to a percent. Well, I know this review has been very brief, and I hope that it has reminded you of the various procedures for converting between percents, decimals, and fractions. The problems in your course guidebook will give you additional opportunity to perform such conversions. Throughout this course, you're going to have to do these kinds of things, so you'll want to make sure you practice now. Next time, we'll talk about variables and how to translate from word problems to algebraic expressions. One of the things that separates algebra from arithmetic or makes algebra algebra is the replacement of some of the numbers in our mathematical problems with things called variables. In essence, a variable is some sort of symbol, usually it's a letter from the alphabet, that represents one or more numbers in an algebraic expression. Using variables in certain algebraic expressions provides us with the needed flexibility to solve a wide range of problems. And so algebra is very important because it allows us to solve that wider range of problems that arithmetic just can't handle. But you might ask, what's an algebraic expression? Well, a definition is something like this. An algebraic expression is a combination of mathematical symbols which might include numbers, variables, and maybe symbols for operations as well. So for example, each of the following is an algebraic expression. You might take something like x squared times y times z cubed. That in itself is one algebraic expression. You might also have something like 5xy plus 7ab. That sum of 2 terms is also called an algebraic expression. Or you might take something like 2 divided by x plus 3 divided by y. Again, it's an algebraic expression. It has some numbers in it, like the 2 and the 3, but it also has those variables in it, like the x and the y that appear in the two denominators. Or you might have the expression that many of us are familiar with, pi r squared. That alone, pi r squared, is an algebraic expression. And I want to point something out there. You actually see two symbols besides the 2, of course. There's a pi and there's an r. The pi is actually a constant. It represents a number. Many of us know it as something close to 3.14. It's not exactly 3.14, but it's close. That is not serving as a variable in that case, but the r is. So there's really only one variable there, that's r, and the pi and the 2 are representing numbers. In all of these expressions that we've just mentioned, each of the letters from the English alphabet served as variables, in fact. And I want you to notice that the variables are often in italics. Every once in a while, you'll see a small letter x in an expression. It might not be italicized. That x is being used as a multiplication symbol. To be honest, we won't use such an x very often, just so we can avoid confusion between whether an x is a multiplication symbol or whether it's a variable. But they are used from time to time by various authors in textbooks and also on internet math sites, for example. So we will use a small x from time to time for multiplication. Otherwise, you might see something like a small dot, small filled-in circle, or maybe just parentheses around numbers and terms in order to represent multiplication. Well, if instead of these things that we've just talked about, we only had numbers, so for example, instead of x squared y z cubed, we had had 2 squared times 5 times 4 cubed, or something like 2 cubed times 5 times 4 cubed. We would have just had an arithmetic problem then, not really an algebra problem. But once we start to replace some of the numbers with variables, something like x squared times 5 times 4 cubed, then we have something called an algebraic expression. And that's where the algebra can come in. The flexibility of that letter x is very, very helpful. Well, throughout this course, you're going to encounter variables and algebraic expressions. And in this lesson, my goal is really to work with you on interpreting or translating English phrases into algebraic expressions. It's very important that you're able to set up math problems, word problems a lot of people call them, so that they can be solved using algebra. Ultimately, if all we can do is manipulate symbols, we're not really that useful. So we need to be able to take English phrases and convert them into mathematical symbols and expressions. So for the next few minutes, I want to translate a number of different English phrases into algebraic expressions. So for example, we're going to try to translate the phrase 5 more than n into symbols in just a moment. We'll also translate phrases like the difference of x and 7, 7 less than x, the product of y and 13, and the quotient of t and 8. So those are several English phrases that I want us to translate today, and I want to translate them into algebraic expressions or into mathematical symbols that we can then use in a mathematical problem. So let's start with the first phrase that we had, 5 more than n. Well, if I had 6 bananas and you have 5 more than me, then I would hope you would say that you had 6 plus 5 or 11 bananas. The same is true with the variable included. When we say 5 more than n, we translate that into mathematical language as n plus 5. We actually add 5 to our variable n. The phrase more than will typically translate to the operation of addition. And here's a tip that I think we want to keep in mind. Many problems are easily solved if you pay attention to these word clues, things like more than meaning addition. And from there, let's look at another example. The second phrase I gave you earlier was the difference of x and 7. The difference of x and 7. I want to translate that now into mathematical language, into symbols. One of the keys in this phrase is the word difference. Now you should ask yourself, what operation, addition, subtraction, multiplication, division, does the word difference correlate to or go with? Well, difference typically is going to go with subtraction. So when we say the difference of x and 7, we mean, in symbols, x minus 7. So that's an example where we see subtraction coming in to an English phrase. Okay, the third phrase was 7 less than x. 7 less than x. So now I want to try to translate that into an algebraic expression. Well, notice the similarity of this phrase to 5 more than x. We saw that just a few moments ago. In this case, though, we want a number which is smaller than x by the amount 7. Remember, we said less than. So I want an amount smaller than x by the amount 7. This then is another way of referring to subtraction. If you want something smaller, you should subtract. In fact, the answer here is x minus 7. And that's exactly the expression we saw with the phrase, the difference between x and 7. So we should just pause here briefly and notice two different English phrases can go with the same mathematical or algebraic expression. That's going to be very important that we'll see that flexibility as we're translating from the English into the algebra. Okay, let's look at another example then. The product of y and 13. Remember what we're trying to do here. We're trying to translate English phrases into algebraic expressions. This is going to be important for us as we build up our understanding of algebra. We'll be handed these word problems. We need to be able to translate them into algebra before we can actually complete the problems. So the product of y and 13. Well, you may have heard the word product in the past when you were doing math. To what operation does product refer? Well, the answer in this case is multiplication. So when we ask for the product of y and 13, the algebraic expression we should write down is y times 13. And remember, you might use a little dot between the y and the 13. You might use one of those little x's as well. I'm going to encourage you to practice using the dot instead of the x. Nothing wrong with the x, but I just want to avoid that confusion later on between the little symbol for x for multiplication and the variable x. Now, you should note that when you're multiplying a variable like y with a number like 13, it's perfectly fine to write it as y times 13. However, the typical practice is that we would write the number in front of the variable. And therefore, I would suggest we practice writing this as 13y, or 13 with a dot and y, instead of y times 13. They're both fine. They both mean the same thing, but 13y is more typical to write than y followed by a 13. Okay, so now let's keep going with our translation of these English phrases. The other one that I mentioned to you earlier was the quotient of t and 8. So now we've seen addition and subtraction and multiplication. What does the quotient refer to? Well, the answer is division. So the answer here is pretty straightforward. It's t divided by 8 or t over 8. Now let me point out, you have two different notations here then for that quotient. You can use the division symbol, the dot, the little horizontal line and another dot, or you can write it as a fraction with t divided by 8. That's a really good reminder that fractions are really about division. Now before we go anywhere, let's point out, you might have said, well, the quotient of t and 8, why wasn't the answer 8 over t? That's a great question. I'm glad you asked it. Well, what would the phrase need to be in order to have 8 over t as the answer? Well, we would have asked for the quotient of 8 and t rather than the quotient of t and 8. So it's very important that we watch the order in which these things happen in our phrases. It's going to be very important as you translate pieces of word problems into algebra. Okay, so let's move to the next level of problems involving variables and expressions. I want you to notice that in the previous examples we were given a letter, N or T or X or Y, which would stand for our variable. But in lots of word problems that you're going to encounter, the name of the variable is not going to be given to you. This means that you and I have to provide the variable names, and that means lots of choices. For some students, the vast number of choices can sometimes be paralyzing. I've known students who were just afraid to move forward with a problem because they didn't know what to call the variable. I don't want you to feel this way. When you're in doubt, just use a variable name with which you're comfortable. Just pick X or pick N. It won't be a problem to do so. There's not a better name over another name. Just choose one, and once you get comfortable with this practice, you'll start naturally picking various letters for your variables. But for now, don't try to get creative. Just use N or use X or use T if you'd like. Okay, with that said, let's look at an example where no variable was actually given to us. I want us to write an algebraic expression for the phrase 8 more than 2 times his age. 8 more than 2 times his age. Well, let's start by identifying the quantity which needs a variable. In this case, it's the phrase his age. So let's begin by letting A equal his age. How do we know that age was the quantity that needed a variable? Well, let's look back at the original phrase for a moment. 8 more than 2 times his age. Let's just walk through the phrase one word at a time and let's see what the words mean. 8 more than 2 times his age. Well, 8 is just a number. That's not going to need a variable. More than also is not a variable. It's not a noun, for example, so I don't need a variable for more than. 2 is a number. It's just going to be a 2 in a few minutes. And times, well, that's not going to be a variable, but I bet you know what it is going to be. It's going to be an operation. And the last phrase is his age. So the only thing that really needed a variable was his age. And I've declared that phrase, his age, to have the variable A. It's very important as we move forward mathematically that we declare what these variables are. So rather than just sort of jumping into the problem without stating that A is his age, we really should pause and write it down on your paper. A equals his age. Often the students who do jump right into a problem by defining a letter with a given variable can't remember later on what the variable letter actually stands for. And the problems are going to get more complicated, and you won't know whether A is his age or her age or something else. So especially when multiple variables are involved, you really want to declare at the beginning of the problem what each variable stands for. Okay, let's go back to our problem then. We've said now that A is his age. I want us to write the algebraic expression for 8 more than 2 times his age. Well, we know his age is A. What is 2 times his age represented by? Well, 2 times refers to multiplying his age by 2. So 2 times his age is represented algebraically as 2 times A. Again, you might write that just as 2 with an A, or you might write it as a 2 with a little dot and an A. Either way, fine. Now, how do we build up to 8 more than 2 times his age? Well, we need to focus now on the 8 more than. And that means that we want to add 8 to 2 times his age. Well, 2 times his age is 2A. Adding 8 to that is going to be 8 plus 2A. Or, as most people would probably write it, 2A plus 8. Either of those two answers, by the way, is fine. It's the commutative property of addition, which allows us to write either 8 plus 2A or 2A plus 8. Let's try another problem of this form where the variable is not given to us. Let's translate 10 less than 3 times the width. Okay, now the first thing we need to do is to declare our variables. What is the unknown here? It's going to be the width. And so I'm going to let W equal the width. Now I want to point out again, you could have let X be the width or T be the width. I chose W because it's going to remind me of width. Then we see that 3 times the width is simply 3 times W. So I can just write that as 3W. And lastly, I need to incorporate the 10 less than 3 times the width. Well, do you remember a few moments ago we looked at an example with less than, and we pointed out that that refers to subtraction. So the phrase 10 less than 3 times the width can be represented by 3W minus 10. And that's going to be 10 less than 3 times the width. Now you might have thought, I thought the answer was going to be 3 times the quantity W minus 10. So you'd be doing W minus 10, say in parentheses, and then multiplying on the outside by 3. Well, that would have been an answer to a very similar phrase, namely 3 times 10 less than the width. Well, that's a slightly different phrase, 3 times 10 less than the width. Notice that the difference is not in the words. In fact, the words are exactly the same. It's just that they're in a different order. So that order is going to really matter as we move forward. Well, we've spent some time discussing variables and then using variables as the building blocks to create expressions. Our next goal is to use these expressions to create equations. So here's a new term for us. Let's make sure we define it. An equation is simply a mathematical sentence that uses an equal sign. That's it. That's what an equation is. And typically that equal sign in a mathematical equation plays the role of the word is or equals in an English sentence. So for example, one way to translate the phrase 7 plus 3 is 10 is to write down the equation 7 plus 3 equals sign 10. Notice that the is there is replaced by an equal sign. One of the most important skills that we need in algebra is the ability to translate these word problems from English to equations. And we'll use that skill throughout the course. But for now, I want to look at a few small examples just to get us started. So let's do the following example. Let's translate this sentence into an equation. The area of a rectangle is the product of the length and width of the rectangle. Well, here we have not one and not two, but actually 3 different variables to define. And that's what we need to do when we start such a problem. So let's do that first. Since there are no numbers here to clue us in, we have to look more carefully at the language and pull out anything that might signal a number, that might be an unknown quantity. And for us, in this problem, those are going to be area, length, and width. All 3 of those things need a variable. So here's what we're going to do. Let's let A be the area of the rectangle. Let's let L equal the length of the rectangle. And let's let W equal the width of the rectangle. Now, the first part of the equation, the English sentence, is very straightforward because it just said the area is. And that means that the first part of the equation is going to be A equals. A for area and the equals sign for the is. But now I don't know what the right-hand side of my equation needs to look like. Well, according to the sentence, it's supposed to be the product of the length and width of the rectangle. Now, if we start to translate that a little bit, it means it's the product of L and W. Remember, L was for length of the rectangle and W was for width. But what's product again? We saw it earlier. It's multiplication. So the right-hand side is L times W, or simply LW. And therefore, I can glue all those pieces together and make my equation. It's just going to be A equals LW. Now you could have written that as A equals L, a little x, W, or maybe just A equals L in parentheses times W in parentheses. These would have all been fine. We'll probably move away from that little x symbol for multiplication, but using parentheses or a little dot, they will continue to show up. Okay, let's build another equation then, since we're on a roll. How about the following? Let's translate this sentence. The number of songs that Tom has on his iPod is 4 more than twice the number of songs that Sam has on his iPod. Okay, what's the first thing we do in these translations? We have to say what our variables are going to be. So I say we use the following. Let's let T be the number of songs that Tom has on his iPod. Nothing special about T, but that's my choice. And I'm going to let S be the number of songs that Sam has on his iPod. Why did I choose T and S? Well, T helps me to remember Tom, and S helps me remember Sam. But again, you could have chosen X and Y, or A and B, or lots of other choices. Now let's go to the translation. The left-hand side of the equation is easy. It's T, because T is the number of songs that Tom has on his iPod. The is in the sentence is going to be replaced by an equals sign. So up to this point, I have T equals and then something on the right-hand side of the equation. Now we need to work on what that right-hand side is. Well, twice the number of songs that Sam has is exactly 2 times S. Twice is going to be translated into that 2, and then of course it's going to be multiplied with S, the number of songs that Sam has. Because we know that the number of songs Tom has is 4 more than twice that number, we're going to add 4. So the right-hand side of my equation is 2S plus 4. And therefore I know that my equation's going to look like T equals 2S plus 4. Well, before we move away from that example, let me give you one more thought. In the previous problem, let's say that the number of songs Sam has is 10. I want to know, how many songs does Tom then have? Sam has 10 songs, and we know that the variable S stands for the number of songs that Sam has. So to figure out how many songs Tom has, I'm going to let S equal 10, and I'm going to plug that 10 in for S in the equation T equals 2 times S plus 4. And that means I'm going to have the following. T is going to equal 2 times 10 plus 4 because I've substituted 10 in for S. Well, I can now simplify that right-hand side. 2 times 10 plus 4, according to my order of operations, I need to do the 2 times 10 first. 2 times 10 is 20, and then I add the 4, and 20 plus 4 is 24. So if Sam has 10 songs, then Tom has 24 songs. Believe it or not, that's algebra. We just used algebra to help us figure out how many songs Tom has based on how many songs Sam has. Well, let's look at another example with this translation in mind and maybe even solve a quick algebra problem in the process. Let's translate the phrase, the number of boys in the class is 2/5 of the number of students in the class. Now, before we go anywhere with this example, let me point out that the class is going to consist of boys and girls. So when I say the number of students in the class, I'm referring to the number of boys plus the number of girls. Now let's go to the actual translation. Again, the phrase, the number of boys in the class is 2/5 of the number of students in the class. We need to start by defining variables. It's the first thing we need to do. There are 2 unknown amounts in the problem. The number of boys in the class and the number of students in the class. Notice that the number of boys in the class, it's going to be less than the total number, but that's fine. We don't have to worry about it at this point. So let's let B be the number of boys in the class, and let's let S be the number of students in the class. So I have 2 variables, and I'm going to work with those to do my translation from the English into an equation. The first phrase that I see in my sentence is the number of boys in the class. Well, thanks to the declaring that I did earlier for my variables, that phrase is exactly B. It's that simple. And the word is in the sentence is going to be replaced by an equals sign. So my equation is B equals something. Now, the right-hand side is a little more complicated, but not by much. So let's look at that right-hand side of the equation now. It comes from the phrase 2/5 of the number of students in the class. Well, the number of students in the class is S. So what I want is 2/5 of s. So now we have a question. How do we translate the word of into algebra? Well, here's a very important rule to keep in mind. In these kinds of sentences, the word of refers to multiplication, and it's going to do that always. So keep in mind when you see something like 2/5 of s, it means 2/5 times s. And now I can tell you my equation. It's going to be b equals 2/5 times s. And there you go. There's the equation that we were asked to write. Well, let's use it. Once we have such an equation, it would be nice to use it somehow. So let's talk about the following question. Let's say the number of students in the class, total number of students, is 35. How many of those students then are boys? Okay, here's an important question that we need to ask ourselves. Which variable is going to get that 35 plugged into it? We have two variables. We have the variable b and we have the variable s. We need to know which one is going to get the 35 plugged in. Well, what did that 35 represent? The total number of students in the class. And if you go back to the beginning of the example, when we wrote down what our variables were going to be called, we know that the total number of students in the class is s. So that 35 is going in for s. And that means we're going to plug 35 in for s into the equation. B equals 2/5 times s. So let's do it. Plugging in 35 for s gives us b equals 2/5 times 35. Now I need to multiply that fraction 2/5 with the number 35. I don't know about you, but for me, it's better to write 35 then as 35 divided by 1. That always seems to help me, because then I have two fractions sitting next to each other, a numerator on one and a denominator, and then another numerator and another denominator. And at that point, I can see things more clearly, like how to multiply and maybe some cancellation as well. When you write 2/5 times 35 over 1, can you see any of the cancellation that's natural there? I hope so. Notice that the 5 and the 35 cancel just a little bit, and the 5 just becomes a 1 in the denominator, and the 35 becomes a 7. So now you have 2 over 1 times 7 over 1, which of course is just 2 times 7. And that's exactly equal to 14. So the number of boys in the class, remember B stands for the number of boys, is exactly 14. And it's important that you always stop at the end of such a problem and ask yourself, what does the number that I got at the end mean? In this case, that 14 means the number of boys in the class. Well, today we've learned about variables, algebraic expressions, and equations. Very important building blocks for a lot of the algebra that we're going to see in this course. We'll definitely see them again very, very soon, and we'll see them often. Next time we'll talk about performing operations on algebraic expressions, and I'll see you then. We've seen algebraic expressions in our previous conversations, and today I'd like to discuss how we can simplify expressions as well as combine expressions with the usual operations, things like addition, subtraction, and so on. But before we do that, I'd like to spend some time on operations between expressions, and I'd also like to talk about evaluating expressions. So let's start with the following example. I want to evaluate the expression t plus 5 quantity cubed minus 4t when t equals -2. Well, when we're asked to evaluate an expression, it means we're supposed to plug in the numerical values for each of the variables and then simplify the result. We've done a little of that already in a previous lesson, but I want to work on some more complicated expressions today. Here we have only one variable, it's the letter t, and we're to plug in -2 for t. That's what we mean when we say evaluate. Well, that would give us -2 plus 5 cubed minus 4 times -2. Now, from our past conversations on order of operations, where we have to handle things inside parentheses, then exponentiation, then multiplications and divisions, and then additions and subtractions, we need to do the following. We're going to take the negative 2 plus 5 that's inside the parentheses, and we're going to simplify that first. Negative 2 plus 5 is 3. So now I have 3 cubed minus 4 times negative 2. The next thing to do is the exponentiation. And so I'm going to take the 3 cubed and turn it into 27. Remember, 3 cubed is 3 times 3 times 3. That's actually going to be important later on in this lesson today. So now I have 27 minus 4 times negative 2. Well, 4 times negative 2, remember that's negative 8, because when you multiply two signed numbers and their signs are different, you get a negative answer. So now I have 27 minus negative 8. And 27 minus negative 8 is the same as 27 plus 8. At that point, I just add those two numbers and I get 35. And my final answer is 35. Let's look at a second example of evaluating expressions which highlights different types of expressions involving exponents. I want to do the following. Let's evaluate AB whole thing squared and A times just B squared for A equals 3 and B equals 4. So let's begin with AB whole thing squared. If you use A equals 3 and B equals 4, you're going to have the following. AB squared is 3 times 4 whole thing squared. Now you need to do the work inside the parentheses first. 3 times 4 is 12, and 12 squared, or 12 raised to the 2, is exactly 12 times 12, which is 144. So AB squared, when A is 3 and B is 4, is 144. Now next, let's do the same kind of evaluation, but with the term AB squared. Well, in that case, you have 3 for A and 4 times B, 3 times 4 squared. Notice that the squaring is only happening to the 4. That's very, very important here. And you have to do that exponentiation before you do the multiplication. Remember your order of operations. 4 to the second power is 16, and that gives me 3 times 16, which is 48. Now, I need you to notice that those two answers are very, very different. 144 and 48 when we did those two evaluations. And that means that the two expressions themselves are very, very different as well. They look similar. One just looks like it has a few parentheses and the other doesn't, but in fact they're very, very different. So note that as we walk through this algebra. In fact, AB to the second power is AB times AB. And if you put all that together, you have AB, AB. And you can move the A's together and move the B's together, and you'll get A to the second times B to the second. Notice now in that case, the A has been raised to the 2. But in the other expression, A times B squared, the A was not raised to the 2. So they're very different expressions, and they're going to give you very different evaluations. Let's look at one more evaluation example before we move on in the lesson. Let's take a word problem of the following form. A farmer has a plot of land, and it's shaped like a right triangle. The area, which I'm going to call A of that triangle, is given by A equals 1/2 B times H. Now, what is B and H in this case? Well, B is 100 feet and H is 300 feet. Let me just point out what B and H really stand for. B is often thought of as the base of your right triangle, and H is often thought of your height, or of the vertical part of that right triangle. Well, with B equals 100 and H equals 300, I'd like to determine the area of the farmer's plot of land. So it means I want to evaluate the expression A equals 1/2 B times H when B is 100 and H is 300. That's going to give us 1/2 times 100 times 300. And if we multiply the 1/2 with 100, it's going to give us 50. 1/2 of 100 is 50. And that means I need 50 times 300, which is 15,000 square feet. So the farmer with this right triangle piece of area has exactly 15,000 square feet to work with. Okay, so we've seen several examples of evaluating expressions at different numerical values. What are some other ways that an expression can be manipulated or simplified? Well, just as with numbers, we can do addition, subtraction, multiplication, and division, and even exponentiation on our expressions. So we're going to look at some rules now, and we're going to follow those rules. They're going to look very similar to rules that we've already seen, but now we're going to do those rules on algebraic expressions, not just numbers. So let's start by adding two expressions. So what's the key here if I wanted to start adding two expressions? Well, if they involve variables, then it's very important that the expressions must be identical except for the number in front in order to actually add those two pieces together. Well, what does that mean? Well, the number in front of an expression is known as its coefficient. And so for example, the coefficient in 3x to the fifth is exactly the 3 that's in the front. If I wanted to add 3x to the fifth and 6x to the fifth, I actually can. It's okay that the 3 and the 6 are different. The key is that the powers on the x's are the same. They're both 5. And therefore, 3x to the fifth plus 6x to the fifth is 9x to the fifth. It's just like 3 apples plus 6 apples is 9 apples. But I would not be able to add something like 2x to the fourth and 3x to the fifth because the powers on the x's are different. In one case it's a 4, in the other case it's a 5. That would be like 2 apples and 3 oranges. There's nothing more you can do with that. Let's look at a few other examples of trying to add some expressions together. Let's consider something like 7x times y squared and 3x squared times y. Notice that the power on x in the first expression is 1, but the power on x in the second expression is 2. By the way, I should pause just for a second. In that first expression, 7xy squared, you don't see a 1 on that x as a power. When the power is not written there, the power is 1. So 7xy squared is the same as 7x to the 1 times y to the 2. Okay? Notice that the powers on the x's then are different between the two expressions. In 7xy squared, the power on x is 1. In 3x squared y, the power on x is 2. As soon as that difference happens, I cannot add those two terms together. But what about something like x times y squared plus x times y squared? Can I add that together? Can I simplify that expression? And the answer is yes. Xy squared plus xy squared is exactly 2xy squared. How about something like 7xy squared with 3xy squared? Well, except for the 7 and the 3, which are the coefficients in front of the terms, these are the same expression. So they can be added together. And in this case, we would have 7xy squared plus 3xy squared equals 10xy squared. And how about something like 7xy squared and 3y squared x? Well, at first those don't look like the same expressions if you read them. But if you look at them just a bit closer, you realize that the 3y squared x can also be written as 3xy squared. Remember that property of multiplication? We called it commutativity. When you can commute the terms inside by multiplication, you can rewrite that term. So that expression becomes 3xy squared. Once you've done that rewrite, you realize that what you're really doing is adding 7xy squared and 3xy squared. Both of those are the same term, except for the coefficient in front, so they can be summed together, and you get 10xy squared. Okay, let's try a more complicated example now. Remember, we're just trying to simplify these terms, simplify these expressions. I'm going to give us a bit more complicated one now. Let's simplify 5a squared b plus 3ba squared minus 6a squared b plus 8 times ab whole thing squared. Well, I want to combine all these terms. I want to shorten the expression as much as possible. That's what I mean by simplifying. So let's just march through this. as we go through. We have 5a squared b plus 3ba squared minus 6a squared b plus 8 times ab squared. The first two terms can actually be grouped together once I realize that the 3ba squared is the same as 3a squared b. And when I group those two together, I realize they are the same term, except for the coefficients, but that's okay. 5 plus 3 is 8. So those two terms are going to become 8a squared b, and then I have minus 6a squared b plus 8 times ab squared. Well, 8a squared b minus 6a squared b is just 2a squared b. Subtraction is going to work just like the addition. And so I'll have 2a squared b plus 8 times ab squared. Remember from our earlier comments that ab whole thing squared is a squared b squared. And because of that, I cannot simplify this expression anymore because one of the terms is of the form a squared b and the other one is actually a squared b squared. So my final answer is as short as it can be. Well, in a nutshell, like terms can be added and subtracted. Just as 7 bananas plus 3 bananas gives me 10 bananas. But 7 bananas plus 3 apples cannot be simplified. And so when I'm looking for like terms for addition and subtraction, I simply need to see if the two expressions are identical except for the possibility of the coefficients in front, the numbers in front, being different. Well, let's talk next about multiplication of expressions. So before we do so, I want to remember a few rules where exponentiation is involved when we're multiplying two terms. So here's a pretty straightforward example. What is a cubed times a to the 5th power? I just want to multiply those two together. And when I do so, a cubed times a to the 5th is the same as a raised to the 3 plus 5, and a raised to the 3 plus 5 is a to the 8th. Now, one error that some students fall into here when they're multiplying a cubed times a to the 5th is that they want to multiply the exponents. And if you did that, of course, you would actually get a to the 15 because 3 times 5 is 15. But that's wrong. A cubed times a to the 5th is a to the 8th. And you can remember that if you write it all out in long form. A cubed is a times a times a, and another a to the 5th multiplied with it is a times a times a times a times a. Get this long string of a's being multiplied together, and what do you have? You have a times 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 a. And that's exactly a raised to the 8th power by definition. So when we're working with these exponents and we multiply two terms together, we want to add the exponents. And that's the first rule we need to remember. When you have any number x, which is not equal to 0, and you have any two exponents, let's say a and b, so that you have x to the a times x to the b, that quantity can be simplified to give me x raised to the a plus b. So x to the a times x to the b equals x to the a plus b. There's a similar rule for division that we need to remember, and in that case, you actually have to subtract the exponents instead of adding. So when you have x to the a and you divide it by x to the b, it's the same as x to the a minus b. So an example would be the following. Let's say you had x to the 7th and you wanted to divide that by x cubed. Well, by the rule I just gave you, x to the 7th divided by x cubed would be x raised to the 7 minus 3. 7 minus 3 is 4, and therefore the final answer would be x to the 4th. We can look at that again, just like I did with that long string of a's a moment ago, by doing the following. X to the 7th is x times x times x times x times x times x times x in the numerator. Divide that by x times x times x in the denominator, which is x cubed. And now you can start canceling x's from the numerator and the denominator, and you'll be left with x to the 4th on top divided by 1. All of the x's in the denominator will go away. And of course, x to the 4th divided by 1 is just x to the 4th. Where did that 4 come from? It's just 7 minus 3. Well, I'd like to say we ought to look at a numerical example just to make sure this is okay. So let's do that real quick with some powers of 2. Let's say you wanted to find 32 divided by 4. So using long division, of course, 32 divided by 4 is just 8. So I know that 32 divided by 4 is just going to be 8 as my final answer. What if I had written it, though, as powers of 2 instead? Well, 32 is 2 raised to the 5th power, and 4 is 2 raised to the 2nd power. And 32 divided by 4 then would be 2 to the 5th divided by 2 to the 2, or 2 squared as some people say. And if you start canceling 2's out of the numerator and denominator, you'll see that 2 to the 5th divided by 2 squared is exactly 2 cubed. And that 3 is coming from 5 minus 2. So in fact, my rule for dividing 2 powers of the same variable really does hold. So these 2 rules that I just shared with you for multiplying and for dividing powers are extremely important. You'll want to memorize them now. You'll want to keep remembering them, refreshing your memory as you go through this course. You're going to want to become comfortable with these 2 rules because you will see them often as we walk through algebra together. Now, a lot of the rules in algebra are presented as an example, so you really should memorize those, but you should also think through about what's going on. Memorize the example, but also memorize the rule. I think that's going to be extremely important. Okay, let's look at some examples of multiplication and division of expressions now, which are a little more complicated. So here's one, which involves only multiplication. I want us to simplify the following expression. U to the 5th times v cubed multiplied by t squared times u to the 7th times v to the 4th. Notice that we're really just multiplying 5 small terms together. A u to the 5th, a v cubed, a t squared, a u to the 7th, and a v to the 4th. Okay. Next, I'm suggesting that we reorder all the terms to our advantage. Remember, we're allowed to switch the way the terms are written thanks to the commutative property of multiplication. So let's get all of the letters, or the variables, next to one another that are the same. And if I do that reordering, I'm going to have t squared times u to the 5th times u to the 7th times v cubed times v to the 4th. Notice I've got the u's together now and I've got the v's together. And now I recognize that I can use the rules that I just mentioned to you a moment ago. In particular, I can merge the 2 powers of u together and write that as u to the 5 plus 7. And I can do the same thing with the powers of v, and I get v raised to the 3 plus 4. Notice that the t squared doesn't have another term with which to combine. It's not a problem. It's a bit lonesome, but it's not a problem for us mathematically. The t squared is just going to sit out in front by itself. And once I add those exponents together, I'm going to have t squared times u to the 12th times v to the 7th. And that's going to be my final answer. Okay, I would suggest then that we simplify a slightly more complicated example than the one we just did by introducing some other types of exponents. So let's simplify the following. 6a to the 5th times b to the 4th times c cubed, that's one term, times 5a to the negative 3 times b to the 8th times c to the 0 times 2a to the negative 2 times b to the 3rd times c to the 7th. Okay, now notice here that I've actually introduced a lot of different situations compared to the previous example. First of all, we have numerical coefficients floating around. They're the numbers out in front. And in this case, they are 6, 5, and 2. They're not a problem, but they are there. Notice I've also thrown in a 0 exponent, c to the 0th power. Again, that's not a problem. It's a little odd looking, but it's okay. And we have some negative exponents now. They're also not a problem. The rules will still follow even with those negative exponents. So let's just work with them as if they were just any other number. So first, let's rewrite the product so that the like terms are near one another. Again, I want to try to get the variables, which are the same letters, next to one another so I can apply my rules. Notice that I can also pull out or put together the numerical coefficients out in front. I can literally pry those out and put them in front of the variables. And that's exactly what I'm going to do here. The following, I'm going to have 6 times 5 times 2, those were the numerical coefficients, times a to the fifth times a to the negative 3 times a to the negative 2 times b to the 4 times b to the 8th times b to the 3rd times c to the 3rd times c to the 0 times c to the 7th. It's a mouthful to say, but it's all right there on the screen. Now, the product of the numerical coefficients is straightforward to do. We're simply going to multiply those like an arithmetic problem. 6 times 5 times 2, and that's going to give me 60. So the final answer's coefficient in front is going to be 60. After that, multiplying all those terms together, remember, means that we just add the exponents. And so that's what I'm going to do here. I'm going to end up with 60 times a to the 5 plus negative 3 plus negative 2 times b raised to the 4 plus 8 plus 3 times c raised to the 3 plus 0 plus 7. And now I just add those exponents, and what do I get? Well, I get 60 times a to the 0 times b to the 15th times c raised to the 10th. Now, most people would write that as 60 times b to the 15th times c to the 10th, since a to the 0 is 1, as long as a is not 0. And so I'm going to suggest that our final answer for simplifying all of that work is 60 b to the 15th times c to the 10th. And before we move to another example, I just want to point out we started with a big mathematical expression before we got down to this much smaller expression. And I think it's very important that we notice that these algebraic rules are allowing us not to work with big expressions, but actually simplify them down to much smaller ones. Okay, so let's look at another example now. Let's look at one that involves some division. We haven't done much with division yet in this lesson. So let's simplify the following. 20 x to the 5th y cubed divided by 5 x squared y to the negative 4th. Now I see that negative exponent. It's okay. It's really not a problem. The rules will still follow even with that negative exponent. But I do want you to notice that this is the same as simplifying 20x to the 5th y cubed divided by 5x squared y to the negative 4. From here, we should be able to handle the numerical coefficients first, and pretty simply. The numerical coefficients are 20 divided by 5, and that of course is the same as 4 divided by 1, or just 4. So our original ratio, or quotient, is now simplified to 4x to the 5th y cubed divided by x squared y to the negative 4. Now we need to use our division rule that I mentioned earlier. I want to put together the powers of x, and I want to put together the powers of y. The rule in that case was that the exponents had to be subtracted one another. The power on the x in the numerator minus the power on x in the denominator, and the same for the powers of y. So I'm going to have 4 times x raised to the 5 minus 2 times y raised to the 3 minus negative 4. Since 3 minus negative 4 is the same as 3 plus 4, which is 7, we know that our final answer for this problem of simplification is 4 times x cubed times y to the 7th. Well, I'd like to think a bit about simplifying some more complicated expressions, and so let's do one more, at least for now, which involves exponentiating something that's even larger. So here it is. Let's look at the following example. Let's simplify a cubed times b to the 5th all squared. Well, a cubed times b to the 5th all squared means exactly a cubed b to the 5th times a cubed b to the 5th. It's that simple. When you square something, you just write 2 copies of it down, one after the other. And so now you have a cubed times b to the 5th times a cubed times b to the 5th. You can now use your commutative property of multiplication to get the a's next to each other and to get the b's next to each other. And at that point, you can use your rule that says you add the exponents in order to simplify. And so you'll have a cubed times a cubed, which is the same as a to the 3 plus 3. And you'll have b to the 5th times b to the 5th, which is the same as b to the 5 plus 5. At that point then you have a to the 6 times b to the 10. And that's just using the rules that we've seen. If we follow those rules, we'll be fine. So I'd like to look at the following example of simplification, which is by far the most complicated one we've seen in the lesson. I want us to simplify the following expression: a cubed times b to the fifth divided by c to the fourth times a squared times b, and I want to raise that whole quantity to the seventh power. That's pretty complicated compared to the other things that we've seen, but it's okay. Let's just follow our rules and let's see where they take us. Well, the first thing I would really like to do is I'd like to split up that fraction into actually two pieces with that power of 7 there. And what do I mean by that? Here's what I mean. The quantity I started you with is the same as a cubed times b to the fifth raised to the 7th power divided by c to the fourth times a squared times b raised to the 7th power. How do we simplify then an expression along those lines? Well, a cubed times b to the fifth all raised to the 7th is the same as writing down a cubed times b to the fifth 7 times. And that means that you would actually have an a cubed 7 times, and you would have a b to the fifth 7 times. So in that numerator, what would the power on a actually be? Well, it would be 3 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3. It would be 21 as the total. And so you would have a to the 21. What would the power on b be? Well, you'd have to add 5 to itself 7 times. And of course, that's 35. So your numerator would become a to the 21 times b to the 35. What does the denominator become? Well, I know how to handle the c to the fourth. I'm just going to write it down 7 times. And if I write down c to the fourth times c to the fourth 7 times, it'll be the same as c to the 4 plus 4 plus 4 plus 4 plus 4 plus 4 plus 4. What is all that 4's added together? It's 28. And so I would have c to the 28th power in the denominator. I'd also have an a to the 14th power, and I would have a b to the 7th power if I use the same sorts of techniques. And now once I've written the numerators in this sort of expanded form, I can now combine them with the rule about dividing 2 powers of a variable. Well, let's do that here. I would have a to the 21 on top divided by a to the 14 on the bottom, and that's a to the 21 minus 14, which of course is a to the 7th. So part of my final answer is going to be a to the 7th. I would also have a b to the 35 on top divided by a b to the 7th. And if I subtract those two exponents, I'll have b to the 35 minus 7, which is b to the 28. So now I have a b to the 28th in my final answer as well. Notice the c doesn't have anything to cancel with in the numerator, so I'm simply going to have a c to the 28th in the bottom. And so my final answer is going to be a to the 7th times b to the 28th divided by c to the 28th. Well, that was a complicated problem. Definitely the most complicated we've seen in the lesson. But that's okay. As long as we follow our rules, we'll be fine. By the way, we've actually used a third rule for exponents in this last example. And that rule is this. If you have x raised to the y, and then that whole quantity is raised to the z, it's the same as taking x and raising it to the product y times z. So for example, in the earlier example, we had c to the 4th raised to the 7th power. That's the same as c to the 4 times 7, which is c to the 28. And we saw that in that example. Today we've looked at a number of very important rules for simplifying algebraic expressions. Next time, we'll begin talking about principles of graphing in 2 dimensions. You'll probably want to get some graph paper and a pencil as we work on that lesson together. I'll see you then. Throughout this course, we'll spend a good deal of time drawing the graphs of various equations in 2 dimensions. We'll especially spend a lot of time drawing the graphs of straight lines. Now, as I mentioned in the previous lecture, you're going to need graph paper and a pencil if you want to do these problems with me throughout this lesson. I want to spend our time together in this lesson talking about some basics related to graphing in the coordinate plane or the XY plane. As we start, let me share a bit of history about graphing in the XY plane and also share a number of vocabulary terms we'll use throughout the course. In fact, there will be a number of vocabulary terms throughout this lesson. It's okay, we'll learn them as we go, but there will be several of them, so I just wanted to warn you. First, let's talk about that history. The XY plane, which is sometimes called the Cartesian plane or the Cartesian coordinate system, is named for the French mathematician and philosopher René Descartes, who was born in 1596 and died in 1650. One of Descartes' major contributions to mathematics was his desire to unite algebra and geometry, or to try to visualize algebra. With this in mind, the Cartesian plane emerged in Descartes' work. And it served as an extremely important tool for those who developed calculus, namely Newton and Leibniz, who completed their work in the latter part of the 17th century. So, what is this Cartesian plane, or XY plane? Well, simply put, it's the plane or 2-dimensional space formed by 2 number lines. One is horizontal and the other is vertical, so that they intersect at right angles. The horizontal number line, or horizontal axis, is often referred to as the x-axis. The vertical axis is often called the y-axis. There's nothing special about using the letters x and y here. Most of the time, these axes are called the x and y axis. But if we're working with different variables other than x and y, we can certainly change the names of the axes if we need. Now, let's take a closer look. Now, these axes intersect at a point. Remember, it's going to be at right angles, and the point at which the intersection occurs has a special name. It's called the origin. So we're going to want to remember that the origin is right in the middle, right where the 2 axes intersect. And those 2 axes actually cut the Cartesian plane into 4 sections. And those sections are called the quadrants. So, if you take a look after you've drawn an x-axis and a y-axis, you should think about labeling the parts of that drawing. So you can label, for example, the origin, which is the point where the 2 axes meet one another. You can label the x-axis. Often people will label the x-axis with an x on the right-hand side, and you can label the y-axis, and often people label that y-axis with a y at the top of that line segment. Now, once you've done that, you can then talk about the pieces of the plane that have been cut out, if you will, by the axes. And in this case, there are 4 pieces. They sort of look like rectangular pieces, although in fact they sort of go off to infinity, so they're not really rectangles. But those 4 pieces are called quadrants. And here's how those quadrants are numbered. Quadrant 1 is going to be in the upper right section of the plane, of the Cartesian plane. Quadrant 2 then is the upper left section of the Cartesian plane. Then quadrant 3 is the lower left section, and quadrant 4 is the lower right section. So the quadrants go 1, 2, 3, 4. In some sense, it might be good to remember that they go counterclockwise, starting in the upper right corner. Now, the origin, the axes, and the quadrants give us the skeleton of the Cartesian plane. But from here, the natural question to ask is, well, how do we label the points in the plane? In fact, that's probably the biggest question of this lesson. How do the points in the plane get labeled? Otherwise, this whole Cartesian plane isn't really helpful to us. Well, let's look at a few more terms, a few more vocabulary terms that we need as we try to decide how to label the points in the plane. Each point in the plane is identified by two numbers. We're going to call those numbers coordinates. There's going to be an x-coordinate and a y-coordinate. The x-coordinate is sometimes called the abscissa, and the y-coordinate is sometimes called the ordinate. I will use those terms throughout this lesson and other lessons, but to be honest, I'll probably call them just the x-coordinate and the y-coordinate most of the time. The x-coordinate and the y-coordinate, when they're put together, those two numbers form what's called an ordered pair of numbers. And this is a very important rule now that you have to keep in mind. When you write down that pair of coordinates, the x-coordinate always goes first, the y-coordinate is always written second. So, for example, the ordered pair 5, 2 has x-coordinate, or abscissa, 5, and the y-coordinate, or ordinate, is 2. But how exactly do we know which point in the plane is then identified by this ordered pair? Well, here's how. The x-coordinate, or abscissa, tells us how far to move horizontally to find our point. By the way, you may struggle sometimes to know what horizontal versus vertical means. One way I remember that is that horizontal starts with the word horizon, and the horizon is out way in front of me this way, and so I remember horizontal in that way, and then vertical must be the other one going this way. So the x-coordinate tells me how far to move horizontally, and if the x-coordinate is positive, then I move to the right of the origin. If the x-coordinate is negative, then I move to the left of the origin. This is exactly what we do with the usual number line. If you think about it, we discussed that in an earlier lesson. If you're on just the regular number line and you want to look at, say, +5, then you go 5 units to the right of the origin. If you want to look at -3, then you go 3 units to the left of the origin. So that makes perfect sense. By the way, the x-coordinate might be 0. That's perfectly legal to happen. And if the x-coordinate is 0, then I simply don't move either to the left or to the right. I just stay at the origin at that point. But then I have to look at the other number in my ordered pair. Remember, that's called the y-coordinate, or the ordinate. Now what do I do with that piece of information? Well, if it's positive, then I'm going to move up the vertical axis from the origin. If it's negative, then I'm going to move down. So in some sense, it acts like another number line, just a number line that's been turned on its side. So again, if my y-coordinate is positive, I'm going to go up. If my y-coordinate is negative, I'm going to go down. What if the y-coordinate was 0? That's perfectly possible to happen. If the y-coordinate is 0, then I'm not going to move either up or down. I'm just going to stay in the same position where I was. Okay, so with that piece of information in mind, let's plot a point. I think that would be a good idea, good way to start. Let's plot the point 5, 2. Let's start with the x-coordinate. That x-coordinate is 5. It's +5. That tells me I need to start at the origin and move 5 units to the right. Okay? Once I'm there, I now need to move up or down depending on that y-coordinate. In this case, that y-coordinate is +2. That means I need to move from here up 2 units and draw a nice big circle right there and fill it in. That point is exactly the one represented by 5, 2. Good, we just plotted our first point. Well done. Let me ask you a quick question about it. In what quadrant does that point live? You've only got 4 choices for the answer, either 1, 2, 3, or 4. 5, 2 lives up in quadrant 1. Very good. If you got quadrant 1, great. You're going to want to remember where those quadrants are. They're going to be very helpful as we work on future problems. Well, let's plot a couple more points. I say we start by plotting something like 3, -4. All right? Thankfully, this problem has a little bit of difference in it because I now have a negative coordinate. Which of those 2 coordinates is negative? It's the -4, and that's the y-coordinate. Well, we'll come to that y-coordinate in just a second, but remember how we start when we're plotting a point. We start at the origin again, and we take the x-coordinate and go either left or right, depending on the sign of that coordinate. In this case, that's the number 3, and that number 3 is positive. So I start at the origin, and I move right 3 units. Okay? From there, I need to work with the y-coordinate. In this case, that's -4. It's negative. That means I have to go down the vertical axis, if you will, 4 units. And so I'm going to go 1, 2, 3, 4 units down in the process. Once I've done that, I can draw a nice circle, and that dot represents the coordinates 3, -4. Now we could ask the same question that we asked earlier. Which quadrant does that point live in? It's 1, 2, 3, or 4. Which one is it? It's 4. That's exactly right. Keeping in mind that the quadrants go 1, 2, 3, 4, that point is in quadrant 4. Well done. Well, let's get some more practice on this. Let's plot another point. How about -2, -5? Well, the abscissa now, remember that's the fancy name for x-coordinate, is -2. That's negative. So I'm going to start at the origin, and now I'm going to move to the left 2 units. So I'm going to be here now. Then the y-coordinate, or ordinate, is negative as well. It's -5, and that means I'm going to move downward 5 units in the process. Once I've done those 2 steps, moving 2 to the left and 5 down, I'm actually at my point's location, and I can draw it in with a little dot with my pencil. And now, let's ask the same question again to close. Which quadrant does that point live in? And now the answer to that is quadrant 3. Okay, I'd like to take this a little bit further by plotting a couple other points, and now I'd like to try to plot one that has much bigger coordinates, and then use that to motivate us to think about our Cartesian coordinate system. So let's try plotting -25, 30. Now, I've already done a few examples with you, and none of the coordinates that we had looked at up to that point were very big, right? 3, 4, 5. Now I'm looking at 2 coordinates that are both pretty big, -25 and 30. And this leads me to talk about your actual plot on your graph paper. You and I actually made some assumptions in the previous examples that I didn't really want to mention at that point, but I'll mention them now. You and I made the assumption that every little piece of the grid was exactly 1 unit. At least that's the assumption I made. I didn't really talk to you about labeling those units, but in fact most people would have just labeled them as 1, 2, 3, 4 in the horizontal direction, and then 1, 2, 3, 4 in the vertical direction as well. But if you want to plot -25, 30 on a piece of graph paper, and you assume that each unit is exactly 1 in measurement, your point is probably not going to be on the piece of graph paper unless you have an immense piece of graph paper. Imagine if I asked you to plot the point -2500, 3000. Your graph paper would have to be immense. So we have a way to get around that. Notice that we weren't required to make each unit of the graph paper exactly 1. We could have, for example, made it 5 or 2 or 10. We could make them whatever we want. And it's very important that we keep that in mind as we're trying to draw these points. So in this case, as we're plotting -25, 30, might I suggest that we make each unit exactly 5 in distance instead? In other words, if you've drawn your 2 axes and you've got the origin labeled, the next unit over from the origin in the horizontal direction, label it 5. You're allowed to do that. Then take the next one and label it 10, then 15, 20, 25, and so on. And then in the vertical direction, you can do the same thing, starting back at the origin again, moving up, make the first line 5, then 10, then 15, then 20, and so on. You can do the same thing in the negative direction. In the horizontal, it would be -5, -10, -15, and so on. And in the downward direction below the origin, -5, -10, and so on. And now you can plot this point, -25, 30, with no trouble. Your paper no longer has to be this big in order to plot it. -25 would require you to go, remember, to the left in the horizontal direction. But now, because your units are 5 at a time, you only have to go 5 over. 5 times 5 is 25. So you've moved in the left direction, in the horizontal direction, and now you need to go up 30. But remember, each jump is 5 units. So you only really have to go up 6 squares on your graph paper. 5 times 6 is 30. And once you've done that, you've plotted your point. Notice that's our first point we've plotted in quadrant 2 in this lesson. But you did it by shrinking the scale of your graph paper. That's perfectly acceptable to do. Not a problem at all. But what's the key? The key is, if you need to show your teacher, show whoever's teaching this course to you what you've done, you have to label those axes. Very, very important tool for us to remember throughout this course. Your axes must always be labeled. Most of the time we expect each square to be 1 in its distance. But in this case, we made each square 5. Perfectly legal. In fact, if you think about it, doing such a thing is like zooming in or out with a camera. That's all we've done when we've gone from making each box 1 unit wide to each box 5 units wide. Well, with that said, I'd like to look at another example then, which has the same kind of feeling to it. Let's actually plot the point 4/3, 5/3. Why not use fractions? Perfectly legal to do so. Let's plot 4/3, 5/3. Now, if you make your units 5 wide and you want to plot 4/3, 5/3, you're going to be there a long time. It's going to be hard to figure out where to put the points. However, just as we went from a unit length of 1 to a unit length of 5, we can also go from a unit length of 1 to a unit length of 1/3. That's also fine to do. And so here's what I would suggest. On a new piece of graph paper, draw your axes again, label your origin, and now as you're labeling the points away from the origin, make them 1/3 in length. So in particular, as you're going down the x-axis to the right, the units would be 1/3, 2/3, 3/3, 4/3, and so on. And then going up the y-axis again, each line segment would be 1/3 and then 2/3, 3/3, 4/3, 5/3. Now where does the point go? Well, now the point is going to land on one of the crosshairs in the graph paper, which is great because the x-coordinate here is 4/3. That means you need to go over 4 units to the right, and the y-coordinate is 5/3. That means you go 5 up. 1/3, 2/3, 3/3, 4/3, 5/3. You draw your dot, you're done. So keep in mind this idea of units and how to label your graph. It's very, very important that we do that. Now, one last example in this vein. Let's plot -0.75, -1.25, a decimal number for each of the coordinates. No problem. Now, here's a question though. What should we make our units? Well, you have choice here. You could make each one 1. And that's not a problem. So your graph would just be 1, 2, 3, and so on as you label the x-axis, and the same for the y. I'm going to suggest here, however, that for -0.75 and -1.25, making each square exactly 0.25 in width would be perfectly acceptable as well. As soon as you've labeled the axes that way, finding -0.75 over here and -1.25 downward, down in quadrant 3, will not be difficult at all. Again, I didn't have to choose 0.25 as the length on my grid, but by doing so, it makes it pretty straightforward to plot this point. Okay, I'd like to put a slightly different spin on these examples by looking at another type of problem. Here I'm going to give you the 2 points labeled A and B already in the Cartesian plane, and now the question I want us to answer is, what are the coordinates of the points? See, in the previous examples I gave you the coordinates and we plotted the points. Now we've already plotted the points, I'd like us to determine the coordinates. So we're sort of doing the problems backwards. Well, let's start with A. I want you to notice that A resides 5 units to the left of the origin, and that means its abscissa, or x-coordinate, is -5. Don't fall into the trap of thinking that A's x-coordinate is positive 5. It would be in a totally different quadrant then. So the x-coordinate for A is negative 5 because the point is 5 units to the left of the origin. That point also sits 2 units above the origin, or 2 units above the x-axis, so its y-coordinate is 2. And therefore, the ordered pair of coordinates for A is negative 5, 2. Now, some students might be tempted to write the answer here as 2, negative 5. In other words, switch the roles of the x and y coordinate. But that's a totally different point. In fact, 2, negative 5 lives in a totally different quadrant. So again, you have to be very careful not to switch the order in the ordered pair. Now, that was A. Let's do B. Well, look at B for just a moment. Something odd is going on there, namely B lives exactly on one of the axes. So is that a problem? Like, should we stop here? No. Just think through the process for just a second. First, the x-coordinate of B is going to determine how far to the left or right of the origin B goes. Well, how far to the left or right of the origin does B go? Answer, not at all. It doesn't move away from the origin in the horizontal direction. You don't have to move either to the left or to the right. And therefore, the x-coordinate of B, or the abscissa of B, is 0, which is fine. What about the y-coordinate of B? Well, in order to get to B from the origin, you have to move 4 units down from the origin. By having to move down, it means that the y-coordinate has to be negative. And in this case, it's negative 4 because you've moved 4 units down from the origin. And therefore, I can write down the ordered pair for B. It's exactly 0, negative 4. As I mentioned before, you might be tempted to write down negative 4, 0 here. Again, that would be wrong, but it does raise a question, where does negative 4, 0 live in the Cartesian plane? Well, if you think about it for a moment, it has to live somewhere on the x-axis. Why is that? Because the y-coordinate of negative 4, 0 is 0. And if the y-coordinate of negative 4, 0 is 0, it means you don't move up or down. So that point must live on the x-axis. Not really in a quadrant so much, but right on the x-axis, 4 units to the left of the origin of 0. As we look ahead to our upcoming algebra work, I'd like us to plot several points at the same time in the Cartesian plane and see what kind of graph we see. So let's look at the following example. I want us to plot several points: 0, 2, 1, 4, 3, 8, negative 1, 0, negative 2, negative 2, and negative 4, negative 6. Once we have them all plotted, I want us to connect the dots, and let's see what kind of graph we have at the end. Now, your first thought is, oh my word, 6 points. Can we do that? And the answer is yeah, sure. Just one at a time. Take your time. We'll plot them together. So let's start by drawing the x and the y axes and labeling them. Remember, the x-axis is the horizontal axis. Put a little x at the end on the right. The y-axis is the vertical axis. Put a y on the top of that. I'm going to suggest a labeling of each axis, say from negative 10 to 10, with each unit being just 1 in length. You're going to have to label those axes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the positive x direction, the negatives in the negative x direction, and then the same in the y-axis as well. Notice that graph paper here is very, very helpful. It can be very difficult to take a piece of blank paper and actually make all of these measurements work out evenly, and that's why I suggest that graph paper is very, very helpful. Now, let's plot these points that I asked you to plot. Okay, 0, 2. Well, the 0 tells me that my x direction hasn't changed. In other words, I don't move to the left or the right. And the 2 is the y-coordinate, so it tells me to move up, because it's positive, 2 units. So this point is going to be on the y-axis, and I'm going to draw it in at 0, 2. Done. We can push that point aside now in our minds and go on to 1, 4. Now the 1 tells me that I need to start at the origin and move 1 to the right, that's the x coordinate, and then move up 4 as we go in the y direction. And so I'm going to go 1, 4. That's going to land me in the first quadrant, and it's going to be at the point 1, 4. Draw that in with our pencil. Next, 3, 8. Okay, the 3 again is my x coordinate. It's positive, so I'm going to move from the origin 3 units to the right, and then I'm going to move up 8 units. And notice at that point, as the point 1, 4, both live in quadrant 1. So that's perfectly done. All right, we have 3 of our points done. Let's do a few more. Next, I asked us to plot -1, 0. Now the -1 is the x coordinate, or abscissa. It's negative, so I have to move to the left 1 unit from the origin. And then the 0 is the y coordinate. I don't move any up or down because it's 0. And therefore that point lives right on the x-axis. I draw that in. The next point is -2, -2. Both the x and y coordinates are negative. So I'm going to move 2 to the left and 2 down, and I can draw that in pretty quickly. And lastly, I have -4, -6. Both points, both coordinates again are negative. So how am I going to get to my point? -4 for the x tells me to go 4 to the left on the x-axis. The -6 tells me to go down 6 units and draw in my point. Which quadrant is that in? Quadrant 3. Very good. You should now have 6 points plotted on your piece of graph paper. Fabulous. Now, I want you to connect them as carefully as you can. Use a ruler or something like that if you want, but connect the dots, if you will. And now here's a question for you. What geometric figure do you see? Well, if you've drawn it carefully, and we've got everything correct, what you should see is a straight line segment. In fact, all of these points that I just had you plot should lie on the line whose equation is y equals 2x plus 2. We'll talk more in future lessons about how to derive the formula y equals 2x plus 2. I haven't shown you anything along those lines yet, but we'll also learn how to draw this line given just the formula y equals 2x plus 2 and not the specific points. We'll learn how to translate between the equation and the plot of the graph. In fact, a significant part of this course will focus on lines and linear equations, so the example I just showed you is really just the tip of the iceberg of what we'll see in the future. In this lesson, we've learned a lot of new terminology related to plotting points in the xy plane or Cartesian plane. I would really encourage you to memorize and understand all of these vocabulary terms that we've seen, because we'll definitely continue to put these ideas into practice throughout the rest of this course. Next time, we'll start doing some algebra by talking about linear equations and how to solve them. Our goal in today's lesson is to begin learning how to solve linear equations. Or we could say we want to find the solutions of a given linear equation. What does it mean to be a solution of a linear equation? It's a great question, especially if we're supposed to be finding these things. So let's define what it means to be a solution. A solution of a linear equation is the value of the variable that makes the equation true. So let me show you a couple quick examples of what it means to be a solution of an equation. First of all, let's show that x equals 3 is a solution of the equation x plus 7 equals 10. Well, when we're given a number which is supposedly a solution of an equation, we simply need to plug in that numerical value to see if the resulting equation is true. So, I'm going to take x plus 7 equals 10, which was the equation that was given to me, and I'm going to plug in x equals 3 for x. When I do that, my equation becomes 3 plus 7 equals 10, or 10 equals 10, because 3 plus 7 is 10. Well, 10 equals 10 is a true statement. So x equals 3 is definitely a solution of the equation x plus 7 equals 10. Let's look at a second example of this type really quickly. Let's show that x equals -3 is a solution of the equation 8x minus 14 equals -38. Well, again, to show that -3 is a solution of the equation that we were given, we simply replace the x by -3, we simplify the equation as much as we can, and we see if what results is true. So I started with 8x minus 14 equals -38. I plug in -3 for x. And when I do that, I get 8 times -3 minus 14 equals -38. Now let's simplify that left-hand side just a bit. 8 times -3 is -24. Then I have to subtract the 14. -24 minus 14 is -38. The left-hand side is -38. The right-hand side is -38. Excellent. That's a true equation or a true statement, and therefore x equals -3 is a solution of the original equation. Well, before we go anywhere, let me point out that not every number I choose for x is going to be a solution of that equation. So let's show that x equals 1 is not a solution of the equation 8x minus 14 equals -38. Well, what do I do to check? Well, I plug in the 1 for x, and I get 8 times 1 minus 14 equals -38. Well, 8 times 1 is just 8. So the left-hand side is 8 minus 14. The right-hand side is still -38. That means that the left-hand side is now -6. The right-hand side is -38. Is -6 equal to -38? Of course not. And that means that x equals 1 is not a solution of the equation that we started with. Now, I'd like us to consider how we would actually find the solutions of these linear equations ourselves. After all, it's a lot more difficult to go find the solution than just to be handed it. The first few examples we've done in our lesson now, we were actually told what the solution is. It's perfectly fine to check those solutions, but the real difficulty with the algebra is to go find those solutions. Now, I said difficulty. It's not really that difficult. We just need to walk through the process in order to solve our linear equations. So I want to start by looking at problems that are often called one-step equations. Now, solving one-step equations is the name given to finding solutions where the linear equations really only need one extra step to solve them. So let me show you a couple of examples of one-step equations. Let's start by solving x minus 5 equals 17. So I have my equation, x minus 5 equals 17. In order to solve that equation, we need to find a solution or a number for x which makes the equation true. Now, I could just start plugging numbers in for x to check. Some people would call that guess and check. And that's okay, but our equations are going to get pretty complicated, so we don't want to just try that. To actually solve this equation, I want to get the x by itself on the left-hand side of the equation. So the question is, how can I get that x by itself legally? In other words, what math can I do to get the x by itself? I mean, there are lots of things we could do to get the x by itself. For example, we could just take an eraser on our pencil and erase the minus 5 on the left-hand side, and we'd be left with x equals 17. But that's not legal from a mathematical point of view. You wouldn't get the correct solution. So we need to think about how to get the x by itself, or to isolate the x on that left-hand side so that we can get our solution. Well, the correct thing to do to get x by itself is to add 5 to both sides of the equation. By adding 5, I'm going to be able to get rid of the minus 5 that's on the left-hand side of the equation. So let's do it together. I started with x minus 5 equals 17, and now I want to add 5 to both sides. I want you to notice that this is sort of like taking a seesaw that's already level and adding 5 pounds on one side or 5 pounds on the other side. If the seesaw was level to start and you add 5 pounds on both sides, it'll stay level. And that's exactly what you want these equations to do as you start to solve them. You want both sides to stay equal throughout the process. So we're going to add 5 to both sides of our equation. And when I do that on the left, x minus 5 plus 5 is just going to become x. Okay, it becomes x plus 0 because minus 5 plus 5 is 0. That's just x though. And then I have 17 plus 5 on the right-hand side, and 17 plus 5 becomes 22. So what's the equation now say? It says x equals 22. The equation actually tells us the solution. The solution is 22. Now we should check that we've got the right solution, especially since we're sort of new at this. So how would we check that 22 is the solution? Well, we'll go back to the original equation and we'll plug 22 in for x, and we'll see if what comes out is a true equation. So the original equation was x minus 5 equals 17. We plug in 22 for x. 22 minus 5 equals 17, and 22 minus 5 is 17. So the equation says 17 equals 17. Is that a true statement? Yes. Fabulous. So indeed, x equals 22 was a correct solution for that equation. I want you to notice that this was called a one-step equation because we really only needed one step to solve it. And that one step was the addition of plus 5 to both sides of the equation. Now, let's look at a second example of this one-step equation type. I want us to solve t plus 4 equals 19. Now again, you could just plug in numbers for t, but let's do it by solving the equation rather than just plugging numbers in randomly. So I'm looking for a number that I'm going to plug in for t to make the equation true. I want to get the t by itself, or isolate the t. And I need to do that, again, in a mathematical way that's allowable, that actually makes sense. Well, we might start by subtracting 19 from both sides of the equation. That's actually a perfectly legal thing to do from a mathematical perspective. So you start with t plus 4 equals 19, and you subtract 19 from both sides of the equation. Great. What do you get? Well, on the left-hand side, you have t plus 4 minus 19. Well, what is that going to be? That's going to be t minus 15. 4 minus 19 is negative 15. So t plus 4 minus 19 is t minus 15. That's my left-hand side. Now, what do I get on the right-hand side? Well, I get 19 minus 19, which is 0. So my new equation is t minus 15 equals 0. Now, that's a perfectly correct equation to state at this point. The problem is it didn't isolate the t at all. That was my goal, was to get t by itself, and we didn't accomplish that. So we could work with the equation that we just had, but I'd rather we went back to the original equation and did something else. Again, what we did was okay, it just didn't get us to the goal of isolating the t, or getting t by itself. Well, what would you do then? T plus 4 equals 19 is our equation. How would you get rid of that plus 4 that's on the left-hand side with the t? Well, what's the opposite of addition or adding 4? It would be to subtract 4. So I'm going to suggest that we take t plus 4 equals 19 and subtract 4 from both sides of the equation. And once you do that, some really great things are going to happen. First of all, what happens on the left-hand side? Well, notice that the plus 4 minus 4, they cancel each other out. And the left-hand side becomes t plus 0, which is really just t. In fact, we'll just quit saying t plus 0 or x plus 0. We'll just start writing it as t or x. So my left-hand side here is t. What's the right-hand side? Well, it's 19 minus 4. That simplifies to 15. And therefore, after we've completed this subtraction, our solution is t equals 15. Well, you could go back again to the original equation, t plus 4 equals 19, and plug in t equals 15 to see if the result is true. Remember, that's what it means to be a solution, is that you can plug in the number and make the original equation true. If you do that in this case, you'll have 15 plus 4 equals 19, which is the same as 19 equals 19. And that's definitely true. If you've got $19 and I've got $19, we've got the same amount of money. So indeed, t equals 15 is a solution of that equation. I'd like to show you more examples of solving one-step equations now, which are going to look a bit different from the ones we've just done. So let's move to the next example. I want us to solve 8y equals 104. 8y equals 104. Now that's a linear equation. It's a perfectly good linear equation. This time there is mathematics around, or numbers around the y, but in this case I've multiplied by an 8 rather than adding or subtracting. I still want to get the variable by itself. In this case I want to get the y by itself. And by getting the y by itself, I'll have my solution. So what do I have to do? I've got to get rid of the 8. How do I get rid of that 8? Again, I could just erase it with my pencil, but that's not legal to do. How would I get rid of the 8? Well, the answer is definitely not addition or not subtraction as before, because the 8 here is not added or subtracted from the y. So what could I do to get rid of the 8? Well, here's the answer. The 8 is being multiplied with the y. What's the opposite of multiplication? The answer is division. So let's take our equation, 8y equals 104, and divide both sides by 8. Remember, if you're going to divide the left-hand side by 8, you have to divide the right-hand side by 8 as well to keep the equation balanced on both sides. Now, what happens when you do that? When you divide by 8 on the left-hand side, the 8's simply cancel, and you have y, or 1y, if you want to write it that way. I would just write it as y. So the left-hand side now just has y on it. Great. Now, I've isolated my y, but I need to go look at the right-hand side now. What does the right-hand side look like? Well, it's the fraction 104 divided by 8. Now, it'd really be good to simplify that as much as we could, so let's do that together very quickly. 104 and 8 are both even, so they both have a 2 in them. If I factor a 2 out of the numerator, I'll be left with 52 times 2. If I factor a 2 out of the denominator, I'll have 4 times 2. I can then cancel those 2's, and I have 52 over 4. The same kind of process will allow me to reduce 52 over 4 to 26 over 2. And 26 and 2 are both even, so I can reduce again, and I'll be left with 13 over 1, or just 13. What does the equation then become? It becomes y equals 13. And that means that y equals 13 is our solution. You could check that if you wanted by taking the 13 and plugging it back into the original equation and then seeing if what comes out is a true equation. Well, let's do one last one-step solution example by doing the following. Let's solve 5/3 times x equals 55. Well, as with the example that we just did, we want to isolate the variable here. In this case, that's x. So what's in the way? What's next to the x? It's the fraction 5/3. Now, how am I going to get rid of that 5/3? Again, I'm not going to add or subtract because the 5/3 is being multiplied with the x. I need to undo that multiplication by dividing by 5/3. Now, I don't know about you, but dividing by a fraction, that feels a little uncomfortable. It's perfectly legal to do, it's perfectly okay to do, but I like to think of it instead as multiplying by the reciprocal. In this case, the reciprocal of 5/3 is 3/5. So, instead of dividing by 5/3, let's multiply both sides of the equation by 3/5. Now, what is that going to give us? Well, before we start doing any simplification, we're going to have 3/5 times 5/3 times x equals 3/5 times 55. Remember, if you're going to multiply the left-hand side by 3/5, you must multiply the right-hand side by 3/5 as well. Now, what happens if you simplify? Well, the 3/5 times the 5/3, they're just going to cancel each other. And the left-hand side then will just be 1x, which I'll just write as x. Well, we've isolated the x. That's fabulous. So now I just need to simplify the right-hand side. Well, what is the right-hand side? It's 3/5 times 55. Okay, can we simplify that at all? Sure we can. What is going to happen between the 5 that's in the denominator of the 3/5 and the 55? They're going to cancel a little bit. In fact, if you write the 55 as 55 over 1, you'll see that the 5 and the 55 can cancel a bit, and you'll be left with 3 over 1 times 11 over 1, which is 33 over 1, or 33. What does that mean? It means that we have x on the left equals 33. That's our solution. Well, let's check it a bit. We had to do some real mathematics there to get to that x equals 33, so let's check. We take our original equation, 5/3 x equals 55. We substitute 33 in for x, and we get 5/3 times 33 equals 55. We can reduce the left-hand side a bit by canceling the 3 with the 33, and we'll have 5 over 1 times 11 is 55, and 5 over 1 times 11 is 5 over 1 times 11 over 1, which is 55 over 1, or 55. We have the equation 55 equals 55, and that's definitely a true statement. So here's a tip that you should keep in mind as you're solving one-step equations. You need to look for the opposite function. If you've got multiplication in the problem, do the opposite, which is division. If it looks like a number is being added to the variable, do the opposite, do some subtraction. That rule will help us as we move on to what are known as two-step equations. So I'd like to transition now to what are known as two-step equations and solve such equations. For example, what if we had an equation like 3x minus 4 equals 6? Now I want you to notice something. If you wanted to get the x by itself, if you wanted to isolate the x, you'd have to get rid of the 3 and the 4 in order to do so. That means that two steps are required, hence the name two-step equations. So let's talk about how we would solve 3x minus 4 equals 6. First, we need to get rid of that 4. And you might say, why the 4 and not the 3? Well, believe it or not, the answer is wrapped up in the order of operations. To isolate the x, we first have to undo the multiplication by 3 and the subtraction of the 4 in reverse order. And so I'm going to start by getting rid of the 4 first. Now to do that, what would I do to get rid of a minus 4 like that? I would add 4 to both sides. And if I do that, the left-hand side becomes just 3x because the minus 4 and the plus 4 cancel each other out. What does the right-hand side become? It becomes 6 plus 4, which is 10. And so the new equation, which is still balanced compared to the original equation, is 3x equals 10. Notice we're now down to a one-step problem. We whittled it down from 2 to 1 step. Well, how do we get rid of that 3? Well, we know how to do that. We divide both sides by 3 or multiply both sides by 1/3, however you want to view it. And if you do that, the left-hand side becomes 3x over 3. Cancellation gives you x. And the right-hand side becomes 10 over 3, or 10/3. There's no reducing you can do to that fraction, so your solution is just 10/3. Now, we should check to make sure that that solution makes sense, so let's do so. We go back to the original equation, 3x minus 4 equals 6, and we replace the x by 10/3. And that gives us 3 times 10/3 minus 4 equals 6. 3 times 10/3 is what we do next, thanks to our order of operations, and that, of course, is just 10. So I have 10 minus 4, which is 6, and of course 10 minus 4 is 6. So I get 6 equals 6, which is definitely a true statement. Well, let's look at another two-step equation. I think it's good to do some practice with these sorts of things. So let's solve another two-step equation which is a little more complicated. At least it looks like it's more complicated as we start it. Let's solve t over 8 plus 1 equals 5. Now, two steps are definitely needed again because you've got to get rid of the plus 1 and the 8. So how do we do that? Well, let's start by getting rid of the plus 1. Now, how would we get rid of a plus 1? Well, I need to do the opposite of addition, and that's going to be subtraction. So I'm going to subtract 1 from the left-hand side of the equation. If I do that, I've got to subtract 1 from the other side of the equation as well. When I do that, I'm going to have the plus 1 minus 1 cancel each other out, and the left-hand side becomes t over 8. The right-hand side is just 5 minus 1, or 4. So I've got the equation now, t over 8 equals 4. And now we're down again to a one-step equation. But I've got to get rid of that 8. Actually, by the way, it's really a 1/8 because t over 8 is the same as 1/8 times t. But that's okay. Let's not fret over that too much. Let's just multiply both sides by 8 and let's see what happens. So we have t over 8 equals 4, and we multiply both sides by 8. Now what does that do to the left-hand side? Well, notice that those 8s are actually going to cancel each other. That's exactly why I multiplied by 8. And when they cancel, I get t over 1, which of course is just t. Now what does the right-hand side do? Well, it's 8 times 4, which is just 32. So my final equation is t equals 32, which means the equation tells me the solution. T equals 32. So 32 is the solution. Now we've checked several solutions throughout this lesson, so I'm going to leave it to you today to check to make sure that 32 really is the solution. It's very, very important to check those things because you want to make sure you didn't make a mistake in your arithmetic or in your operations. So I'll leave it to you today to check that, but indeed, that really is the solution. Well, I want to move to a word problem now. We haven't really done any word problems in this lesson up to this point, so I want to move to a word problem that involves solving a two-step equation. So let's set up the problem, let's first state it, and then we'll try to write it into some algebraic statements. So here we go. Imagine that Mary has a mail order business where she sells books of some sort, and let's say that each book costs $3 plus your shipping cost, which is $5 on any order. So the books are $3 each, and then there's just a flat shipping rate of $5 on any order. We want to write an equation that describes the amount spent as a function of the number of books purchased. That'll be our first step. And then once we've done that, I want us to determine how many books we can purchase if we have $50. Okay, let's start by building the equation. We certainly weren't given an equation, we just had a whole bunch of words and numbers floating around. So what's the first thing we do when we're handed a word problem like this and we need to actually set it up algebraically? We must start by naming some variables. Well, notice that no variables were given to us, so we need to come up with them on our own. So I suggest the following. Let's let B equal the number of books that we purchase, and let's let A be the total amount of money that we spend. Okay, once that's done, we now need to interpret the English sentences that we were given into algebraic expressions, into an equation. Well, each book costs $3. So the total cost for B books is going to be 3 times B before we add the shipping. Let's step back a bit. Let's say you bought 2 books, then the total cost for just that would be 3 times 2 or $6 before shipping. If you bought 10 books, the total cost for that would be 3 times 10 or $30 before shipping. So if you bought B books, the total number is 3 times B for your cost for the books before shipping. Well, we need to add the shipping in. So how much is that going to change my algebraic expression? Well, the shipping cost is $5 added on to the cost of the books for any order. It doesn't depend on how many books you buy. 1 book or 1,000 books, your shipping cost is just $5. So, in order to get our total cost, or the total amount that we'll spend, we need to take the 3B, which was the cost for the books themselves, and add 5. And that addition of 5 is going to be for the shipping. That is the total cost for us. And therefore, A, which is the amount of money we're going to spend totally, equals 3B plus 5. There's your equation. A equals 3B plus 5. And it's excellent that we pulled that off. That's not an easy thing to convert from the English phrases to an algebraic equation. But that's great that we got that far. Now we need to worry about the second part of the problem. We were told that we wanted to find out the number of books that we could purchase if we had $50 for them. Now, here's a question. Does that $50 represent A, the amount of money that we're going to spend, or B, the number of books? You should always ask this kind of question. And you know, we weren't told in the problem that 50 was either A or B. In fact, the problem didn't even say anything about A or B when we started. So we have to decide, does that $50 represent A or B? Well, $50 is going to be the total amount of money that we spend. And since we named our variables at the beginning and we declared what they stood for, it's pretty easy to look back and say, that 50 is the value for A. So if we go back to our equation, which said that A equaled 3B plus 5, we can replace the A with 50, or plug 50 in for A. And once we've done that, our equation becomes 50 equals 3B plus 5. Now, you know, equalities, you can switch both sides if you want. So instead of writing 50 equals 3B plus 5, I can also write 3B plus 5 equals 50. It's just like looking at a seesaw from one side and then from the other. It's going to look the same, except for switching around. So I'm going to rewrite it as 3B plus 5 equals 50, basically just to get the variable on the left-hand side. And now I want to solve for B. Why? Because the problem was asking, how many books can I buy with $50? And B is the number of books that I can buy. So I want to solve 3B plus 5 equals 50 for B. Well, that's a two-step equation. We've done several of those already in this lesson. So let's get B by itself. How would I do so? Well, the first thing I'm going to do is get rid of that 5, that plus 5 on the left-hand side. And how do I get rid of a plus 5? I subtract 5. But I have to make sure I do it on both sides in order to balance everything out. When I do that, the left-hand side becomes 3B. The right-hand side is 50 minus 5, which is just 45. And my equation is now 3B equals 45. Now what do I do? Well, I've got to get rid of that 3. How do I do so? I divide both sides of the equation by 3. And when I do that, the left-hand side will have the 3's just cancel, and I just get B, which is what I wanted. And the right-hand side is 45 divided by 3. Now, does that simplify? In fact, it does. If you check, 3 does divide into 45 evenly, and you're left with 15 when you simplify 45 over 3. And the new equation is B equals 15. Now, we could just stop there and on our papers circle B equals 15 and happily get up and leave. But we really ought to stop and ask ourselves, what in the world does B equals 15 mean? Well, in the context of this problem, B was the number of books that we could buy. And therefore, B equals 15 means we can buy 15 books if the amount of money we have to spend is $50. Well, today we've learned how to solve a number of types of linear equations, but we're not done with this theme. Solving equations like these is extremely important in algebra, and so we'll spend more time on linear equations in our next lesson. In our previous work together, we learned how to solve a number of types of linear equations. We called them one- and two-step equations. My goal in today's lesson is to continue that discussion by solving more complicated examples of linear equations. So let's get our feet wet with an example that isn't much more complicated than the ones we saw in the previous lesson. Let's solve 5r plus 9 plus 2r equals 86. Now, I want to point out that this is a linear equation because all of the variables, in this case the r's, are raised to the first power, r to the 1 basically. So let's get to our solution. The first thing we need to do is notice that the variable r is actually present on the left-hand side in two different places, the 5r and the 2r. So what do? Well, Don't worry about it. Just add those two terms together. 5 oranges plus 2 oranges is 7 oranges, so 5r plus 2r is 7r. At that point, our equation simplifies to 7r plus 9 equals 86. But that's just a two-step equation. We can solve that. We were doing that in the previous lesson. First, let's subtract the 9 from both sides. 7r plus 9 equals 86. 9 subtracted from both sides is going to leave me 7r on the left, because the 9 minus 9 will cancel. And on the right, I'll have 86 minus 9, which is 77. So the new equation at this point is 7r equals 77. I'm trying to isolate that r, so what do I do next? I divide by the 7. And when I do that, on the left-hand side, the two 7s will cancel, leaving me with just r. On the right-hand side, I'll have 77 divided by 7, which is 11. Our solution then to the original equation is r equals 11. Now, as we've been doing in our previous lessons, we should check to make sure that what we've done is correct. So, in this case, I go back to my original equation, 5r plus 9 plus 2r equals 86, and I replace all of the r's, in this case both of the r's, with 11. And when I do that, I'm going to have 5 times 11 plus 9 plus 2 times 11 equals 86. 5 times 11 is 55 plus 9 plus 2 times 11, which is 22, equals 86. And now I just need to simplify that left-hand side. 55 plus 9 plus 22. Well, 55 plus 9, that's 64. 64 plus 22, that's 86. So I have 86 equals 86, which is a true statement. I want to point out that it would have been very difficult to guess that the answer was 11, based on the original equation. That was not easy, but you and I now know how to solve these equations, which is fabulous. So let's try another example, which is similar to the one that we just did, but it appears, at least at first, to be a bit more complicated. Let's solve the following. 3/4 x plus 2/5 x equals 15. Okay, I see those fractions, and you might be a little concerned about them at first, but it's really not a problem. So what are we going to do to handle those fractions? Well, one way to handle them is to get a common denominator and then add the fractions. We can do this, remember, because we're just adding like expressions. One fraction times x plus another fraction times x. But I'd like to share another idea which is mathematically the same, but it actually gets rid of the fractions in one step. And that idea is this. Let's multiply both sides of the equation by 20. So I'm going to have 20 times 3/4 x plus 2/5 x on the left, and I'm going to have 20 times 15 on the right. Now, someone has to be asking, why in the world did you pick 20? Why didn't you pick 15 or 100 or 5,000? Well, what's the least common multiple of 4 and 5? 4 and 5 are my two denominators of the fractions. Well, the least common multiple of 4 and 5 would be the least common denominator of the two fractions if we went down that path. But the least common multiple of 4 and 5 in this case is 20. Let me say it a bit differently. 20 is the smallest number which has 4 as a factor and also has 5 as a factor. And because of that, I've chosen to multiply both sides by 20. Now, let's go from there. I've got the 20 times 3/4 x plus 2/5 x equals 20 times 15. I want to now distribute that 20 into the parentheses on the left-hand side. And when I do that, I will have 20 times 3/4 x plus 20 times 2/5 x. On the right-hand side, I'll have 20 times 15. But notice what happens with the 20 times 3/4. Something really nifty happens. The 4 cancels with part of the 20 and leaves us with a 5, so that the term 20 times 3/4 x simply becomes 5 times 3x. The fraction is gone, which is great. Look at the second term on the left, 20 times 2/5 x. Well, the 5 that's in the denominator of 2/5 again cancels with part of the 20. And it leaves us with 4 times 2x. Look at the left-hand side now. You should have 5 times 3x plus 4 times 2x. No fractions. They're completely gone. Now look at the right-hand side. It's kind of gotten a bit bigger. 20 times 15 is 300. That's okay. That number is still manageable. But the point now is we've gotten rid of the fractions. And for some of us, that's actually a very comforting thing to do. Now, let's move forward from there. 5 times 3x is 15x. 4 times 2x is 8x. So the left-hand side becomes 15x plus 8x. And that all equals 300. 15x plus 8x, those two can be added because they're like terms. It's just a number times x plus another number times x. 15x plus 8x is 23x. And so my equation now is 23x equals 300. How do I finish isolating that x? I divide both sides by 23. The left-hand side has the 23's cancel. I just have x then. And on the right-hand side, I have 300 divided by 23. So my solution is x equals 300 divided by 23. Now, before we go anywhere, you might ask the question, does 300 over 23 simplify in any way? Can we make it reduced any lower than 300 divided by 23? Well, the answer is no, and the reason for that is 23 is actually a number that doesn't have any divisors other than 1 and 23. Well, if 23 then doesn't divide evenly into 300, that fraction will not reduce. And you can check, maybe with long division, that 23 does not divide into 300, and therefore our solution is 300 over 23. It can't be simplified anymore. Now, let's look at a different type of multi-step equation, and let's try to solve it for its variable. Here's the equation. -3 times the quantity a plus 5 equals 12. Okay, I need to get that a variable isolated. I need to get a by itself on the left. How do I do it? Well, one way to approach this problem would be to distribute that -3 into the parentheses. And if we did that, we would have -3 times a plus -3 times 5 equals 12. And if we simplified that left-hand side, we'd have -3a minus 15 equals 12. Why does it become minus 15? Well, because -3 times 5 is -15. Remember those rules with multiplying two signed numbers where the signs are different? And if you have plus a -15, it's the same as minus 15. Now at that point you have -3a minus 15 equals 12. That's a two-step equation. We've done those before. We did them in the previous lesson. So at this point, we could finish that problem, if we wished, just using what we did to solve two-step equations. But I think there's a different approach to this problem, which is just as good, and I'd like to show you that approach as we finish this example. So the first thing to do when we have -3 times the quantity a plus 5 equals 12 is to divide both sides by the -3. Why do I do that? Because it will cancel out the -3 that's on the left-hand side, and I will simplify the left-hand side quite nicely. So I'm going to divide both sides of my equation by -3. When I divide the left-hand side by -3, I'll have -3 times the quantity a plus 5 divided by -3 equals 12 divided by -3. The -3's on the left will cancel, leaving me with a plus 5. The right-hand side becomes 12 divided by -3. Again, using my rules for dividing signed numbers, that's going to become -4. So I'm now down to a plus 5 equals -4. Now, I just need to find a at this point. That means I need to get rid of the plus 5 that's on the left. And in order to do that, how do I get rid of a plus 5? I subtract, and I subtract a 5. If I do that on both sides of the equation, the left-hand side will simply be a, and the right-hand side is -4 minus 5. -4 minus 5 is -9. Think again about that number line. start at -4, and then go to the left 5 more units because of the -5. And if you do that, you'll land at -9. So my solution in this case is A equals -9. I think we should keep up the good practice of checking our solutions, and so let's do that here. Checking your work is the best way to make sure your work is accurate, and I recommend it as a step to make sure that your grades are as best they can be. So let's go back to the original equation and let's plug in A equals -9. If we do that, we have -3 times A plus 5 equals 12. That means plugging in A equals -9 will give us -3 times -9 plus 5 equals 12. I'll have -3 times -4 equals 12, and therefore 12 equals 12. That's a true statement, and so we did have the right solution to start with. Excellent. Now, let's transition to a new level of complexity in these problems and look at a really complicated looking equation, at least at first. Let's solve the following equation. 5x plus 3 equals -4x plus 39. Okay, now that's much different than anything we've seen up to this point. Can you tell why it looks a lot different than before? Well, it's because we have x's now on both sides of the equation. In all of the equations we've solved up to this point, we've kept all the x's on one side of the equation. So here's now a rule to live by when it comes to solving linear equations. As soon as possible, we need to get all the variables on one side of the equation and all of the constants, or the numbers that are by themselves, on the other side of the equation. It doesn't matter which side of the equation you put each piece. You can put all the variables on the right and all the constants on the left if you'd like, but it's important to get all of those variables on one side together and all of the constants, or numbers without variables, on the other side. So in this case, I'm going to put all the constants over on the right-hand side, and I'm going to put all of the variables on the left-hand side. So we started with 5x plus 3 equals -4x plus 39. I'm going to subtract 3 from both sides, and that's going to get rid of the plus 3 on the left. And when I subtract 3 from both sides, I'm going to have 5x on the left equals -4x plus 39 minus 3. And 39 minus 3 is 36. So I have 5x equals -4x plus 36. Now, I want to get all of the x's over to the left-hand side. The 5x is already there, so I just need to move that -4x over to the left-hand side. How am I going to get -4x from the right over to the left? I simply add 4x to both sides. By the way, it's okay to add variables to both sides of our equation. Up to this point, we've just added numbers, but now we're adding 4x. It's okay to add a term like that. Once we do that, the left-hand side will become 5x plus 4x, which is 9x, and the right-hand side will have the -4x and the 4x cancel, and you'll just be left with 36. Well, now we're down to 9x equals 36. That's a pretty straightforward equation to solve. How? You've just got to get rid of that 9. And in order to do that, you divide both sides by 9. 9x divided by 9 is just x, and 36 divided by 9 is 4. And therefore, our solution is x equals 4. Let's check. We should always check. So let's plug in x equals 4 for our variable everywhere in the equation. Remember, there's one on the left and one on the right in the original equation. Doing that, I'll have 5 times 4 plus 3 equals -4 times 4 plus 39. The left-hand side then becomes 20 plus 3, and the right-hand side becomes -16 plus 39. Well, the left-hand side simplifies to 23 pretty quickly, and the right-hand side is also 23. That's a true statement, and therefore we had the right solution to start. Now, Let's look at a real-world example of how such an equation can actually come up in a word problem. So I want you to consider the following puzzle. When 3 times my age is increased by 6, it's the same value as when 5 times my age is decreased by 80. So here's the question. How old am I? By the way, I'm sure some of you are saying, well, that's not really that real world. Okay, I understand, although my age really is a real world question. But these kinds of problems or puzzles actually do require some very important algebra techniques to solve. So it's good practice. And these kinds of questions do come up also on exams and tests that you might have to take. So let's go for it, even if it doesn't sound very real world in the process. We need to start by defining our variable or variables. You always need to do that when you're working on a real world or word problem type of issue. Well, in this case, there's really only one unknown quantity, and that's my age. So let's let A equal my age. Now, we need to write an equation which translates all of that English into mathematical symbols. Well, the first part of the sentence translates to 3a plus 6, or 6 years more than 3 times my age. Then we had the word is or equals in the middle of that sentence. We need to replace that with an equals sign. And then we talked about multiplying my age by 5 and then reducing it by 80. And that means the right-hand side is 5a minus 80. So the equation that we're going to work with is 3a plus 6 equals 5a minus 80. Notice that we now have an equation with the variables on both sides. That's very similar to the equation that we just solved in the previous example. So let's now solve that for the variable a. And just remember, the variable a is my age, and that was what the problem asked us to figure out, my age. Now, we've got two choices from here. We could move all of the a's to the left-hand side and all of the constants to the right-hand side, or you could move all of the a's to the right-hand side and all of the constants to the left-hand side. Either of those is fine. In this case, I'm just going to move all the a's to the right-hand side. Why? Personal preference. I get to pick. You get to pick as well. So I'm going to move them to the right. Actually, there's more reason to move them to the right than to the left. If I move them all to the right, it will keep the coefficient in front of the a positive. I kind of like that. You don't have to do that, but it will do it in this case. And by moving all those a's to the right, I'll have a positive coefficient. Again, you could move them to the left if you're more comfortable with that. In fact, if you'd prefer that, when I'm done with this example, you might move the a's to the left and do all of the equation manipulations to see if you get to the same solution. Might not be bad practice. Now, I want to move all the a's to the right-hand side, and let's move all the constants to the left. And if I do that, I need to subtract 3a from both sides. By subtracting 3a from both sides, 3a minus 3a on the left will go away, and I'll just have 6 on the left-hand side. On the right-hand side, I'll have 5a minus 3a, which is 2a, and then minus 80. Don't lose the minus 80. It's just there by itself for now. So I have the equation 6 equals 2a minus 80. Now, I need to move the constants to the left-hand side then. And how am I going to do that? I need to get rid of that minus 80 so that it's away from the a. In order to do that, I'm going to add 80 to both sides. And when I do, the minus 80 on the right with the plus 80 will cancel. And I'll just have 2a on the right-hand side. On the left-hand side, I'll have 6 plus 80, which is 86. And so my equation becomes 86 equals 2a. Well, I want to get a by itself. How do I do that? I divide now on both sides by 2. And the 2 that's in front of the a will cancel with the 2 in the denominator, leaving me just a. On the left-hand side, I'll have 86 over 2. That simplifies to 43. And so a equals 43. Now what was A again? A was my age in years, and so the problem says that I'm 43 years old. Now, we could check the solution by plugging it back into the original equation, but for the sake of time, I'm not going to do that here. You might try that in your own time and make sure that we work the problem correctly. But even if we're not going to check it exactly, let me ask you this question. Does 43 years make sense? Does that seem like a decent answer? I mean, if you look at me and you say, yeah, he looks like he's in his mid-40s, that looks about right. Okay, fine. But what if our answer had been negative 43 for my age? Would that make any sense at all? No, of course not. What if our answer had been negative 5 for years? Of course that makes no sense. What if the answer had been 2 years? A equals 2. Again, I'm not 2 years old, that's pretty clear. And what if the answer had been 430 instead of 43? Maybe we would have made a little arithmetic mistake. Do I look like I'm 430 years old? I say not. So I'd hope that if any of these numbers had come out as your answer, that you would have stopped and said, those don't make sense. And in the process, use that as a prompt to go back and make sure that all of the work you did was correct. I encourage you to keep this kind of critical thinking in mind as we continue throughout this course together. I'd like to turn a corner now and talk about two other types of equations and their solutions. So, quick question. Have you noticed that all the linear equations that we've discussed up to this point have had exactly one solution? Do you think this will happen for every linear equation we write down? Well, let's see. Let's solve the following equation. 4 times 5x minus 6 equals 5 times the quantity 4x plus 2. Well, let's start by distributing the 4 that's on the left-hand side and distributing the 5 that's on the right-hand side. And when I do so, I'm going to have 4 times 5x minus 4 times 6 equals 5 times 4x plus 5 times 2. Okay, what is that when you simplify? Well, 4 times 5 is 20, so I'll have 20x minus 24, which is 4 times 6, equals 20x, that's the 5 times 4x, plus 10, which is 5 times 2. So I have 20x minus 24 equals 20x plus 10. Now, let's get all the x's on the left-hand side of the equation. To do that, I'm going to subtract the 20x from the right-hand side. And when I do so, indeed the 20x on the right-hand side is going to cancel, but notice what happens to the 20x on the left. I have 20x minus 20x. They're gone. That's 0x as well, which is just 0. And what does that leave me? It leaves me the equation negative 24 equals plus 10. Now, we've done nothing wrong at this point. All of our algebra is correct. So if we stop for a moment, we need to ask ourselves this question. Is negative 24 equal to 10 ever? No, it's never equal. Negative 24 is never equal to 10. So we haven't made a mistake. What in the world is going on? Well, we could actually check our work by putting the x's on the right-hand side, and we get the same answer. So what does it mean? Well, it means that the equation we started with actually doesn't have a solution. We haven't done anything wrong. It's just that the equation I started you with has no number that we can plug in for x in that original equation to come out with an equation that's true. In other words, there's no solution. This sort of thing can happen, so don't get too nervous if you don't see a solution. Sometimes a solution just isn't there. Now, should you pause and maybe check your work to make sure you haven't made some sort of small mistake in your arithmetic? Sure, it probably wouldn't hurt to pause and make sure that we didn't lose a 0 somewhere or add when we should have subtracted. But the point is, we should make sure that our work is correct. Once we do, if there's no solution, there's no solution. No problem. Okay, so we've now seen examples where you can have one solution. We saw lots of examples like that over this lesson as well as the previous lesson. And we've seen an example now where there are no solutions, which is fine. Now I'd like to show you another interesting situation that can occur if you pick the right equation. So let me start us by looking at this equation. Consider 4 times 5x plus 10 equals 5 times 4x plus 8. Perfectly good-looking equation. Nothing overly spectacular about it, but let's start with that and distribute the 4 that's on the left and the 5 that's on the right. Now, if I do those distributions, I'm going to have the following. 4 times 5x plus 4 times 10 equals 5 times 4x plus 5 times 8. Okay? Nothing odd there. We're fine so far. Now, 4 times 5x, 20x. 4 times 10, 40. 5 times 4x, 20x. 5 times 8, 40. So my equation is 20x plus 40 equals 20x plus 40. Now, before we go anywhere else, I want you to notice that currently the left-hand side of my equation and the right-hand side of the equation are equal no matter what we plug in for x, because the two sides are the same. That is, basically, the opposite of what we saw in the previous example. And it leads us to another vocabulary term for our course. And here's what that vocabulary term is. It's the word identity. And here's a definition for an identity. An equation that is true for every possible value of the variable is called an identity. And that leads us to think about the previous example we were just looking at. I had the same thing on both sides of the equation, which means no matter what I plugged in for x, the left-hand side was going to equal the right-hand side. And that means that the equation we started with was an identity. Well, that leads us to a big picture comment that we should make about linear equations. So let me make that comment now. Every linear equation that you will ever see is going to fall into one of 3 categories. First, the equation might have exactly one solution. Second, the equation might have no solutions at all. Or third, the equation might be an identity, which means every number is a solution. Well, we spent our time today in today's lesson looking at a lot of different types of linear equations and how to solve them. I've tried to show you lots of different examples, hoping that you'd be encouraged with all that practice to have confidence in solving equations in the guidebook. I think you've seen so many different types of examples that you can probably do your work with confidence now as you practice with the guidebook questions. Next time, we'll begin talking about graphs for linear equations by talking about the concept of slope. I'll see you then. One of the most important concepts in the study of linear equations is the slope of a line, because the slope shows up in so many ways in math and science. My goal in this lesson is to introduce you to the concept of slope and discuss a number of ideas related to slope. So let's start our conversation about slope with a discussion of how the word is used in everyday language. So you should ask yourself, when have you ever heard the word slope used in the usual English language? Well, you may have heard people refer to a ski slope, for example. Well, what does that normally refer to? Is it the lodge where everyone goes? Is it the ski that they put on their foot? Of course not. It usually refers to the natural incline of the side of the hill or mountain on which people are skiing. And that certainly gives us a visual idea of what is going on in algebra as well. The side of the hill or mountain can be thought of as a straight line, although that's a bit of a stretch, of course, with the natural terrain of the hill. But if you think about it as a straight line, you start to get the feeling for the concept of slope. Well, how else have you ever heard slope used in everyday language? Well, you may have seen road signs on highways, near hillsides or mountainsides, warning drivers that the upcoming road is very steep or slanted. Some people will refer to the slope or grade of that road to describe the steepness of that portion of road. And it's that steepness that we want to think about today when we think about the mathematical use of the word slope. And so let me give you a working definition for slope, and then we'll go from there. I'm going to use the following definition as we start our conversation in thinking about lines and drawing lines in the following way. The slope of a given straight line is its rate of change, which is defined as follows. The slope is the vertical change of the line divided by the horizontal change of the line. Some people like to say that that's the rise over the run, where the rise refers to the amount of vertical change and the run refers to the amount of horizontal change. So it's very important to remember, slope is all about the change in the y direction over the change in the x direction. Remember that slope is going to be a ratio or a fraction, change in y over change in x. Now this quantity, which we're calling slope, measures then how steep or how flat a straight line is, because it's measuring how fast the vertical amount is changing as the horizontal amount changes. So a steep hillside will have a large slope because the vertical or y values are changing very quickly as the horizontal changes just a little bit, while a road that's relatively flat will have a small slope because the vertical distance is small while the horizontal change is quite large. Well, I've talked enough at this point in vague terms. I'd like us to look at some mathematical examples to try to solidify this concept. Let's start by finding the slope of the following line. Notice that I've labeled two specific points which lie on the line. If you look at the image, you'll see that they are at the coordinates 0, 1 and 1, 3. We talked about the Cartesian plane a few lessons ago, and that's exactly where these points lie, and now we've connected the points with a line. What I'd like to do now is use those 2 points to determine the slope of that given line. Now, we need to go back to the formula that I mentioned to you a few minutes ago to calculate that slope. The slope is going to be the change in y divided by the change in x, or rise over run. Well, how do we calculate the values in this fraction once we are given those 2 points? Well, I would suggest that we look at the same graph now with just 2 extra little line segments drawn in. I'm going to take the 2 points that I already highlighted, and from the lower left-hand point, I'm going to draw a little horizontal segment. And then from that higher point, I'm going to drop a vertical segment so that those 2 segments, along with the line that we were given in the first place, make up a right triangle. Now, the lengths of the 2 segments that we've drawn in are exactly the rise and the run. So if you take the length of the vertical segment that we drew in to create our right triangle, we will have the rise. And if you take the length of the horizontal segment, you'll have the run. In this case, the vertical segment is exactly 2 units long, and the horizontal segment is exactly 1 unit long. Simply look at the units on the axes of our graph in order to see this. And therefore, the slope of this particular line is exactly 2 divided by 1, which is 2. Now, let me point out something very quickly. It's very tempting to say that the slope is 1 divided by 2 instead of 2 divided by 1. That's a common mistake that you don't want to make. When you're writing down the slope, it's always the change in the vertical direction or the change in y divided by the change in x. So be very careful that you always write the numerator as the change in y and the denominator as the change in x. So the slope of that line was 2, but you might be saying, gosh, I really benefit from having a formula. Could you give me a general formula that would help me to know what the slope is no matter what points you gave me, and I think that's a good idea. So let's say the following as our formula for slope. If you're given any 2 points in the Cartesian plane and their coordinates are x1, y1, that's the first point, and x2, y2 for the second point, then we're going to say that the slope of the line connecting those 2 points is given by the rule y2 minus y1 divided by x2 minus x1. So I see it's the change in the y's, or the difference in the y's, divided by the change in the x's. Now, let me make one other comment very quickly before we move on to another quick example. When you write down y2 minus y1 over x2 minus x1, you must use the coordinates in the same order. Here's what I mean. If you're going to choose y2 minus y1 for the numerator, then you've chosen the y coordinate out of the point x2, y2 as the first piece in the numerator. When you do that, you must choose the x pieces in the denominator then in the same order. So the slope is y2 minus y1 over x2 minus x1. Don't switch them and do the following. y2 minus y1 over x1 minus x2. You will have crossed up your information. You'll get the wrong slope. Now, let's use this formula to go back to the example I did a moment ago and just make sure that we get the same slope between the 2 points 0, 1 and 1, 3. Using the formula that I gave you, slope equals y2 minus y1 over x2 minus x1, we would have 3 minus 1 on top, those are the 2 y values being subtracted from one another, divided by 1 minus 0. Those are the 2 x values being subtracted from one another. The numerator, 3 minus 1, is 2. The denominator, 1 minus 0, is 1. 2 divided by 1 is 2. And that's what we got earlier. So that checks the work that we did a moment ago. Now, some of you might be asking, and it would be a good question if you were asking it, what if we had used different points on the line that we started with? I mean, what's so special about 0, 1 and 1, 3? If we used 2 different points, would we still get a slope of 2 on that line? Well, we hope we do, right? The slope ought to be 2 no matter what 2 points we choose. And so I'm going to suggest that we look at 2 very different points on the line and we see if we get the same slope. So, look back at your image now and you should see that 2, 5 is a point on the same line, and -4, -7 is also a point on that line. Now we should be able to use those coordinates in order to calculate the same slope. So let's do so. Let's use our formula, change in y over change in x, or y2 minus y1 over x2 minus x1, and let's see if we get the same answer. Well, the numerator is going to be the change in the y, so that's going to be 5 minus the -7. The denominator is going to be 2 minus -4. Notice that I started with the 5 on the top, which was the y coordinate in the point 2, 5. I started then in the denominator with the 2, which was the x coordinate for the 5. So I have 5 minus -7 divided by 2 minus -4. Remember, 5 minus -7 is the same as 5 plus 7, and 2 minus -4 is 2 plus 4. So I have 12 on top, I have 6 on the bottom. That fraction looks very different, but when you reduce it, you just get 2, and we get the same slope, which is fabulous. You can probably see why all those lessons we did earlier on with adding and subtracting negative and positive signed integers really paid off. Notice how those calculations of slope, just a bit of arithmetic, turned out to have a lot of trickiness to them with all those minus and plus signs. Don't worry about those things, just make sure you're very careful as you do your arithmetic in calculating slope. All right, let's try a second example now with a totally different line. I want us to find the slope of the following line. I want you to notice that I've labeled 2 points again on the line. It's very important that we find at least 2 points in order to find the slope. The 2 points I've labeled now are -1, 7 and 2, -8. So one of the points is in quadrant 2 and the other point is down in quadrant 4. We can use those 2 points to find the slope of this new line. So let's do it together. The slope is the rise over the run, or the change in y over the change in x. And in this case, using the 2 points that I've given you, we would have the following. Numerator would be -8 minus 7, and the denominator would be 2 minus -1. All right, we can now simplify that fraction a bit. The numerator becomes -15, and the denominator is actually 2 plus 1, if you think about it for a moment. 2 plus 1 is 3, so I have -15 divided by 3. And remember, when you have a negative on top and a positive on the bottom, the division is going to be a negative for the answer. And so I'm going to get -5. 15 over 3 is 5. So the slope of my line here is -5. Now, here's a comment I want you to think about. We'll talk about it a little bit in just a minute. Notice that in the first example, I had a positive slope. It was 2. And now in this example, I have a negative slope, which is -5. Is it all right to have a negative slope? I mean, was that a legal thing to have happen? Or should we have been thinking critically there? Maybe we would have caught a mistake. Well, the answer is that we took both of those slopes exactly correctly. So don't fret, you actually got the right answers in both of those cases. But I want you to think about why one of the slopes was positive and one of the slopes was negative. So here's what's happening. If your line is increasing, or if your line is going up as you look at it from left to right, then your slope is going to be positive. That was the case in our first example. The line was going up like this. As you read it from left to right, it was going up. Your slope then will be positive. If your line, on the other hand, is decreasing, so it's going down as you read it from left to right, then your slope is going to be negative. And in the example that we just completed, that's exactly what happened. The line was going down like this. As you see it, reading from left to right, it went down, and that slope is going to be negative. It was -5. Now there's a second comment we need to make with regard to slope. The slope is trying to tell us something about the steepness of the line. And so it's important not only to think about the sign, whether it's positive or negative, it's also important to think about the size of the slope as well. Notice that in the case of the slope of -5, the line was actually more steep than the case where the slope was +2. So I'm sorry for the pun here, but what is the point of what I'm trying to say? Well, the point is, as we deal with points and lines, if your line is very, very steep, so it's actually trying to go vertical, if you will, then you're going to have a larger slope. Now, it might be something positive and large, like +100, or if it's trying to be steep but it's going negative, then you might have a -100 for the slope. If your line is more flat, so it's trying to get more horizontal, then you're going to have a very small slope. And by having a small slope, I mean it's going to be close to 0. So in fact, a line that just looks maybe like this would have a slope maybe of just 1/2 or 1/10 in the process. So we have the idea now of steepness. For example, a line of slope 20 might be very, very steep in this direction, but the line of slope 1/10, which is only 0.1, might be very, very flat. So you have to balance out now the issues of the size of the slope and the sign of the slope, positive or negative. And those two very different things are going to tell you two very different things about the lines that you're studying. Okay, so let's look at some more examples then. Let's go back to just finding the slope between 2 points. Let's take the points -2, 8 and 6, 7. Now, what's the difference between this example and previous examples? Well, I'm not showing you any graph. All I've done is given you 2 points in the Cartesian plane. Well, do we need the line then? The answer is absolutely not. Once you have those 2 points, you can calculate the slope to your heart's content, because all you need is the formula. y2 minus y1 over x2 minus x1. Now, of course, once we calculate that slope, it'll tell us the slope of the line that would go through those 2 points, but I don't need the line in order to calculate that slope. So let's use our formula. y2 minus y1 over x2 minus x1. In this case, that would give us the following. The slope would be 8 minus 7 divided by negative 2 minus 6. Well, 8 minus 7, that's just 1, and negative 2 minus 6 is negative 8. And so I have just negative 1/8 as my slope. Now, before we go anywhere, we should really ask ourselves, what does negative 1/8 as a slope tell me about the line that would connect these 2 points? Okay, the slope is negative, and that means that the line is going to go down somehow as I look at it from left to right. But all the negative tells me is that it goes down. It doesn't tell me whether it's steep or whether it's relatively flat. But now I have to think about the size of that slope, and the size was 1/8. If I take the absolute value of negative 1/8, I get 1/8. 1/8 is pretty small. It's only 0.125 if you do its decimal equivalent, and that means, because it's small, that the line is going to be relatively flat. So it's going to go down, but it's going to be relatively flat in the process. And if you were to plot those 2 points and then look at the line in the Cartesian plane, that's exactly what you'd see. Now, before we move to the next example, I'd like to think about the following. Some of you might be saying, what if I used the points in the opposite order? You know, I keep telling you which point to use first and which point to use second in the equation for slope. What if I actually used the 6, 7 point first and the negative 2, 8 point second? Well, let's try it. Let's use the same formula, but use the 6, 7 information first. Well, in that case, the slope would be 7 minus 8 divided by 6 minus negative 2. Okay, what do we get then? 7 minus 8, that's negative 1. 6 minus negative 2 is the same as 6 plus 2, which is 8. So I have negative 1 over 8, and that's the same answer we had as before. So what's the point? The point is the order in which you use the points in the slope form does not matter. All that matters is that you divide the y information by the x information. And once you've done that, you're good to go. Okay, let's find the slope of another line, and I've chosen some points kind of carefully this time to see what happens. Let's find the slope between the points 4, 6 and negative 7, 6. Again, I don't need the graph of the line to calculate the slope. I really just need the 2 points. So let's just go after the slope using the coordinates that were given to us. The slope is going to be the rise over the run, the change in the y's over the change in the x's. So I'm going to have the following. The numerator will be 6 minus 6. Did you notice that both of the y coordinates were actually the same? They're both 6. The denominator is going to be 4 minus negative 7. Okay? What does the numerator become then? Well, it becomes 0. And the denominator becomes 4 plus 7, which is 11. Now, what is 0 divided by 11? This often gives students trouble. Well, 0 divided by 11 is exactly 0. When you have a 0 in the numerator of a fraction and the denominator is not 0, then that whole fraction is 0. A 0 in the numerator of a fraction is not a problem in a fraction. So keep that in mind. 0 divided by 11, 0 divided by 19, 0 divided by 3, they would all be 0. Now, that's a pretty small slope. What kind of line has a slope of 0? Well, if you plot those 2 points that I gave you in the Cartesian plane and you connect the dots, you'll see exactly the kind of line you'll get. You'll get a horizontal line. In fact, we can say the following. Every horizontal line has slope 0. To use a fancy mathematical term, this is a characterization of horizontal lines. Okay, what do I mean by that? What I mean is this. Every horizontal line has slope 0, and every line with slope 0 is horizontal. So if you ever have a line that has slope 0 and you haven't graphed it yet, you immediately know that it has to be flat, completely flat. It has to be a horizontal line. Well, I'd like to look at one more example along these lines related to slope, and here it is. Look at the following graphic. I've drawn the line and I've labeled 2 points, and the 2 points in this case have coordinates 3, 1 and 3, 8. Let's see what happens when I calculate the slope of that line. So here we go. The slope between those 2 points is going to be 8 minus 1, so that's the difference between the two y coordinates, divided by 3 minus 3. That's the difference in the x coordinates. Okay, what does that give me when I simplify for just a second? Well, it gives me 7 on top, 8 minus 1 is pretty easy to calculate, and it gives me 0 on the bottom. Now, this is very, very different from the fraction that we were looking at just a few minutes ago. Notice now that the 0 is in the denominator rather than in the numerator. So, what is 7 divided by 0? Well, to use a big math term, we say that that slope is undefined, or we say that you can never divide by 0. Division by 0 is undefined. And therefore, we have a problem, because this line doesn't seem to have a slope. All the other lines we've looked at in this lesson had a slope, 2 or -5 or -1/8. In this case, 7 over 0 is undefined. It is not a real number. And so we're going to say that this vertical line has undefined slope. Now, you might say to me, well, maybe we just made a mistake, or maybe we could use 2 different points on the line other than the 2 points that were there, and we'd get a different slope and everything would be fine. Well, here's the problem. For any 2 points you pick on that line, the x coordinates are both going to be 3, whether it's 3, 0 or 3, 1 or 3, 8 or 3, -16. And that means that in the denominator of your slope, you're always going to have, in this example, 3 minus 3. You're not going to be able to get around that. And because of that, you're going to get 0 in the denominator. And that's going to be undefined. So our slope for a vertical line is always going to be undefined. We'll say we simply cannot find the slope of a vertical line, and that's sort of the opposite of the slope of a horizontal line, which is always just 0. As we close out today's lesson, I'd like to spend a few more minutes talking about these fractions where zeros show up, either in the numerator or in the denominator. Believe it or not, as someone who's taught college-level students for a long, long time, this seems to be an issue even for college students when zeros show up either in the numerator or in the denominator of a fraction. So let me talk about that again just for a moment by giving you a quick example. I said earlier that something like 0 over 7 is equal to 0. Let me give you a quick analogy to why that's true. Let's say you had 0 pizzas, just bear with me for a second, and you had 7 people that you wanted to divide 0 pizzas up with. Well, how much pizza would each of those 7 people get? Well, you have no pizza, so the answer is each person would get 0 pieces of pizza. That's why 0 over 7 is 0. But let's take the picture and flip it. What if you had the fraction 7 divided by 0? I said a moment ago that that was a problem. Think about the thing I was saying about pizzas one more time. Now you have 7 pizzas and you want to divide them amongst 0 people. How much pizza would each person get? Well, this makes no sense. You have no people to give the pizzas out to. So 7 over 0 makes no sense at all. 7 pizzas, 0 people. how much does each person get? It doesn't make sense. So keep in mind, 0 over 7 equals 0. 7 over 0 is undefined. Well, we've seen today this very important concept related to lines, which we call slope. We've calculated slopes for a number of lines. We've talked about how their signs, plus or minus, tell us something about which direction the lines are going in. And we've talked about how the size of the slope tells us something about their steepness or their flatness. Lastly, we saw two very special types of lines: horizontal lines and vertical lines. In the coming lessons, we'll talk more about how slope plays a key role in the algebra related to straight lines. Next time, we'll use what we've learned about slope to begin graphing certain linear equations which are in what is sometimes called the slope-intercept form. I'll see you then. In our last lesson, we spent time talking about slopes of lines, and now in this lesson I'd like to shift our focus a bit to studying the graphs of linear equations. It's very important that we remember that algebra is much more than solving equations and manipulating algebraic expressions, x's and y's and so on. In particular, it's very important that we keep in mind the visual or graphing side as we study algebra. So as we get started, let me encourage you to get some graph paper if you don't have it already. It's going to be very, very helpful as we walk through the lesson today. My main goal in this lesson is to introduce you to the slope-intercept form of the equation of a line. In fact, we're going to do this in two directions today. Sometimes we're going to start with the graph of a line and we'll write down its equation, and sometimes we'll start with the equation of the line and take that and draw the graph that corresponds. So let me start by sharing the definition of the slope-intercept form of a line. If m is the slope of a line, and often the letter m is going to refer to the slope of a line in this lesson, and b is the y-intercept of the line, that's the place where the line crosses the y-axis, then the slope-intercept form of the equation of that line is going to be y equals m times x plus b. Or most of the time I'll just say y equals mx plus b. So here's the picture you should have in mind as we think about y equals mx plus b. If you look at the image of the line before us, you'll see that there's a y-intercept. That is the point where the line crosses the y-axis. And notice that in this case, the point that it crosses the y-axis at is 0, 1. It would be the 1, that y value, that we would focus on for the letter b. The slope of this line, how steep it is or how flat it is, that slope would be what we would call m. So, with that said, let's do some very specific examples to determine the slope-intercept form of the equation of a line. So let's look at this line together. We notice that it's got a y-intercept. It also has an x-intercept. It turns out we don't need to worry about the x-intercept, in fact, but to write down the slope-intercept form of the equation of this line, I'm going to need to know its slope, and I'm going to need to know its y-intercept. Well, the y-intercept is very easy to figure it out here. It is b equals 3. Notice the point where the line crosses the y-axis. That point has coordinates 0, 3. So b is 3. Well, that's half the problem. Now I just need to find the slope, which is this letter we're calling m in this lesson. Well, remember from the previous lesson that the slope is the rise over the run. So it's the change in the y direction divided by the change in the x direction. You can pick any 2 points that you want to find the slope of this line. So I'm just going to pick 2 points. One of them is 0, 3. That's pretty clear from the graphic. But the other one, I can choose whichever I want. Well, I'm going to choose 1, 5. That point is also on the line. Remember, you have to pick a point on the line. You can't just pick some point randomly out of the Cartesian plane. But if you pick a point that's on the line, you're good to go. So I'm going to pick 1, 5. My 2 points then are 0, 3 and 1, 5. The slope formula that we saw in the previous lesson is y2 minus y1 over x2 minus x1. And so the slope is going to be 5 minus 3 over 1 minus 0. What does that give me? It gives me 2 in the numerator and 1 in the denominator, and 2 divided by 1 is 2. Note that the same would have been found if you had used minus 1, 1 and 3, 9. That's where the 2 points on the line differ from the 2 points we talked about earlier, but we should get the same slope. So let's see what we get then. The slope is going to be, using those 2 points, 9 minus 1 divided by 3 minus negative 1. That gives us 8 on top, 9 minus 1, divided by 3 plus 1, or 4. 8 divided by 4 is 2. And that was the slope we found earlier when we used the other 2 points that we mentioned. So I can now write the equation of my line in slope-intercept form. Remember, it's y equals mx plus b. M is 2, b is 3, so I have y equals 2x plus 3. Well, before we go anywhere to another example anyway, we should ask ourselves a question. Does this answer make any sense at all? Well, the 3 at the end makes sense because that was the y-intercept, but what about the 2? The 2 was the slope. Well, I can look at the line that we started with and I can see that the slope was definitely positive because the line is going up as I read it from left to right. I can't really tell so much about the steepness, but it's about right. Having a 2, for example, as opposed to, say, 200 for slope. If the slope had been 200, my line would have been much more vertical. But having a plus 2 there makes sense. If we had found negative 2 for slope, we would have thought the line was doing this, and that's exactly the opposite of what we should have seen. Okay, let's look now at a second example where we're trying to find the slope-intercept form of the equation of a line. So we have a new line now. Notice that it looks like it's slanting down as you read from left to right. You should ask yourself, what does that mean about the slope? Talk about that in just a second. But before we go to the slope, let's ask this question. What is the y-intercept? Well, the y-intercept looks like 1. It looks like the line goes through the y-axis at y equals 1. What does that mean about the point on the line? At the y-intercept, the point has coordinates 0, 1. Okay, so b is 1. That's great. That's half the problem again. I just need m now, which is the slope, and once I have that, I can write down the slope-intercept form of the equation. Now, the line is going down like this. What does that mean about the slope? It means it's negative. Very good. So whatever I get for the slope at the end, I better get a negative answer. If I get a positive answer, I've made a mistake. Now, the slope is also going to have to be relatively small because the line is somewhat flat. It's not like this, for example. It's actually a bit flat. So hopefully we'll see a slope that's relatively small and negative. Now, I need 2 points to figure out this slope. Well, I already have the point 0, 1. That was the y-intercept. Do you notice there that there's also a pretty clear x-intercept? There's a point where the line crosses the x-axis. And thankfully, I can see the coordinates of that point pretty well. They're going to be 4, 0. Now, I have to tell you, I often make mistakes about these coordinates. I could have easily written down 0, 4 instead of 4, 0. But thankfully, we got it right when we said that the point was 4, 0. So, 2 points. 4 comma 0 and 0 comma 1. And once I have that information, I can find my slope m. So m is going to be the change in the y's divided by the change in the x's. The change in the y here is 1 minus 0, and the change in the x's is 0 minus 4. The numerator then is just 1, and the denominator is negative 4, and of course that's just the fraction, negative 1/4. Hey, that's negative, which is fabulous, and it's also small, which is also fabulous because that's exactly what we said we needed earlier. We needed a small negative slope. And therefore, the slope-intercept form of this equation is y equals negative 1/4 times x plus 1. Now, let's move to another example. I'd like to find the slope-intercept form of the following line, and I'm just going to point out right now that it's a horizontal line. Okay? The y-intercept is staring us in the face when you look at that graph. Can you see what the y-intercept is? B, the y-intercept, is going to be negative 2 because the line crosses the y-axis at y equals negative 2. So B is negative 2, that's great. Now I need to know the slope of this line. Well, do you remember what we talked about? When we talked about horizontal lines and slope, we said that every horizontal line has a slope of 0. And therefore, m in this example is going to be 0. That makes finding the slope-intercept form of the equation of this line easy. It's going to be y equals mx plus b, or y equals 0x plus negative 2, which is the same as y equals negative 2. So notice in this equation, the x term has disappeared. All right? This is very, very important. The only thing you see is y equals some number. There are no x's. That's going to be very important as we study horizontal lines. Their equations are always going to look like y equals negative 2, or y equals 5, or y equals 3. Y equals just a number. The x term will have disappeared, and that means we can see a very special form for a horizontal lines equation. Well, let's transition a bit and look at the problem from the opposite direction. So what do I mean by that? Here's what I mean. I want to take the equation of the line and hand that to us first, and then I want us to be able to draw the graph of that equation. So this is sort of the opposite skill to what we've been looking at so far in this lesson. So here's the example I want us to look at. Let's sketch the graph of y equals 5x minus 7. Okay, we want to sketch this graph, so the first thing we need to do, we need to take out a piece of graph paper and draw our axes, our x and our y axis. The x is the horizontal and the y is the vertical. And we need, if we can, to plot a couple points, because as soon as we could do that, we could just connect them to get our straight line. Well, the first thing we know from y equals 5x minus 7 is that the y-intercept must be at negative 7. So I can immediately plot a point. Now, where in the Cartesian plane is it located? It's located at the coordinates 0 for x and negative 7 for y. So it's down on the y-axis at negative 7. Okay? That's it. That's one of my points, and now I just need one more point. Again, if you can find two different points on this line, you'll be done. Because once you find those 2 points, you can connect them with a straight line, and you're done. So let's use the slope now to find a second point. We know from the equation that was given to us that the slope is equal to 5. That's the m, the number in front of the x. And how do you think of 5? You think of it as 5 divided by 1. Now, that ratio is the rise over the run. So let's walk through what 5 over 1 is really telling us. It's saying the denominator being the run, or the horizontal direction, means that when I walk to the right 1 unit, because the denominator is 1, I need to move up 5 units. Okay? The rise is 5 and the run is 1. So every time I walk 1 unit over, I need to walk 5 up. Or you might think of it this way: every time I walk 5 up, I need to walk 1 over. Either way, you'll get to the same point up here. So if I start with that y-intercept at 0, -7, and I move 1 unit over and 5 units up, I'm going to be at the point 1, -2. And again, if I start at 0, -7 and go up 5 and then over 1, I'm still going to end up at 1, -2. Now, once you have those 2 points plotted, just take out a pencil, a straight edge, maybe a ruler or something like that, and you can connect the 2 dots to make your straight line. Okay, let's look at another example like this, where you want to take the equation that you're given and sketch the graph of that equation. We're going to make it a little more complicated now by throwing in some fractions. But don't worry, we'll be fine. Here's the equation I want us to sketch. Y equals -1/2 x plus 7/2. Okay, now, as we did in the previous example, I already know what the y-intercept is. You know, these examples are all about interpreting the information that's been given to us from the equation. So my y-intercept is coming from the number at the end of the equation. That's the 7/2. And therefore, I know one of the points on the graph is 0, 7/2. So I start at the origin and I simply march 7/2 units, which is the same as 3 1/2 units, up the y-axis, and I mark a point. Now, I've got to get that second point in order to figure out how to plot the graph. And so I'm going to now use the slope information. And in this case, I'm going to use the -1/2. So that's m. Now, what does -1/2 tell me about the line in question? How can I go from one point to the next on the line? Well, by having -1 divided by 2, here's what I know. Every time I move 2 units to the right, I've got to move down 1 unit. Why down and not up? It's because of that negative sign that's in front of the 1. So every time I move 2 units over to the right, I have to move down 1 unit. Now again, if I had started at the same point and moved down 1 unit first and then 2 to the right, I'd land at the same place. The point is, I can get to another point on this line if I start at the y-intercept and go through the process that I was just describing. So, start at 0, 7/2 and move 2 units to the right and down 1 unit. Well, what do the coordinates of that new point look like? Well, they're going to be at 2, because I started at 0 and moved 2 over to the right. What's the y-coordinate going to be? It's going to be 7/2 minus 1, because I had to go down 1 unit. Well, what is 7/2 minus 1? I've got to be able to calculate that now. 7/2 minus 1 is the same as 7/2 minus 2/2. And now with a common denominator, I can subtract 2/2 from 7/2, and I will have 5/2. 7/2 minus 2/2 is 5/2. So the point on the line with this 0, 7/2 is 2, 5/2. And now I have 2 points on my line. And I can plot both of those, just draw them in on my grid. Now I want you to stare at those 2 points for just a second on your paper. Notice that the line that you're going to draw that connects those 2 points will have what kind of slope? Is it going to be positive or is it going to be negative? Well, the answer is it's definitely going to be negative because your line is going like this. So it's going down as you read it from left to right, okay? And with a slope of -1/2, 1/2's not that big, we would expect that the line would have to be relatively flat. Not steep like this, but pretty flat. In fact, your line will be pretty flat. And once you take the 2 points that you've drawn and just connect them, you'll see that your line is a nice, flat, negative sloped line. Okay, now I'd really like to change gears in this lesson and spend a few minutes talking about a different type of problem. So here's the question I want to talk about. It's still related to slope-intercept form of lines, but I want to think about it from a totally different perspective. What if someone walked up to us and gave us not the equation of the line and not a graph of the line, but a table of pairs of points on the line? Could we find the slope-intercept form of the equation of that line? You might ask, why in the world would I care about such an example? Well, the fact of the matter is, in the real world, when you're doing science, when you're doing lots of other things, what you get first is data. You get information, which typically could be points on a graph, for example. So we need to have the ability to actually have someone hand us data, which isn't very visual and doesn't have an equation wrapped around it, and use that data to either find an equation or plot the graph. So here's the example I want us to start with. I want us to find the slope-intercept form of the equation of the line with the following points. So here are the points now in a table. When x is 0, y is 5. When x is 1, y is 3. When x is 2, y is 1. When x is 3, y is negative 1. And when x is 4, y is negative 3. Now, don't let this table mess you up. All that's happening is this is a shorthand way of writing down 5 points, or 5 ordered pairs. And those ordered pairs would be 0, 5, 1, 3, 2, 1, 3, negative 1, and 4, negative 3. Okay, so from that table, I want us to figure out the slope-intercept form of the line. That means I need to figure out two things, the y-intercept, and I need to figure out the slope. All right, how do I get the y-intercept from the table? Well, what is true about the y-intercept? What's true about it is that it's on the y-axis, which means its x-coordinate must be 0. Now, in the table that you were handed, is one of the points going to have 0 as its x-coordinate? Yeah, it is. In fact, it's the first value that you were given. The first point you were given was x equals 0, y equals 5. And therefore, the y-intercept of that line is going to be at b equals 5. So you've now found half of the slope-intercept form of this equation. And now what you need is the slope, which we call m often. Well, it looks like every time I increase the x by 1 in my table, I decrease the value of y by 2. Do you see that pattern in the table? Every time the x's increase by 1 in the first row of the table, the y's go down by 2. That means when the run changes by 1, the rise changes by negative 2. So in fact, I should go like this. The rise goes down by 2. And therefore, the slope is going to be negative 2 divided by 1, which is negative 2. So my m value is negative 2. And therefore, the slope-intercept form of this equation is negative 2x plus 5. I should say y equals negative 2x plus 5. Remember, an equation always needs an equals sign. Now, you might say, boy, you found that slope fast. I didn't like that at all. Okay, if you wanted to calculate the slope, you could have just taken 2 points out of the table and done y2 minus y1 over x2 minus x1. And we would have found the same result. We would have found negative 2. But as you're staring at table data, I want you to see if you can see patterns like the one we saw. And if you can see them the right way, you can see things like the slope. So if you want to calculate it, please do. But you should get negative 2 for the slope if you calculate it from the points. Okay, let's do another example with one of these tables just to get the practice. Let's find the slope-intercept form of the equation of the line with the following points. Now, we're only going to go with about 3 points here, but that's okay. The table says that 3 of those points are negative 2, negative 2, 0, 4, and 3, 13. That's how we're going to read that data. Now, I want you to notice again that the y-intercept of this line has pretty much been handed to us with no work, but we have to interpret it. What's true about the y-intercept? It's a point where the x-coordinate is 0. In the table, Do you have a point where the x-coordinate is 0? Yes, you do. It's the one 0, 4. So b in this example is going to be 4. You needed that for the slope-intercept form of the equation. Now you've got it. So now again, you just have to find the slope. So the question is, how do you calculate the slope in a case where the x is changing so dramatically? Notice in this table that the x's are changing not by 1, but by 2 or 3. In the earlier table, in our previous example, the x's were just so friendly, they were just growing one at a time. Here, the x's are kind of bouncing around. So how in the world am I going to figure out the slope? Well, the answer is just pick 2 points out of the table and calculate the slope with the rule we've already seen. It doesn't matter which pair of points you choose as long as they're different points. And in fact, we're now going to calculate this slope a couple different ways using different data from the table just to make sure we get the same slope different times. So here we go. Let's use the first 2 points in the table, -2, -2 and 0, 4. If I use those 2 points out of the table, here's the slope that I get. M equals 4 minus -2 divided by 0 minus -2. That's y2 minus y1 over x2 minus x1. And if you simplify that a bit, you're going to get 4 plus 2 on top and 0 plus 2 on the bottom, which is 6 over 2, which is 3. So we could just stop here. We could say, look, the slope is 3, we're good to go. But just for fun, let's try using 2 different points to see if we get the same slope. So I'm going to use the 0, 4 and the 3, 13, and I'm going to see if I actually get the same slope in the process. In that case, using y2 minus y1 over x2 minus x1, the slope would be 13 minus 4 divided by 3 minus 0. 13 minus 4, that's 9. 3 minus 0 is 3. 9 over 3 is 3. Excellent. We got the same slope, which we needed to get. If this is the graph of a straight line, then the slope should be the same no matter what 2 points we choose. If we had gotten something other than 3, we would have known we made a mistake, in fact. But just for fun, let's actually use the first point and the last point in the table, find the slope using those, just to make sure we've got this down. So here we go. Use -2, -2 and 3, 13. Those are 2 points on my line. Let's calculate the slope. Using y2 minus y1 over x2 minus x1, I'm going to have 13 minus -2 divided by 3 minus -2. What does that give me? The numerator becomes 13 plus 2, and the denominator becomes 3 plus 2. That's 15 over 5. When you simplify that fraction, you get 3. So no matter how you calculate the slope, no matter which points you choose, your slope in this example is going to be 3. Now, let's bring all the information together. The slope is 3, and a while ago, we found out that the y-intercept was 4. And once we know that, we can write down the slope-intercept form of the equation. It's going to be y equals mx plus b, or y equals 3x plus 4. Now, I'd like to look at another example that has this kind of form where we use a table of data. And so let's look at the following table. Find the slope-intercept form of the equation of the line that has that information or has those points on it. So what's my table look like? Well, the points look like they're going to be 1, 4, 3, 4, 5, 4, 6, 4, and 8, 4. So I want you to notice there, that looks like a pretty special line because all of the y values look like they're the same. Okay, let's see what kind of line this really is. Well, the first thing we've been doing in all these examples, what have we been doing? We've been finding the y-intercept. Wait a minute, how did we find the y-intercept? It was the place where x was equal to 0. Do we have x equals 0 in my table? No. Oh no, what in the world are we going to do? Well, don't worry too much. We're actually okay. Let's think for just a second about what this line looks like. If all the y values are actually the same, then that means all the points are at the same height above the x-axis. What kind of line has all of its points the same height above the x-axis? It's a horizontal line. This table actually refers to a bunch of points on a horizontal line. Now, if it's horizontal and all of the points are 4 units above the x-axis, where's the y-intercept? The y-intercept is at 4. So b equals 4. Now I need the slope of the line. Do you remember? The slope of a horizontal line is m equals 0. You could have calculated that using a couple of the points. In fact, if you used 3, 4 and 8, 4, then the slope would be 4 minus 4 divided by 8 minus 3, or 0 divided by 5. Remember, that's okay. That's equal to 0. So the slope equals 0, and the y-intercept equals 4, and therefore my equation is y equals 0x plus 4, or just y equals 4. Now, I'd like to move forward then and just finalize our lesson today by sharing with you just a few closing thoughts. First of all, notice that we've talked about the slope-intercept form of the equation of a line today. I want you to remember that you need 2 pieces of information for that. You need the y-intercept, which we often call b, and you need the slope, which we often call m. But with that in mind, let me point out something. In almost every one of the examples we did today, the b, the y-intercept, was given to us. In fact, it was only in the last example when we didn't have that y-intercept handed to us. What would happen if we didn't know that value of b? Well, we'd have to do more work to find it. You can actually find it with a little algebra, but it's not always easy. And that means that the slope-intercept form is not always the best form of the equation of a line. It's okay to have, and it's a good one to have, but we might want to come up with a different form of the equation of a line. What does that mean? It means that in the next lesson, we're going to learn about other forms of the equation of the line where we don't have to have the y-intercept. And I'll talk about that in our next lesson. As we continue to look at the graphical side of linear equations, I'd like to demonstrate another form for writing the equation of a line. It's known as the point-slope form of the equation, and it's very versatile. In fact, I think it's more versatile than the slope-intercept form for the equation of a line. Let me show you what I mean with an example. I'd like you to find the equation of the line given here. Now, let me be clear about what this graph tells us and what it doesn't tell us. First of all, we see that the line goes through the point 2, 0. Now, that's on the x-axis, and so it's the x-intercept of the line. Let's assume we were also told that the line goes through the point -2, 10/3. That's up in quadrant 2. From here, I'd like to work out the equation of the line. Well, with the 2 points that have been given to us, we can calculate the slope relatively easily. We've been doing that now through a couple of lessons. Let's go through the practice of calculating the slope once again with the 2 points that we have, -2, 10/3 and 2, 0. Well, with that information, we know that the slope is rise over run, or y2 minus y1 over x2 minus x1. So I can use my data and plug it into the formula. And then the slope is going to be 10/3 minus 0, all divided by -2 minus 2. Well, the numerator is pretty easy to simplify. That's just 10/3, and the denominator is -4. Now, 10/3 divided by -4 is the same as 10/3 times -1/4. And if you write all that out, you'll see that the final answer there then is -10 divided by 12. 3 times 4 is 12. And -10 divided by 12 can be reduced to -5 divided by 6, because the 10 and the 12 both have a factor of 2 that can be canceled. Now, I'm trying to get the equation of the line that someone gave me to start this problem. I have found the slope, but I need one more piece of information. And if I want to use the slope-intercept form of the line, I need to find the y-intercept. Now, again, not the x-intercept. I know what the x-intercept is here, but I need the y-intercept. That's what I need in the slope-intercept form. But what is it? Look back at the graph of the equation that was given to us. Can you tell what that y-intercept value is? Notice that it doesn't cross at a whole number value. It's obviously somewhere between 1 and 2, but is it 1.5, 1.4, 1.6, 1 1/3, 1 2/3, 1 4/7? I don't know where it is, at least not right now. It's just not clear from the graph what that point is. And that's the downside of the slope-intercept form of the equation of a line. If you can't easily find the y-intercept, or if it hasn't been given to you, then the slope-intercept form is a bit unfriendly. Now, don't get me wrong. We could go find the y-intercept with a little bit of algebra, but I think it's a better form of the equation to write down when you write down the point-slope form. And that's the subject of today's lesson, and so that's what I want to share with you now as we move forward. The definition of the point-slope form of the equation of a line that passes through the point x1, y1 and has slope m is the following. It's y minus y1 equals m times the quantity x minus x1. Now, let me say a few things about that formula. First of all, it's extremely important. So as soon as you can, you should put that to memory. The second comment I want to make is this. The y1 and the x1 in the formula are going to be constants. They're going to be the numbers that come from the point you were given. The y and the x are going to be variables, so we'll leave those alone. It gets a bit confusing when you see a y and a y1 and an x and an x1. Don't worry about that. Plug in the x1 and the y1 from the point that you have, and then leave y and x alone. Now, with this form of the equation of a line in our hands, we can actually write down the equation of the line we were discussing a few minutes ago. We found that the slope was negative 5/6. That's going to be the m value in our equation. And we already knew one point that the line went through. That was the point 2, 0. Well, that's exactly the information we need to use the point-slope form of the equation of a line. Using that formula, y minus y1 equals m times x minus x1, I can now write down the following equation for this line. It's going to be y minus 0, that's the y value of the point, 0, y minus 0 on the left equals negative 5/6 times the quantity x minus 2. Notice that that formula is perfectly fine for this line. That's the right equation. But I could actually use a different point now and write down what appears to be a different equation. Remember, there was another point I said was on the line, and that was the point negative 2, 10/3. Why not use that point instead of the point 2, 0? The answer is, why not? You can use it if you'd like. So let's now write down the equation of the same line using that different point. The equation is going to be y minus 10/3, it's the y value there, equals negative 5/6 times the quantity x minus negative 2. The x coordinate here is now negative 2. So inside those parentheses, I'm going to have x minus negative 2. If I simplify that equation just a bit, my new equation will be y minus 10/3 equals negative 5/6 times the quantity x plus 2. Now, it would be very natural for you to say to me at this point, now wait a minute. We just wrote down two equations for this line. Y minus 0 equals negative 5/6 times the quantity x minus 2, and y minus 10/3 equals the quantity negative 5/6 times x plus 2. Those don't look anything like each other. Well, they both have a minus 5, 6 in them, and they have a y and an x, but they look a lot different from one another. You'd be right in saying that. But the fact is that the point-slope form of the equation of a line can look very different because it depends on the point you choose to use. But we can also rewrite both of these equations in such a way that they look the same. In fact, if we rewrote them a bit with some algebra and made them look like the slope-intercept form of the line, they would look the same. Let me do that for you right now. The first equation would look like the following. Y minus 0 equals negative 5, 6 times the quantity, x minus 2. Well, of course, y minus 0 is just y, so the left-hand side becomes y, then it equals negative 5, 6 times x minus 2. Now I'm going to distribute the minus 5, 6 into the parentheses. So I want to multiply the x by a minus 5, 6, and I want to multiply the negative 2, or the minus 2, times a negative 5, 6. And when I do that, the right-hand side becomes negative 5, 6x plus 10 sixths. Again, the plus comes from the minus in front of the 5, 6 and the minus in front of the 2. And now I have the equation y equals negative 5, 6x plus 10 sixths. 10 sixths can be reduced just a little bit. It's the same as 5 thirds. And it means that my equation is actually y equals negative 5, 6 times x plus 5 thirds. Notice that that's in the form y equals mx plus b. In fact, we now know that the slope is negative 5, 6. I knew that already. But I also know that the b is 5 thirds. Remember what b is for? It's the y-intercept. So if you go back to the picture that we drew originally, we now know what that y-intercept is. It's 5 thirds, or 1 2/3. Remember I said it was something like 1 1/2, or 1 1/3, or 1 2/3. Now we actually know what it is. It's 1 2/3, and we found that thanks to the point-slope form of the line. Now, I had two equations that looked very different earlier. I want to take the second one now and convert it from point-slope form into slope-intercept form, and I want to see what it looks like. So let's do that here. That second equation was y minus 10 thirds equals negative 5, 6 times x plus 2. Now, distribute the minus 5 sixths on the right-hand side again, and you'll have y minus 10 thirds equals negative 5, 6x minus 10 sixths. Now, that looks pretty complicated, but we're okay. There's a constant on the left, which is negative 10 thirds, and there's a constant on the right, which is negative 10 sixths. I can add the 10 thirds to the right-hand side, and when I do that, my equation will then be y equals negative 5, 6x minus 10 sixths plus 10 thirds. Rewriting 10 thirds as 20 over 6 to get a common denominator, I'll then have y equals negative 5, 6 minus 10 sixths plus 26. Minus 10 sixths plus 20 sixths is actually plus 10 sixths. And so I have y equals negative 5, 6x plus 10 over 6. 10 over 6 is the same as 5 over 3. And so my equation is y equals negative 5 over 6 times x plus 5 over 3. Do you remember that equation? That's the same equation we found earlier when we took the first version of the point-slope form and rewrote it into slope-intercept form. So what have we seen? We've seen that this point-slope form of the equation of a line is more versatile because it doesn't need the y-intercept, and it doesn't mind which point you use. No matter what point you choose, you always have the same equation. It might look different from another equation, but they actually are the same equation, just hiding underneath. Now, let's move now to another example where we can use the point-slope form of the equation of a line to our advantage. Here's the example. I want us to write the equation of the line that has slope 5 and passes through the point -1, -3. Well, with the slope-intercept form of the equation, we'd have difficulty because right now I do not know what the y-intercept is. No one gave it to me in the problem, but they did give me the slope and they did give me a point. And therefore, I can use the point-slope form of the equation to write the equation of this line. And here's what it is. It's going to be y minus the y value equals 5, that's the slope, times x minus the x value. Well, that's going to be y minus negative 3 equals 5 times x minus negative 1. If you cancel out those negatives there, the y minus negative 3 becomes y plus 3, and the x minus negative 1 becomes x plus 1. So the equation is y plus 3 equals 5 times the quantity, x plus 1. Now, let me share a few comments about the kinds of mistakes or pitfalls you can run into as you're using the point-slope form of the equation. First of all, some students will accidentally switch the roles of the x and y coordinate of the point when they're writing down the point-slope form of the equation. So, for example, instead of writing y minus negative 3 equals 5 times x minus negative 1, some students will write y minus negative 1 equals 5 times x minus negative 3. What they've done is switch to the x and the y coordinates at that point. And if you do that, you're probably going to get the wrong equation of your line. So please be careful with that very common mistake. And secondly, as I mentioned a few minutes ago, you can now write down the slope-intercept form of the equation of the line if for some reason you wanted it. So, for example, let's go back to the equation. Y plus 3 equals 5 times the quantity x plus 1. Then that formula becomes y plus 3 equals 5x plus 5. That's the distributive property. I've distributed that 5 into the x plus 1. Now I can subtract the 3 from the left-hand side over to the right-hand side, and I'll have y equals 5x plus 5 minus 3. 5 minus 3 is 2, and so I will have y equals 5x plus 2. And notice that that is the slope-intercept form of my line. Now, look at the graph that's on your screen, and you'll see the graph that had slope 5 and went through the point minus 1, comma, minus 3. Do you notice that it really does go through that point? Notice also that it goes through the point 0, comma, 2. That was the y-intercept that we found earlier. But I want to point out, if you started down at minus 1, comma, negative 3 and walked up 5 units and over 1 unit to the right, you would be at 0, comma, 2. Well, walking up 5 and over 1 is the rise over run. 5 up divided by 1 over. That's exactly the slope. That's why the slope is 5. And so those 2 points are definitely on this line because they match this slope information. Many of you have probably heard of the phrase, 2 points define a unique line. In other words, if I give you 2 points, you can draw exactly one straight line that goes through those 2 points. Well, it turns out, even if that's all someone gives you, the point-slope form can be used to find the equation of that line. The slope-intercept form typically is not going to be able to do that for you, but the point-slope form can. So let's do an example that looks like that now. I want us to find the equation of the line that passes through these 2 points, 3, comma, 2, and negative 1, comma, negative 5. Well, I would suggest that we use the point-slope form of the equation. We already have a point in hand. We actually have 2 points in hand. So all we need is the slope, and once we have the slope, we're set. But the slope is a piece of cake here because we just need those 2 points that they gave us. So let's calculate the slope now, and we'll be well on our way to finishing this problem. The slope in this case, remember we often call it m, is going to equal 2 minus negative 5 divided by 3 minus negative 1. Remember, it's the y2 minus y1 divided by x2 minus x1. Now, 2 minus negative 5 is 2 plus 5. 3 minus negative 1 is 3 plus 1. And therefore, the slope here is 7 divided by 4. That's positive 7 divided by 4, or 1 3/4. And now we can just write down an equation for the line using the point-slope form. And you can use any point you want. Well, we were given two of them. One of them that we were given was the point 3, 2. So I'm going to go ahead and use that one now to write down my equation. The equation for my line would be y minus 2 equals 7/4 times the quantity x minus 3. Now, I could use the other point if we'd like. Let's go ahead and do so. That point was -1, -5. And then my equation using the point-slope form would be y minus -5 equals 7/4 times the quantity x minus -1. If I simplify some of those double negatives, the minus -5 and the minus -1, by changing them to plus signs, I'm going to have y plus 5 equals 7/4 times the quantity x plus 1. I cannot stress enough that these two very different looking equations both represent the same line. Both of these equations would be valid answers to the problem we started with. So it's not always the case that there's just one correct answer to a mathematics problem. When you're using the point-slope form of the line, you can have many different correct equations. It's just about which point you use. The slope would all be the same. The point you use might be different. So just for fun, let's look at the graph of this line given the 2 points that we had. Now, as I showed a few minutes ago with other examples, look how difficult it could have been to find the y-intercept of this line with just the information that was originally given to us. Remember, the only thing they gave us was 2 points on the line. With that point-slope form of the equation, we actually can find the y-intercept. It turns out it's at the quantity -13 divided by 4. Or if I wrote it as a mixed number, it would be -3 1/4. Now, if you look at the graph for just a moment, you'll see that it does appear that the y-intercept crosses somewhere between -3 and -4. So -3 1/4 makes perfect sense. But what if you would have had to find that yourself? That would have been very, very difficult. But once you have the equation, you actually can find that point. Now, I'd like to shift gears just a bit and look at problems related to the point-slope form of the equation of a line from the opposite direction. What if we're given the equation of a line in point-slope form? Could we draw the graph of that line pretty quickly? Well, it's all about interpreting what's in the equation that we're given. So let's look at a few examples where we're given the equation and we interpret the information we need. So here's the first problem. Let's graph the equation y minus 6 equals 1/2 times the quantity x minus 3. Well, one key here is to recognize that this is the equation of a line and it's in point-slope form. We have the slope sitting out in front and we have a point embedded there, so we just need to be able to interpret what we've been given. Well, first of all, what's the slope of the line? Well, the slope is going to be that constant that's sitting in front of the right-hand side portion of the equation. And in this case, that constant is 1/2. So the slope is positive 1/2. Well, what else do we know? Well, we actually know the coordinates of a point through which the line passes. And that point is 3, 6. Again, remember, the point it's passing through is not 6, 3. That's a common mistake to make. The point is going through, or the line is going through the point 3, 6. The 3 is in the x and the 6 is in with the y. So the point we're going through is 3, 6. Now, we know the slope is 1/2 and we know a point that we're going through is 3, 6. If we started at 3, 6 and use the fact that 1/2 is the rise over run, we can actually find another point. So starting at 3, 6, we could go up 1 unit and over 2 units to the right. And if we did that, we would be at 5, 7. That's because 3 plus 2 is 5 and 6 plus 1 is 7. Now you have 2 points and you can plot the line through those 2 points by just connecting the dots once you've drawn the dots. And so your line is pretty straightforward to draw at that point. Notice that the y-intercept of the graph appears to be right around 4.5. It looks like it's going through the y-axis between 4 and 5. We could figure that out exactly using the point slope form of the equation, but that's not what was asked of us. So let's not fret over it for now. Notice also that the x-intercept appears to occur at -9, 0. And lastly, we should ask, does the graph even make sense? Well, it definitely goes through the point 3, 6. It definitely has a positive slope because it's going upward as we read it from left to right. But notice it's not very steep. It's not like this, for example. It's kind of flat. And so the fact that it had slope +1/2 seems to fit with the sketch that we've made. Okay. With that said, let's look at another example of this type. It's always good to try to do lots of examples in math of the same type just to nail down the ideas. So let's look at another example of this type. I'd like us to graph the equation y - 4 equals 7 times the quantity x + 2. Now again, we see that this is the equation of a line which is in point slope form. That's good. Now, let's interpret what's in the equation to help us understand how to graph the line. Well, can you see the slope? Do you see it sort of jumping out at you? The slope in this case is 7. It's that constant in front of the right-hand side of the equation. Now, if the slope is 7, it means that our line is going to go in this direction as opposed to this direction, and it's going to be kind of steep. We'll use that information in a second. Secondly, I need a point through which the line travels. All right, now, what would you say is a point? Well, some of you might say, I think a point that it goes through is 2, 4. Well, you'd be close, but you'd be incorrect. In fact, your graph would be very wrong if you had the line go through 2, 4. Why is 2, 4 not one of the points? It's that pesky plus sign in the original equation. Remember something, the point slope form of the equation of a line is y - y1 equals m times x minus x1. It's not y - y1 equals m times x plus x1. Do you see that difference of sign on the right-hand side? That is a common mistake, so be careful not to miss that. Now you might say, well, what in the world am I supposed to do then? I can't just erase that plus sign and make it a minus sign. What do I do? Here's what you do. You take y - 4 equals 7 times x plus 2 and rewrite the plus 2 as minus a -2. And your equation then becomes y - 4 equals 7 times x minus -2. And now that you have the equation in that form, you can actually see what your point is through which the line passes. Do you see it? It's -2, 4. So the guess of 2, 4 was kind of close, but we needed a negative in front of that 2 in order to get the right point. So I can now sketch the graph of this line. It passes through -2, 4, and it has slope 7. So to get another point, I start at -2, 4, I rise up 7 and over 1. And if I go up 7 and over 1, I'm going to be at the point -1, 11. Remember, that's what that 7 means. It's like a 7 over 1. So the rise is 7 and the run is 1. And once I have those 2 points plotted, I can draw the graph and I'm done. And once you've drawn it, you should again check that the slope of 7 seems to be making sense. Your line needs to be going upward as you read it from left to right. And now in this case, it should be pretty sharply upward as we go. Well, I'd like to look at one more example trying to see how the point slope form of the equation of a line can be used to graph a line that satisfies that equation. So here's the equation I want us to look at. Y minus 2 equals -3 times x minus 5. Okay, now this thing again is in point slope form. I see y minus a number equals a number times x minus another number. So I'm in perfectly good shape for the point-slope form of a line. Now, what's the slope? Well, where is the slope located? In the point-slope form of an equation, it's located right in front of that x minus piece on the right-hand side. And in this case, my slope is going to be -3. That negative comes along with the slope. So my slope really is -3. Or to use the letter that we've normally used for that variable, m equals -3. Okay? Now I have the slope. I need a point. There's a point there. It's hiding. It deals with that 2 and that 5. What's the point that the line goes through? It's not 2, 5. It's 5, 2. Remember, the 5 is first because it's with the x, and the 2 is second because it's with the y. So now I know the slope. The slope is -3, and I know a point, 5, 2. I can find another point on the line by starting at 5, 2, going down 3 units and over 1 to get to my next point. Why am I going down? Because the slope is -3. So I go down 3 units and over 1 to the right. And once I've done that, I can find my new point, which is 6, -1. And once I have that point, I can draw my line and I'm good to go. And now if I do plot those 2 points and connect them, I'll see that my graph goes downward like this as I read it left to right. And it should go down because the slope here was negative. Well, today we've seen a new way to write down the equation of a line. It's called the point-slope form of the equation. I really think it's a great way to write down the equation of a line. It's very flexible. It doesn't require me just to know the y-intercept of my line. So I would strongly encourage you to get comfortable with the point-slope form of the equation of a line. You'll certainly be using it again in future lessons. Next time, I'd like us to apply what we've been learning about equations of lines, like slope-intercept form and point-slope form, to some very special types of lines. And those are called parallel and perpendicular lines. I'll see you then. In this lesson, I would like to look at relationships between very special types of lines, and these are called parallel lines as well as perpendicular lines. First, let's talk about parallel lines. What's a good working definition of parallel lines? Well, how about this? 2 lines in the Cartesian plane are parallel if they never intersect one another. You've probably seen this idea of parallel in the past, either in another mathematics class or just in the usual English usage of the word parallel. Think about parallel streets maybe in the downtown of your city, or the lines that are on a football field, which are parallel. You might have even heard the phrase parallel universes to mean universes that don't intersect. But that raises a question. We've used it a lot in our English language, but from an algebra perspective, how can we describe when 2 lines are parallel? Well, the following property is very helpful. 2 non-vertical lines are parallel if they have the same slope and different y-intercepts. So if we just check on the slopes of the 2 lines and we make sure that the slopes are the same, but the y-intercepts are different, then we know that the 2 lines are parallel. So, for example, if I give you these 2 equations, y equals 3x plus 2 and y equals 3x minus 4, I can tell you that those 2 lines will be parallel. I haven't even seen the graphs yet, but I know that the 2 lines really will be parallel. Why? Because they both have the same slope. Do you know what that slope is? That's right, it's 3, but they have 2 different y-intercepts. The y-intercept of one of the equations is 2, the y-intercept of the other one is -4. Remember, those 2 equations are written in what's called slope-intercept form. Well, because they have the same slope but different y-intercepts, I know that those two lines are going to be parallel. And if you were to graph those two equations, you'd actually see that they're parallel. Just look at the graph and you'll see that the two lines will never intersect. I'd like to turn to looking at a couple of examples where we're not sure if the two lines are parallel, and we have to do a little bit of algebra work in order to figure it out. So let's start with the following example. Take the two equations, y equals negative 2x plus 7 and 10x plus 5y equals 12. Those are two perfectly good equations of lines. Let's figure out if those two lines are going to be parallel. Well, to do this, I need to figure out the slope of each line. That's the first thing that's important. Remember, to be parallel, the two lines are going to need to have the same slope. It's pretty clear that the line represented by the first equation has slope negative 2 because of the form of the equation as it was written. The problem is, what's the slope of the second line? I've got to get a little bit of work done in order to figure that out. Well, I'd like to do some algebra to rewrite that equation into slope-intercept form. So let's do that right now. The equation we started with was 10x plus 5y equals 12. In order to get that in slope-intercept form, I need to get the y by itself, preferably on the left-hand side. So let's leave the 5y by itself on the left-hand side. How am I going to get that 10x out of the left-hand side and move it over to the right-hand side? I'm going to subtract 10x from both sides of the equation. And if I subtract 10x from both sides of the equation, the 10x on the left minus the 10x will be 0, and that will be gone, and the left-hand side will just be 5y. But on the right-hand side then, a negative 10x or a minus 10x is going to show up, and then I'll have to add in the 12 that was already there. Remember, I had to subtract 10x from both sides. So the equation now is 5y equals negative 10x plus 12. But I need to get that 5 away from the y. Remember, I want to isolate the y, to use that language. And how do I get rid of a 5? Well, I can either divide by 5 or multiply both sides by 1/5. And in fact, that's the language I want to use. Let's multiply both sides of that equation by 1/5. When I do that, the 5 on the left-hand side multiplied by the 1/5 will just become a 1. And the left-hand side will become 1y, or just y. The right-hand side of the equation now is a little more complicated looking. It's 1/5 times the quantity negative 10x plus 12. Now I need to simplify that a little bit. So how am I going to do that? I'm going to distribute the 1/5 into the parentheses, which means I'm going to multiply the 1/5 with the negative 10x, and I'm going to multiply the 1/5 with the 12. And when I do that, my equation is going to become y equals 1/5 times negative 10x plus 1/5 times 12. Again, I've used the distributive property in order to do that. And now let's simplify a little bit. The 1/5 times the negative 10, well, it's definitely going to be negative because I'm multiplying a positive 1/5 times a negative 10. So it's going to have to be a negative 10 times 1/5. I could do a little bit of cancellation between the 10 and the 5, and I'll be left with exactly 2 over 1, or 2. But don't forget the negative sign, and so I'm going to have y equals negative 2x plus 1/5 times 12. Well, 1/5 times 12 is just not going to simplify very well, except that I can write it as one fraction, just squeeze it together, and make it 12 divided by 5. And once I've done that, I have my second equation that we started with written in a new form. It's written in slope-intercept form as y equals negative 2x plus 12 over 5. Now I need to notice something. I have two equations now. Both of them have been written in slope-intercept form. They both have the same slope, negative 2. But their y-intercepts are different. One of them is at 7, and one of them is at 12/5. With that information, can we decide whether the two lines are parallel? The answer is yes, we can. They are indeed parallel. They both have the same slope, but they have different y-intercepts, so they won't ever cross one another. They'll just be parallel lines. Well, let's do another example, a similar kind of example, except that now I want to find the equation of a second line, which is parallel to one that I've already been given. So here's the problem. Find the equation of the line that passes through the point 6, 4 and is parallel to y equals negative 3x plus 5. So I already know one of the lines, it's y equals negative 3x plus 5, but now I want the parallel line to that one, which goes through 6, 4. Well, the equation for this new line that's going to go through 6, 4 needs to be in slope-intercept form. If I can pull that off, thankfully, the one I was given is in slope-intercept form. It's y equals mx plus b, or y equals negative 3x plus 5. We saw that slope-intercept form back in lesson 10. So I know the slope of the line that was given to me. It's got slope negative 3. The new line then also needs to have slope negative 3. Fabulous. But how am I going to use that information to my advantage to find the equation of the new line? Well, you know the slope of the new line, and you know a point that it's supposed to go through. That was the point 6, 4. What do you think you can use then to write down the equation of this new line? The answer is the point-slope form of the equation. Great. So let's use the point-slope form. Let me remind you of what it was. The point-slope form said, if you know a point, x1, y1, and you know the slope of the line, then the equation of the line is going to be y minus y1 equals m, that's the slope, times x minus x1. And that means, in this case, with slope negative 3 and a point 6, 4, the equation of this new line is going to be y minus 4 equals negative 3 times the quantity x minus 6. Now let's simplify that just a little bit. That's going to be y minus 4 equals negative 3 times x plus negative 3 times negative 6. I've got to go ahead and do that distribution again of the negative 3. And if I simplify that a little bit, I'm going to have y minus 4 equals negative 3x plus 18. Now I'd like to write that in slope-intercept form if I can. And if you stare at it for just a second, it's very close to slope-intercept form already. In fact, the only thing that needs to be moved is that minus 4. How do I get rid of a minus 4 on the left of that equation? I add 4 to both sides of the equation. When I add 4 to the left, I get y minus 4 plus 4, which is y minus 0, which is y. And the right-hand side becomes negative 3x plus 18 plus 4. Remember, if you're going to add 4 to the left, you've got to add 4 to the right. Well, 18 plus 4 is 22, and so my equation comes down to y equals negative 3x plus 22. Now, does that equation look like the equation of a line that's parallel to the equation we began with? Yes, they have the same slope, but they have different y-intercepts. Well, I'd like to look at one more problem on parallel lines in this lesson, and this time it's going to be a word problem. So let me walk you through the words of the problem before we jump into the actual algebra. So a construction company has been tasked with building a new road, which is to be parallel to Main Street in your downtown. A graph of the current street has already been plotted out in the Cartesian plane and given to the construction company. Now, in this graph, each horizontal step of length 1 represents 1 mile, so that if you went from the point 2, 0 to 3, 0, you would travel exactly 1 mile in that direction. And that's the same as moving from, say, the point 5,1 to the point 6,1. Each unit left to right is exactly 1 mile. The new road is supposed to be built 2 miles east of Main Street to avoid some of the buildings that are directly east of Main Street. You don't want your roads running right through the buildings. So I want the equation of the line that is going to be the line for the new road 2 miles east of Main Street. Well, There's a lot to digest in those words, but we can handle it. Let's just read through it a little bit at a time and pull out what it is we can find. So let's start by figuring out what we need. Well, we've been asked for the equation of a new line, which is going to represent this new road. No problem. If I need the equation of a line, what do I have to find? That's right, I'm going to need a slope, and I'm also going to need a point that the line goes through, and I'm going to have to keep one other thing in mind. These two lines are supposed to be parallel, which means the slopes of the two lines have to be equal to one another. Okay, so let's move forward from there, and let's see what it is we want to do. What is the slope of Main Street on this grid? Well, thanks to the grid, it's pretty easy to figure that out just by using rise over run. Let's pick out 2 points on the line which are kind of convenient to us, and then let's figure out the slope. So staring at this graph for just a moment, do we see any points on the line where the line actually goes through the grid points? Well, yes we do. In fact, we see that the line goes through 0, -3. That is the y-intercept, by the way. And it also goes through the point 2, 1. So we now have 2 points through which that line already runs. That means the slope of that line is the following. It's 1 minus -3 divided by 2 minus 0. And that's the same as 1 plus 3 divided by 2, which is 4 divided by 2, which is 2. And what does that mean? It means that the slope of the first line was 2, and it means the slope of our new line needs to be 2 as well. So we now know the slope of the new line is going to be 2. Remember, the new line is for the new road that the construction company needs to build. Well, from there I can use the point slope formula to determine the equation of this new line, but I need a point on the line. So let's go back to the problem now and ask ourselves, where is this line supposed to go? Well, it's supposed to go 2 miles to the east of Main Street. Notice, for example, that the point 2, 1 is on Main Street, and that means if I go 2 units to the right from there, I'll be on the point 4, 1 on the new road. Well, that means then I know everything I need to write down the equation of the line that represents this new road. It's going to go through the point 4, 1, and it's going to have slope 2, because the slope of the line for Main Street was 2. And therefore, with the 4, 1 point and the slope of 2, I can use the point slope form of a line to write down the equation. It's going to be y minus 1 equals 2 times x minus 4. Now let's simplify that just a bit to get it in slope-intercept form. Y minus 1 equals 2 times x minus 4 is the same as y minus 1 equals 2x minus 8. The 8 comes from the 2 times 4. So I have y minus 1 equals 2x minus 8, and if I just add 1 to both sides of the equation, y will be by itself on the left, because minus 1 plus 1 is 0, and on the right I'll have 2x minus 8 plus 1. And minus 8 plus 1 is minus 7. So I have y equals 2x minus 7. We see that this is the correct equation if we just plot the line for Main Street, which was already given to us, and we plot the line for this new road, and we do so on the same set of axes. And if you look at that, you'll see that you've got 2 parallel lines, and the construction company now knows where to put this road based on that grid. Now, I'd like to transition to the concept of perpendicular lines now as we continue in this lesson. Perpendicular lines are also a very special type of line. And so the first thing we want to do is ask, well, what does it mean for 2 lines to be perpendicular to one another? Well, from a graph perspective, it means that the lines intersect at right angles. So they're going to make a symbol like this when they intersect. That's what it means to be perpendicular. But how do you notice when 2 lines are perpendicular if all you have are the equations? In other words, they didn't give you the drawings for the lines, they just give you the equations that tell you what the lines are. Well, it turns out from an algebra perspective, we can figure that out once we know the equations. And here's the property that we need to remember about perpendicular lines. Two lines are perpendicular if the product of their slopes is -1. Now, do you remember what product means? The product is the multiplication of the two numbers. So when we say two lines are perpendicular, if the product of their slopes is -1, it means that two lines are perpendicular if the slope of one of the lines times the slope of the other line is exactly equal to -1. The sort of fancy mathematical way of saying that is this: the slope of one of the lines must be the negative reciprocal of the other slope of the other line. So that's a big phrase. Let me just give you some small examples. 3 and -1/3 are negative reciprocals of one another. Notice that one of them is positive and the other one's negative, and 3 and 1/3 are reciprocals of one another. 5 and -1/5, they are also negative reciprocals of one another. And lastly, 2/3 and -3/2, they're also negative reciprocals of one another. Notice that one of them is positive, the other one is negative, and 2/3 and 3/2 are reciprocals of one another. So, for example, the lines given by these two equations are perpendicular. Y equals 2x plus 3 and y equals -1/2 x plus 5. Look at the product of their slopes. The product of their slopes is 2 times -1/2. And 2 times -1/2 is going to be -1 once you cancel those 2's. Notice that 2 over 1 and -1/2 are negative reciprocals of one another. If you quickly sketch a graph of those two equations, you'll see this perpendicular nature of the two lines. They're going to cross at 90-degree angles. Similarly, if you had the lines given by the equations y equals 4/7 x minus 3 and y equals -7/4 x plus 8, those two lines would also be perpendicular to one another. Their slopes, using the equations, are exactly 4/7 and -7/4. I know that because the two equations were already written in slope-intercept form. Those two slopes are negative reciprocals of one another. They're clearly reciprocals if you ignore the negative sign, and one of them is positive and one of them is negative. So I'm definitely going to have two negative reciprocal slopes when I have 4/7 and -7/4. And again, if you just draw a quick sketch of those two lines, you'll see that they are indeed perpendicular. Might I point out very quickly, if you think about it for a second, if you have two perpendicular lines, one of them is going to have positive slope, and the other one is going to have negative slope, so that they actually cross at 90-degree angles. So you have to have one of them being positive and the other one being negative in order to have perpendicular lines. Remember, that's very different from parallel lines, where the two slopes actually had to be the same in order to get the parallel line pair. So here, with perpendicular lines, I'm going to need one positive slope and I'm going to need one negative slope so that the two will cross correctly. Now, I can use this kind of information to obtain equations of lines which are described to us in terms of being perpendicular to one another if I just think through how to handle the negative reciprocal for the slope. So let's look at an example where we would have to do that kind of a thing. Let's find the equation of the line which is perpendicular to the line given by y equals 2/3 x minus 1, so that the new line has y-intercept 0, 4. Now, we've been given the y-intercept of the new line, so the slope-intercept form of the line should be very straightforward to write down. In fact, we know that the equation must be y equals mx plus 4, since the y-intercept was given to us as 0, 4. So the new line, which is supposed to be perpendicular to that other line, must have an equation of the form y equals mx plus 4. Remember that that m is the slope of this new line. Well, What is the slope of that new line? It has to be the negative reciprocal of the slope of the line that was given to us. Well, what was the slope of the line given to us? It was 2/3. So the slope of this new line must be the negative reciprocal of 2/3. And the negative reciprocal of 2/3 is -3/2. So the equation of this new line must be y equals -3/2x plus 4. And that line is pretty straightforward to draw. It's got a y-intercept at +4, and it has this slope of -3/2. And if you sketch those two lines, which would be very wise in order to check your work, you'll see that the two lines go exactly where they're supposed to go, and that they're clearly perpendicular to one another once you've drawn them. Well, let's look at another example about these perpendicular lines very, very quickly and see how things work out. Here's the example. Are the lines given by the equations y equals 4/5 x plus 2 and y equals 5/4 x minus 1 perpendicular? Y equals 4/5 x plus 2 and y equals 5/4 x minus 1. Well, if you stop and think about it for just a second, we can actually answer this question very quickly. Notice that the two slopes are positive, 4/5 and 5/4. So they're both positive. They're kind of small. 4/5 and 5/4 aren't very big numbers. But since they're both positive, they can't be perpendicular to one another because the slopes have to be negative reciprocals of one another. I see that they're both reciprocals, 4/5 and 5/4, but one of them has to be negative and one of them has to be positive. So don't fall into that trap of thinking, well, I saw 4/5 and I saw 5/4. The two lines must be perpendicular. One must be negative in terms of slope and the other must be positive in terms of slope. So these two guys are not perpendicular. Let me say it a different way. If the slopes are both positive, 4/5 and 5/4, then the two lines are actually going to both go in this direction. One of them might be like this, and the other one might be like this, for example, a little more steep because they have different slopes, but they're both going up. They're both increasing because both slopes are positive. If that's true, then they can't be perpendicular because, again, one must be going up like this and the other must be going down. Well, let's move on then to a word problem that talks about perpendicular lines with the goal of trying to see how we can incorporate perpendicular lines with one of these real world or word type problems. So in the graph that's given to you, the line represents a street in front of a house where the house is being built. The point on the y-axis represents the location of the front door of the house. That point is not on the line, notice, but that's the point where the front door of the house is going to be located. The owner of the home wants to have a sidewalk built coming out of the front door, which is perpendicular to the street. So the question is, based on this grid, what is the equation of the line that will represent that sidewalk? And again, that sidewalk needs to be perpendicular to the street. Okay, let's first figure out the slope of the line representing the street. Of course, if we figure out the slope of the line representing the street, we'll know some information about the slope of the line representing the sidewalk. I want you to note that we don't need the full equation of the line representing the street. I only need its slope, so I'm not interested in its y-intercept. I could probably find it very quickly, but I don't need it. I just need the slope. So let's get 2 points off of that line, which is representing the street, and let's find the slope of that line. Well, the y-intercept is there, 0, 5. You can see that pretty quickly. And another point that goes through the grid marks pretty nicely is the point 2, -1. You see how that one also goes through that grid line set pretty nicely. With those 2 points in hand, I can get the slope of the street. So the slope of the street is going to be 5 minus -1 divided by 0 minus 2. We've been doing this a lot, haven't we? But it's good to make sure we're careful about it as we walk through these calculations. 5 minus negative 1 is the same as 5 plus 1, which is 6. And of course, 0 minus 2 is negative 2. So you have 6 over negative 2, which is negative 3. Quick question, does the line that's in the graph that was given to us look like it has a negative 3 for slope? Yes, it does, because it's going down in this direction. Now, with the slope of that line given to us now, well, it wasn't given to us, we calculated it ourselves, we can now calculate the slope of the sidewalk line. It has to be perpendicular, the sidewalk has to be perpendicular to the street, so the slope of the sidewalk line has to be the negative reciprocal of the slope of the street. The slope of the street is negative 3, and so the slope of the sidewalk is going to be positive, remember it has to be a different sign, and it has to be the reciprocal of 3. What is the reciprocal of 3? It's 1/3. And therefore, the slope of the sidewalk line is going to be positive 1/3. Now, what are the coordinates of the point through which the sidewalk line is supposed to go? Well, that was the little point down on the y-axis there, 0, negative 4. Well, I have a point on the line, and I now know its slope, so I can now calculate the equation of the line that represents the sidewalk. Let's write it down very quickly. It's going to be, using the point slope form, y minus negative 4 equals 1/3 times x minus 0. Or y plus 4 equals 1/3 x, which is the same as y equals 1/3 x minus 4. In fact, it might have been easier just to use the slope-intercept form if you think about it, since 0, negative 4 was the y-intercept of that line. And if you plot both of these lines now on the same set of axes, you'll actually see that you do get perpendicular lines. The sidewalk and the street really will be perpendicular with one another. Well, we've spent several lessons now talking about linear equations. We've talked about slope. We've talked about its importance and how to interpret it. We've talked about the slope-intercept form of the equation of a line and the point-slope form of the equation of a line. We've talked about graphs of lines in general and the special types of lines called parallel and perpendicular. As best you can, you'll want to get comfortable with these parallel and perpendicular lines as we continue through this course together. Next time, we're going to shift gears a bit from the graphical side of linear equations, and we're going to start talking about how linear equations can be used to solve word problems. And I'll see you then. Mathematical facts and equations can be represented in a wide variety of ways. You might use a picture or a graph, for example, to describe a mathematical relationship. Or you might write down a table of facts or values to demonstrate the relationship to someone. Or you could give the algebraic relationship with an equation between the variables in question. All of these approaches are valid, and it's very important that we have the ability to use all of them and to understand how to interpret what each of these representations tells us. You never know what kind of information you'll be handed when starting a problem. So being able to work from a graph, or from a table, or from an equation will be very important. In previous lessons, we spent a good bit of time going between equations of lines and graphs of lines. I'd like to focus on some different material now as we go into this lesson. In particular, I want us to consider how to use tables of data to represent linear equations. And I'd like to see how to go from tables to either equations or to graphs of linear equations. This is very important as we move into trying to understand real-world examples that involve linear equations. So let's start by talking about how a linear equation can be summarized with a table of values. Let's determine whether the following table of data describes a linear equation or some other type of equation. You never know when the data is handed to you whether it's linear or not. So let's march through trying to understand whether the data is linear. Here's our table. The x value 0 has a corresponding y value of 5. So 0, 5 is one of the points of data. X is 1, y is 8. When x is 2, y is 11. When x is 3, y is 14. When x is 4, y is 17. And when x is 5, y is 20. So that's our table of data. And now I want to know, are those points basically on a line, or do those points satisfy a linear equation or a linear relationship? Well, notice that the amount of change of the y values in the table is constant. It's the same throughout the table. That is, as each x value increases by 1, as you read down the list, the y values increase exactly by +3. So I should be clear here. When I say the y values increase by +3, I mean we add 3 to each y value to get to the next y value. So, since we add the same amount to the y values every time the x value grows by 1 unit, we know that this table represents a linear equation. So let me just make sure that I'm understood here. When I say we add 3 each time, I mean the following. To go from the 11 to the 14, I've added 3. To go from the 14 to the 17, I've also added 3. And to go from the 17 to the 20, for example, I've added 3. Now, we assume that the same pattern will hold if the x values get larger. Like if you looked at x equals 7, or x equals 8, or x equals 9, or even x equals 100. And we also make the same assumption if the x's get smaller, like if we had x equals -1, or -2, or -3. But this is a drawback for using a table to describe an equation. Why is that? Because you can't write down all the information about the equation in one table. So when you're handed a table, you have to make certain assumptions about what's going to happen to the data which is outside of the table. So that's one comment to make about this table. The second comment to make about the table is this. That common amount that we're adding to each y value, +3, which is giving us the next y value, that's actually the slope of the line in this example. So the slope of the line really is 3. Well, what would we have done if the x values had not just grown by 1? We actually kind of had it easy on ourselves since the x values just went 0, 1, 2, 3, 4, 5. Well, that would definitely complicate matters if the x values grew in a less nice pattern, but we can handle that later. In fact, we'll talk about it in a later example in this lesson. Let me also point out that we can actually write down the equation of the line that gives this table of data. How? Well, the slope of the line is 3, as we've already said. Notice also that the y-intercept was given to us. The first point in the table is 0 for x and y for y is 5. 0, 5. That's the y-intercept. If the slope is 3 and the y-intercept is 5, then the slope-intercept form of the equation of this line is y equals 3x plus 5. And from the table of data, we've now figured out the equation of this line. Now you might say to me, I'm not sure you got that right. Well, let's try plugging in one more point in the table to see if it actually works. The equation is y equals 3x plus 5. Let's use the point 4, 17 and see if that point really is on the line y equals 3x plus 5. Well, x is 4, so 3 times x plus 5 would be 3 times 4 plus 5, which is 12 plus 5, which is 17. And that's the y value. So indeed, those pieces of data from the table actually do all live on the line y equals 3x plus 5. Okay, so let's look at another example where data comes into play, where we have a table of data and we're trying to figure out, does that table of data represent a linear equation or maybe some other kind of equation? So here's the table of data that we now have. When x is 0, y is 1. When x is 1, y is 6. When x is 2, y is 11. When x is 4, y is 21. And when x is 7, y is 36. A nice set of data. Now when you look at those pieces of data for just a second, and I ask you, do those represent a linear equation? My guess is that many of you would first say, no way. And the reason you would say that is because the y values are not increasing by the same amount. I see the 1 and then the 6, and that needed a 5 to make the increase. And then 11 minus 6 is also 5, so I needed a 5 to add to make that increase. But then when I look at the next piece of data in the table, I see that I've grown from 11 to 21 in the y. 21 minus 11 is 10. That's not 5. And if I look at the next piece of data, it's even worse. 36 minus 21 is 15. So it looks like the y values are growing kind of sporadically, and therefore I don't have a linear equation. I can understand you saying that, but I want to slow you down before you make that your final answer. Notice that the x values are also not growing at the same amount. Do you see how they go 0, 1, 2, 4, 7? They're not growing like the previous example that just grew one at a time in the x's. That's a very important key in this example. So let's now go back to the table for a moment and look more carefully at the data that's been given to us. First, we see that when the x value goes from 0 to 1, the y value goes from 1 to 6. That's a change of 5 in the y value, right? 6 minus 1 is 5. The same is true when the x goes from 1 to 2. So if the table is representing a linear equation, it must be the case that an increase of 1 in the x value corresponds to an increase of 5 in the y value. By the way, think about how that goes towards rise over run. Now, let's see what happens when x changes from 2 to 4. Well, when x goes from 2 to 3, the y value would have to grow by 5. And then when it went from 3 to 4, it would have to grow by 5 again. So when x goes from 2 to 4, the y value needs to grow by 10, or 5 plus 5. Is that what happens? Yes, that's exactly what happens. When x is 2, y is 11. And when x is 4, y is 21. And 21 minus 11 is 10. So in fact, we're still on track for this table to represent a linear equation. Let's look at the last pair of points then. X equals 4, y equals 21. And x equals 7, y equals 36, to see if this same relationship holds. Now, in the case when x is 4 and we move from 4 to 7, the difference in the x values is 3. 7 minus 4 is 3. So the growth in the y values then would need to be 5 plus 5 plus 5. Why? Because we want to go from x equals 4 to x equals 5, and then to x equals 6, and then to x equals 7. So I actually need to make sort of 3 jumps. And each of those needs to grow by 5. And 5 plus 5 plus 5 is the same as 3 times 5, which is 15. Is the change in the y's equal to 15 at that point? Well, when x is 7, y is 36. When x is 4, y is 21. 36 minus 21 is 15. And that was exactly what we needed the jump to be, from 21 up to 36. And therefore, guess what? This table really does represent a linear equation. And it turns out that the linear equation is y equals 5x plus 1. Well, we know this is true because the slope of the line is 5. That's what all those calculations we just did told us. Every time we moved 1 over in the x direction, we had to go up 5. And the y-intercept is clearly 0, 1 from the table that was given to us. And therefore, the y-intercept value, b if you will, is 1. So my equation must be 5x plus 1. Well, let's look at another example of this type just for a moment. Another table of information, table of data, and let's see if this table represents a linear equation. Here's the table. We're going to have 0 for x and 1 for y. That's going to be 1 point. Then we'll have 1 for x and 2 for y. And then the next point will be 2, 5. The next point will be 3, 10. And the last point will be 4, 17. In other words, when x is 4, y is 17. Now, for this table to represent a linear equation, I know that the slope between any 2 points we choose must be the same amount. In other words, if all of these points live on one line, then no matter which 2 points I choose on the line, the slope between those 2 points must be the same. This is true of all linear equations. So here's what I'm going to do. I'm going to take my table of values and I'm just going to start picking a couple of points and I'm going to ask what's the slope between those 2 points. And if this table represents a linear equation, then all of those slopes will be the same. So let's start with the slope between the points 0, 1 and 1, 2. Those were the 2 pieces of data at the beginning of the table. The slope in that case is going to be y2 minus y1 over x2 minus x1, or 2 minus 1 over 1 minus 0. 2 minus 1 is 1, 1 minus 0 is 1. That's 1 over 1. And therefore, my slope is just 1. And that means the slope between any other 2 points that I pick from my table must also be 1 if this table represents a linear equation. So let's pick the next pair of points. How about when x is 1, y is 2, and when x is 2, y is 5? We could choose lots of pairs. We could choose when x is 2, y is 5, and x is 4, y is 17. But I'm just going to use 1, 2, and 2, 5 for this example. Well, what's the slope between 1, 2 and 2, 5? Well, I go back to my slope formula for m, y2 minus y1 over x2 minus x1. And in that case, my slope is 5 minus 2, that's the difference in the y's, divided by 2 minus 1, that's the difference in the x's. 5 minus 2 is 3, 2 minus 1 is 1, 3 divided by 1 is 3. And now, if you remember what we just did a few moments ago with this example, we have a problem. Notice that the slope between 0, 1 and 1, 2 was exactly 1. Remember we did that calculation a few moments ago. But the slope between 1, 2 and 2, 5 is 3. And that's different from 1. What does that mean? It means that the table that we were given in this example is not representing a linear equation. Think about it. From 0 to 1, the slope might be 1 like this, but then from 1 up to 2 for x, the slope is getting higher. So the graph must be going like this, and then it must be going something like this. And that definitely can't be the slope of a straight line. It can't be the graph of a straight line. It feels like it's curving somewhere in between. Let me share a few thoughts here about this example, though, before we move on to other things. First off, it turns out that the points that I gave you in this table all satisfy a certain equation. I kind of know what that equation was already. I was the one who made the table. But it turns out that they satisfy that equation, y equals x squared plus 1. Y equals x to the second power plus 1. That's not the equation of a line because of that power of 2 on the x. Remember, a linear equation has a power of 1 on the x. So it's going to be something like y equals x to the 1 plus something, or y equals 7 times x to the 1 plus another number. So that power of 2 in the equation y equals x squared plus 1 would actually tell us that this data cannot satisfy a linear equation. So if we'd have had that equation, we could have finished this problem a long time ago. But that's the helpful thing about algebra. The equations can tell us a lot. The fact of the matter is that without the equation, all we had was the data. And that's pretty real world. Sometimes all you can do is get data and tables of numbers, and you have to figure out what's going on from there. So if we had the equation, it could have told us immediately that this was not data from a straight line. Well, there's another way we could have known that it wasn't going to be data for a straight line. What if we had just drawn the graph? Well, what does the graph look like for something like y equals x squared plus 1? Well, in fact, it sort of looks like a bowl or a cup. It's called a parabola. We'll talk about parabolas in future lessons, so you don't need to know that term right now. But the point is, if we had had the graph and we had seen that the graph made this curved shape that looks like a bowl or a cup, we would have known immediately that we would not have been staring at a linear equation. We would have been staring at something else. Now, I'd like to transition to a slightly more real-world type of problem that can come up when you're looking at data. So here's the word problem, and I'll walk us through it as we go. A scientist measures the circumference of a certain tree. So she's measuring the outside distance of this tree as it grows over a period of 4 years. And the data she collects can be found here. Now here's a table which is going to look a bit complicated compared to some of the other tables we've seen, but it's not a problem. The x values are in years, and the x values are going to be 0, 1, 2, 3, 4. These are the years that she's taking her measurements. So x equals 0, think of it as the first time she made the measurement. So it's like the beginning of the experiment. X equals 1 then would be her measurement after 1 year from the beginning. X equals 4 would be a measurement exactly 4 years after she started. The y values, which are corresponding, are going to be in centimeters, and they are going to be 45.72 when she began at x equals 0. When x is 1, it's 60.96. When x is 2, we have 76.20 centimeters. When x is 3, 91.44 centimeters. And when x is 4, the y value, which is this circumference of the tree trunk, is 106.68 centimeters. So this tree has been growing as the years have gone by. And here's the question. Does the tree's circumference appear to be growing in a linear fashion? And if it is, use that information to predict the circumference of the tree in year 10. Okay, the first thing you might do is say, oh my word, there's no way I want to try this problem. Look at all those decimal numbers. How in the world am I going to figure out whether this data follows a linear equation? Well, you shouldn't jump into it that negatively. We can really handle this by just checking the slopes as we go from one point to the next. If we can show that the slopes between any two pairs of points are the same, then we'll know that all of these points live on one line. So that'll be the first part of this problem. So let's take the pairs of points, just two at a time in the table, and let's calculate the slopes. Let's start with the first 2 points. The first point is 0, 45.72, and the second one is 1, 60.96. Do the slopes. The slope of that is going to be 60.96 minus 45.72 divided by 1 minus 0. Now, to do that difference in the numerator, you might actually need to write the numbers in a vertical way. That's how I like to write numbers in decimal form when I need to add or subtract them, and then line up those decimal points and do the subtraction. When you do that, the numerator is going to become 15.24. The denominator, that's the easy part, is 1 minus 0, which is 1. So the slope between those 2 points is 15.24 divided by 1, which is just 15.24. Now, the slopes between every other pair of points then must be 15.24 if all of this data is actually living on the same line. So let's now try the second pair of points and see if the slope is 15.24. Well, those points are 1, 60.96 and 2, 76.20. So the slope is going to be 76.20 minus 60.96 divided by 2 minus 1. And again, the denominator is really friendly. 2 minus 1 is just 1. I can do that. What's the numerator? Again, you might need to write the numbers vertically. 76.20 minus 60.96. Line up those decimal points. When you do that, that difference is going to be 15.24. Hey, divided by 1, that's 15.24. And that's a great sign. It means that the slopes, at least between the first two pairs of points, are the same. So those 3 points are definitely living on a straight line. But you know, it could be the case that the tree grows in a sort of linear fashion like that, and then all of a sudden it has a growth spurt and it starts to grow really, really fast. So we can't determine yet that we're on a straight line until we check all the other points. So let me do that pretty quickly. Let's take the slope between 2, 76.20 and 3, 91.44. When I do that, I need to do the change in y's divided by the change in x's. That's going to be 91.44 minus 76.20 divided by 3 minus 2. Notice the way the table's working here. All the denominators are 1, which is really friendly. And 91.44 divided by, or 91.4 minus 76.20 is 15.24. When I divide that by 1, I get 15.24. This is a great sign, but it doesn't mean we're done yet. So let's check the last slope between that last pair of points. 3, 91.44 and 4, 106.68. When I do my difference of y's on the top, I'm going to have 106.68 minus 91.44. I'm going to divide that by my difference in the x's, which is 4 minus 3. And I will have, when I do those differences, 15.24 divided by 1, which is 15.24. Guess what? All of these points live on the same line. So indeed, this table, which looked kind of messy at first, really turns out to contain a whole bunch of points on one line. Now here's the question. If you want the equation of that line, you need the slope, and if you can get it, the y-intercept. Well, what's the slope? Well, you just calculated it 4 times. It's 15.24. So there's m, 15.24. What's the y-intercept? Go back to your data. The y-intercept needs to be the point where the x value is 0. Remember, the y-intercept lives on the y-axis for the graph, and if you're on the y-axis, your x value must be 0. So your y-intercept is right in front of you. It's 0, 45.72. And therefore, equipped with the slope and the y-intercept, you know that the equation of the line in slope-intercept form is y equals 15.24x plus 45.72. Now, you could actually sketch the graph of this line, and if you do so on a piece of graph paper, it might be a little complicated because you're not exactly sure how to make all those grid lines in terms of their units. I mean, 15.24 and 45.72 might be a little hard to figure out. But if you sketched it, maybe on a calculator or a computer, one such sketch would look like the following. Now, notice that that line has positive slope, 15.24, and that works out well, and it also goes through the right y-intercept. You could also plot all the individual points in the table to make sure they live on that line, and everything would work. So you started with a problem that you might have been real scared about. In fact, you figured out that equation with relative ease. Now, the problem was actually 2 problems, if you remember. We were told that if the data satisfied a linear equation, that we wanted to use that equation to figure out the circumference of this tree in year 10. So now that I know the equation, I can actually figure out this prediction. What's going to happen? I'm going to take my equation, y equals 15.24x plus 45.72. Year 10 is an x value, and so I'm going to plug in 10 for x into that equation and simplify to find y. Remember, y was telling me the circumference of the tree in centimeters. So my equation was y equals 15.24x plus 45.72. Plugging in 10 for x gives me y equals 15.24 times 10 plus 45.72. And that's y equals 152.4 plus 45.72. Remember, when you multiply a decimal by 10, it just moves the decimal point to the right 1 unit. And when you add 152.4 to 45.72, you get y equals 198.12. Remember to add those. It's probably good to write them in that vertical notation. Life will work out real well for you. Now, we've predicted then, using our equation, that the tree is going to be 198.12 centimeters around its circumference in year 10. It would probably be wise to take our graph and see if that point, 10, 198.12, is actually on the graph. If you do so, you'll find that it really is. Now, let me give you a few comments about the example we just did before we leave it. First, the fact that this data was exactly linear is, okay, probably not completely realistic. I mean, trees don't grow that precisely, and there's probably a bit of human error involved in taking the measurement around this tree. So I know that in a real world, we might see a trend towards linear growth, but we probably would not have seen these exact values. So I'm willing to admit that. On the other hand, it was still good to see how these decimal numbers could actually fit along a linear equation on the graph of a line. Secondly, what if I had asked you to use that same equation to predict the circumference of this tree in year 1000? Now, of course, this scientist is probably not going to be around for 1,000 years, but she could keep handing it down to later scientists and so on. If we use that equation, y equals 15.24x plus 45.72, and we replace x by 1,000 and simplify, you're going to get y equals 15.24 times 1,000 plus 45.72, which is 15,240 plus 45.72, which is 15,285.72 centimeters. That translates to a circumference of over 500 feet. And currently the world record is just under 200 feet for a tree's circumference. So did we do some mathematics incorrectly? No, not really. The issue here would really be our assumptions. To assume that that tree is just going to keep growing at the same rate over the next 1,000 years is faulty. There are lots of reasons that trees and lots of other things don't just keep growing at the same rate. Drought, insect attack or disease, old age, you name it. This tree is hard to imagine that it will grow the same way for 1,000 years. So, what's the point? When we want to use mathematics to help predict the future, we should be wise as to how far out in the future we try to predict. The uncertainties of the future are exactly why the weatherman usually can't tell you accurate predictions about the temperature or rainfall for much more than a few days into the future. So be very careful when you're using mathematics to try to actually predict what's going to go on well into the future. Well, we've begun to think a bit about looking at word problems and how real-world situations can be looked at via linear equations. I want to continue to look at these kinds of themes in our future lessons together. I'll see you then. We've talked a bit in previous lessons about ways that linear equations appear in real-world problems and word problems of various sorts. In today's lesson, I'd like to continue down that path and consider various examples where real-world data comes into play. In the process, we'll once again return to this theme of understanding multiple representations of linear equations, whether it's tables of data, or graphs, or algebraic rules. One way in which linear equations arise naturally in the real world is in the conversion of units from one system to another. Things like converting from inches to centimeters or miles to kilometers, things like that. I'd like us to look at an example involving temperature conversions today. So, here's a table of values of temperatures in degrees Fahrenheit and degrees Celsius. And what I'd like to do is find a linear equation which relates the degrees Fahrenheit to degrees Celsius. So let's look at the table for just a moment and make sure we understand what the table is telling us. First of all, we notice that when the degrees Fahrenheit is 32, then we have 0 degrees Celsius. In other words, when F is 32, C is 0. I want you to notice here that I'm using F and C as opposed to X and Y. It's okay to have that. We're just changing the variables so I can remember which one is Fahrenheit and which one is Celsius. So when F is 32, C is 0. When F is 50, C is 10. When F is 77, C is 25. And when F, or the degrees Fahrenheit, is 212, C, or degrees Celsius, is 100. So basically we have 4 ordered pairs here: 32, 0, 50, 10, 77, 25, and 212, 100. Now, the problem doesn't say this explicitly, but I want us to find a formula where F is being treated as the independent variable, like X, like the number you plug into the formula, and C is being treated like the dependent variable, like Y in most cases, where Y is what comes out at the end. We could also find a formula which does the exact opposite, where we treat C as the independent variable, or the variable you plug in, and we treat F as the dependent variable, the one that comes out. But that's another problem. So let's only do one problem with this example. Let's find this formula now where F is treated as the independent variable and C is treated as the dependent one. So let's start, first of all, by finding the slope of the line. Now, you might stop and say, well, how in the world do you know that this data is really going to fit on a line? Well, we could check all the possible pairs to confirm that the data really all fits on one line by checking all the slopes and making sure they're the same. But for the sake of time in this lesson, let me just promise you that they really all do fit on a line and that the slopes really will all be the same. If you'd like to check those later, you certainly can. Well, if we know they're all on a line, then it means we just really need 2 points to find the slope. So I'm going to suggest we use basically the first 2 points in the table, and they are 32, 0 and 50, 10. Notice that I have the 32 in the first position in the ordered pair and the 0 in the second position of the ordered pair. Again, the degrees Fahrenheit is acting like the X, and the degrees Celsius is acting like the Y. Well, then I can calculate my slope using those 2 points just by doing y2 minus y1 over x2 minus x1. Except we're not using x's and y's. So it's going to be something like the difference in the degrees Celsius divided by the difference in the degrees Fahrenheit. We can still handle it though. And that slope is going to be 10 minus 0 divided by 50 minus 32. And now we need to simplify that fraction. 10 minus 0, that's straightforward, that's just 10. 50 minus 32 is 18. And so our slope is 10 divided by 18. However, that's definitely not in reduced terms because the 10 and the 18 are both even, so I can factor a 2 out of both and cancel those 2's, and I'll be left with 5 divided by 9. That's in reduced form. So my slope of the line in this example is going to be 5 divided by 9, or 5/9. Well, next I just need 1 point, and I can use the point-slope form of the equation of the line to find the equation we want. You can pick any of the points that are in the table. I'm simply going to pick 32, 0 as my point. Let me give you a quick hint. By choosing 32, 0, I'm going to make my arithmetic a little easier because that 0 is not really going to do a whole lot with the arithmetic. So I choose that point somewhat carefully in order to make my work later on a little bit smaller. Then my equation of the line is going to be c minus 0 equals 5/9 times the quantity f minus 32. Remember, that's the point slope form of this line. And again, since I'm not using x's and y's, we have to be a little bit careful where we put the numbers. But notice that the 32 was a Fahrenheit reading, and it went with the f in the term f minus 32. And the 0 was a Celsius reading, and it went with the c minus 0. Now, c minus 0 is just c, so my formula looks like c equals 5/9 times f minus 32. And if you notice, that's an equation of my line. I'm actually done. I've finished that part of the example. I can plug in any value of f now, any one you choose, even one that's not on the table, and I can tell what the value of c will be. Now, if you're not satisfied with whether all the data points actually fit on the line, you could easily check by simply plugging in the coordinates of each point and confirming that the equation is satisfied. I'm not going to do that for all the points, but let's check one, just to make sure we did the work right. Let's take one of the points off of the table and see if it really satisfies the equation that we just found. So let's take the point 77, 25. Remember, 77 is a Fahrenheit reading and the 25 is a Celsius. So I'm going to plug in 77 for f and 25 for c, and I'm going to see if that equation gives me a true statement. When I plug in those values to the formula I found, I'm going to have 25 equals 5/9 times 77 minus 32. And now I need to simplify. Well, I see the 77 minus 32 in parentheses. My order of operations tells me I must do that first. And 77 minus 32 is exactly 45. Now I have 5/9 times 45, and if I factor out a 9 from that 45, it will cancel with the 9 that's in the denominator of 5/9. And what I'll be left with on the right-hand side is simply 5 times the other 5 that's coming out of the 45. I'm just going to have 5 times 5. And that means I have 25 equals 25. And that's definitely a true statement, and so we're good to go. That one point definitely lives on the line that we found. And that equation again was c equals 5/9 times f minus 32. Now, I'd like to use this information. We worked pretty hard to get that equation, so let's use it to find something else. For example, let's determine the temperature in Celsius, which would correspond to 80 degrees Fahrenheit. You might actually be somewhere today where it's 80 degrees Fahrenheit. Maybe you need to know what the temperature is in Celsius. Okay, so we'll do that in a moment. And secondly, I'd like to determine the temperature in Fahrenheit if someone tells us that it's 40 degrees Celsius. So those two problems are kind of different, but we can use the same equation to figure them both out. So let's do the first problem. To do that first problem, I simply am going to replace f by 80, and I'm going to solve it for c. Notice how nice it is now to use these letters f and c rather than x and y, because I don't have any confusion as to where the 80 is going to go. It's a temperature in Fahrenheit. It's going to go in for the variable f. So we were pretty smart in using f and c here. It makes our life simpler later on. Well, I'm going to plug in 80 for f into the equation I had. The equation I had was c equals 5/9 times f minus 32. So that's going to become c equals 5/9 times 80 minus 32. 80 minus 32 is 48. So I have c equals 5/9 times 48. Now, 9 and 48 don't have any common factors that are really going to allow me to do any reduction. So I'm just going to write 48 as 48 divided by 1, and I'm going to multiply 5/9 with 48 divided by 1. When I multiply two fractions like that, I simply multiply the numerators together and I multiply the denominators together. The numerator will then become 240. 5 times 48 is 240. And of course the denominator is just 9 because 9 times 1 is 9. And now I can actually do a little bit of simplification there. 240 divided by 9 is actually 80 over 3. Well, actually that tells me something then. The fact that I could do that simplification means there really was a little bit of cancellation that I could have done with the 9 and the 48. But notice, it's okay. We just did the cancellation here. If we had done it earlier, we would have come up with the same answer. So in fact, I could have canceled out a little bit between the 9 and 48, but it really is okay. What does that tell me now? C equals 80 over 3. It tells me that the value in Celsius for the temperature 80 degrees Fahrenheit is basically 80 over 3 degrees. Well, I've never heard a weatherman say 80 over 3 degrees in my life, but if I wrote that as a mixed number, it would be 26 and 2/3 degrees, which is basically about 26.66. It's not exact, but it's approximately 26.66 degrees. So that's my conversion. 80 degrees Fahrenheit is about 26.66 degrees Celsius. Now, there was a second problem that I mentioned a few moments ago, and that was this. What if we knew that the degrees in Celsius was 40, and I wanted to find the degrees in Fahrenheit? Well, what would we do now? Well, we're going to approach the problem in a similar way, but this time the 40 is a value for C. So I'm going to plug that in for C, and then I'm going to find F. I'm going to solve for F. We can do that. Let's go for it. The original equation was C equals 5/9 times F minus 32. We're going to plug in 40 for C, so the left-hand side becomes 40. And now I've got to get F by itself. Notice that there's only one variable now. It's the F. Everything else is a number throughout that equation. So how am I going to isolate F, or get F by itself? Well, the first thing I need to do is get rid of that 5/9 that's sitting out in front of the F minus 32. The most straightforward way to do that is to multiply that term by 9/5, the reciprocal of 5/9. Because when I multiply 5/9 times 9/5, everything will cancel and I'll just have a 1. But remember, if you multiply one side of an equation by 9/5, you must multiply the other side of the equation by 9/5 as well. So the left-hand side will become 9/5 times 40, and the right-hand side is simply going to become 1 times F minus 32. The 9/5 and the 5/9 will cancel each other out. And so your equation is 9/5 times 40 equals F minus 32. How does 9/5 clean up? I sure hope it cleans up some. Well, 40 has a 5 in it. In fact, 40 is 8 times 5. So if I cancel those 5s, I'll be left with 9 times 8 on the left-hand side, and 9 times 8 is 72. So my equation is now 72 equals F minus 32. And notice that the F is almost by itself now. What would we do to get the F by itself? Well, we need to remove that minus 32. What's the opposite of subtraction? Addition. So if I add 32 to both the left and the right-hand side, the right-hand side will simply become F. The left-hand side becomes 72 plus 32, which is 104. So let's interpret what we just found. When you have 40 degrees Celsius, or 40 degrees C, it equals 104 degrees Fahrenheit. We should quickly check that with a plot of our linear equation to make sure that point lies on the graph. So I've drawn very quickly a plot of that graph here, and we should check to make sure, at least if we can just see it somewhat generally, whether 104, 40 lies on the graph. Remember, the point really is 104, 40, not 40, 104, because we're treating the Fahrenheit values as the x values and the Celsius values as the y values. Excellent. Well, let's move on to another example, which is also related to temperature, but in a very, very different way. So here's the example. It's known that the boiling point of water depends on the altitude at which we're boiling the water. In other words, if you're down in a valley versus on top of a mountain, the actual boiling point of water, or the temperature at which the water will begin to boil, differs. It's also known that the relationship between boiling point and altitude is actually linear, so the points will live on a straight line. Given that the boiling point of water is 100 degrees Celsius at sea level and approximately 91.6 degrees Celsius at 8,000 feet above sea level, I want to know what the boiling point of water is in Denver, Colorado at Mile High Stadium. Well, this is a great question with lots of nuances, so we should start by asking the following. What is the linear relationship that describes the boiling point of water in degrees Celsius and the altitude above sea level in feet? Okay, so let's take some time to define our variables. It's always important to lay out what the variables are going to be. So let's let h be the height above sea level in feet, and let's let b be the boiling point temperature of water in degrees Celsius. What I'd like us to find is a linear equation which treats the h as the independent variable, like the x, and it treats the b as the dependent variable, like the y. Well, the first thing we need to do if we want to find the equation of a line is to find the slope. And since the b is acting like the y here, the slope is going to be change in b over change in h. So what does that give us? Well, if we use the 2 points that I gave you earlier, change in b over change in h will be 100 minus 91.6 divided by 0 minus 8,000. If you simplify that just a bit, the numerator becomes 8.4, the denominator becomes negative 8,000, and you're left with a slope of negative 0.00105. Now, just real quickly, when we draw the line later on, it means that the slope being negative is going to make us go down like this, and since the slope is pretty small and close to 0, the line will actually be pretty flat, but it does have to go down. Now, can we find an equation for the line? Well, we have 2 points, 0, 100 and 8,000, 91.6. Notice that being at sea level is the same as being at h equals 0. That's an assumption I've made there, but it's a very, very important one. And that means that the y-intercept, or I should say the b-intercept, is easy to find because we have that point given to us when h is 0. Since we have the intercept, I would suggest we just write down the slope-intercept form of the equation of this line. Here it is. b equals negative 0.00105 times h plus 100. Remember where that 100 came from? It came from that point which had 0 and 100 in it. Now, we need to use this equation to find the value of b, the boiling point, when the h, the height, is 1 mile. Mile High Stadium is called Mile High Stadium because it's 1 mile above sea level. But wait a minute, we have to be very careful of our units. This is a very important part of today's lesson. We must always watch our units. And how have we been measuring height in this example? Well, we've been doing it in feet. So we need to convert 1 mile into feet. It turns out that 1 mile is exactly 5,280 feet. So we need to use h equals 5,280 in the equation for the boiling point. And that means that the boiling point of water at 1 mile high above sea level is given by b equals negative 0.00105 times 5,280 plus 100. If you do some arithmetic there, b becomes negative 5.544 plus 100, or 94.456 degrees Celsius. Now, we should make sure that this thing actually makes sense. So let's go back to the data, the information that we had to begin with. At sea level, which was 0 feet, the boiling point is 100 degrees. At 8,000 feet above sea level, the boiling point will have dropped to 91.6 degrees Celsius. 1 mile, 5,280 feet, is somewhere between 0 and 8,000, and it's closer to the 8,000 than it is to the 0. So I would expect my answer to be somewhere between 100 degrees and 91.6 degrees, but probably closer to the 91.6 than to 100. The answer that we found, 94.456, is between 100 and 91.6, and it's a bit closer to the 91.6 than the 100. And this gives us confidence that the result that we found is in the right ballpark. Certainly, if, for example, we had found a temperature of 5,000 degrees, we would have known that we were wrong because it should have been between the temperatures that we'd already seen. Okay, let's look at another example, this time starting with a graph which models a situation, and let's see if we can go from there to solve a real-world problem. Here's the example. A child is standing at the top of a tall building and accidentally releases a helium-filled balloon, which then rises steadily above him. The graph that you see here shows the height of the balloon above the ground for several minutes. I want you to notice that the x-axis here represents the time in minutes from the moment the child lets go of the balloon, and the y-axis represents the height of the balloon in feet above the ground. I'd like us to take some time just to look at this graph and make sure we understand what it tells us before we do anything else. Remember, one of the important things I want us to constantly think about is how we represent linear equations in different ways. And one of those ways is with a graph. So let's think about what the graph actually tells us. First of all, how high off the ground was the child when he released the balloon? Well, if you think about what the graph is telling me for a second, that answer is the y-intercept. Why is that? Because at that point, 0, 100, the time is 0. And time equals 0 is the time when the child let go of the balloon. So the value of 100, which is that y-intercept, tells me that the height of the building, or the height at which the balloon was as soon as it was released, is exactly 100. So the child was on a relatively tall building when he actually let go of the balloon. Next question, what is the rate at which the balloon goes up? The balloon is taking off. We've been told that it's going at a steady rate. So if it's going to go along this straight line in terms of time versus its height, then what's going to tell us the rate at which the balloon goes up? Answer? It's the slope. That's exactly the interpretation of this line. The slope tells us the rise over the run, or the ratio of the change in the height, or y value, to the change in the time. So the slope is telling me the ratio of change in height over change in time, and that's basically telling me that the units for the slope are feet per minute. So what's the slope of the line? Well, look at the graph once again. After 2 minutes in the air, the balloon has gone from being 100 feet off the ground to 500 feet off the ground. And I want you to notice that the line goes through the point 2, 500. That's how I know that after 2 minutes, the balloon is 500 feet off the ground. And therefore, the slope must be 500 minus 100 divided by 2 minus 0, or 400 divided by 2, which is 200 feet per minute. So the balloon is moving at about 200 divided by 60, or 20 divided by 6, or 10 divided by 3 feet per second. When I divided by that 60, I went from minutes to seconds. It's going about 3 1/3 feet per second. That's not a bad pace. Now, let's look at another example where we want to involve a graph as we march through the problem together. Here's the example. Suppose an elevator starts at the top floor of a building, which is 800 feet high, and suppose it goes down at a steady rate. After 15 seconds, the elevator is 560 feet above the ground. Here's the question. How long will it take the elevator to reach the ground, or to reach the ground floor? Well, one of the biggest keys here in the language that was given to us is that the elevator is going down at a steady rate. A steady rate, or a constant rate, is mathematical jargon which tells us we're dealing with a linear equation which relates the height of the elevator to the time it takes to go down. Given that we know we'll have a linear equation, we know we just need two pieces of data, 2 points that lie on the line. So let's start by defining some variables again, which will help us draw this line and get a feeling for what's happening with the elevator. Let's let x be time in seconds, and let's let y be height above the ground in feet. So x is telling me the time that the elevator is moving, the amount of time that the elevator is moving, and y is telling me how high the elevator is above the ground. Then we were given two pieces of information, namely, when the time is 0, the elevator's at 800 feet. Remember, that's when we started running the elevator, so time equals 0. And when the time was 15, the elevator was 560 feet above the ground. These 2 points have to lie on the line. From those, I can figure out the slope, right? Let's do it very quickly. It's going to be 800 minus 560 divided by 0 minus 15, or 240 divided by negative 15, which is exactly negative 16, and in this case that's going to be feet per second. So the elevator is traveling at a rate of negative 16 feet per second. Now, we should pause. What does that negative sign actually tell me? Well, simply put, the negative sign is telling me that the elevator is going downwards. That's all it's telling me. So it's going down at a rate of 16 feet per second. Now, from there I can get an equation for the line using the slope-intercept form of the equation. Why? Because 0, 800, which is one of the points on my line, is the y-intercept of the line. And we know the slope, we just figured it out. So we can figure out the equation of the line now very straightforwardly. Y equals mx plus b is the slope-intercept form of the equation of the line, and that's going to be y equals negative 16x plus 800. Now, we could sketch that graph. Here's a sketch, and from it, we were asked to determine how long it would take for the elevator to be on the ground. Well, how high is the elevator off the ground if the elevator is on the ground? Answer, 0 feet. So what I want to know is what is the x value when y equals 0? Well, what does that mean about the graph of this line? That's exactly the x-intercept of the graph of this line, right? When y is 0, you're somewhere on the x-axis. So I'm looking for the x-intercept of this graph. Well, look at the graph. I tried to plot it carefully on some graph paper so that we could try to see where that cross is made. And in fact, if you look at the x-axis, it appears that the x-intercept happens when x equals 50. Now, let's interpret that. X equals 50 is 50 seconds. So the graph is telling us that once the elevator started going down at the very top of the building, it took exactly 50 seconds for it to reach the ground floor. Now we should confirm that with the equation very quickly. Our equation was y equals negative 16x plus 800. If I want y to equal 0, I can let that left-hand side be 0, and I'll have 0 equals negative 16x plus 800. Subtracting 800 to the left-hand side will give me negative 800 equals negative 16 times x. How do we get the x by itself? We divide both sides by negative 16, and the left-hand side will then become negative 800 divided by negative 16. Because I have two negatives there, they will cancel each other, so my final answer will be positive, and 800 divided by 16 is 50. So, indeed, x equals 50 seconds is the correct answer. Well, we've taken some time today to talk about some real-world problems and how they relate to linear equations, and we'll continue this theme as we move on to the next lesson. I'll see you then. In this lesson, we're going to talk about a new mathematical topic for you and me. It's called systems of linear equations. Now, of course, we've been dealing with linear equations already, so this isn't completely new, but the idea of a system of linear equations is new for us. These kinds of problems are going to arise very naturally because they basically deal with trying to find when two lines intersect. And knowing when two lines intersect has lots of applications. So, what in the world is a system of linear equations? Well, it's actually basic, and it is this. A set of two or more linear equations form a system of linear equations. In some ways, we want to think of the equations as linked together. And we say that an ordered pair that makes all of the equations in the system true is a solution of the system. So, let's take a quick example and just make sure we understand this idea of a solution of a system. Here's a very small system of linear equations. Y equals 2x minus 5 and y equals x minus 2. Those two equations taken as a little group forms a system of linear equations. A solution of this system is x equals 3 and y equals 1, or written as an ordered pair, simply 3, 1. Let's quickly confirm that 3, 1 really is a solution of this system. In the first equation, we substitute x equals 3, y equals 1, and we get 1 equals 2 times 3 minus 5, or 1 equals 6 minus 5, or 1 equals 1. And of course, that's a true statement. Now, we're not done, though, checking that this is a solution of the system. We have to make sure that this point is a solution for every one of the equations. So now I have to go to the second equation and make a very similar substitution. I want to let x equals 3 and y equal 1. And I will have 1 equals 3 minus 2, or 1 equals 1. And that's true as well. What does that mean? I've now shown you a solution for both equations in the system, and therefore I say that 3, 1 is a solution of the whole system. Well, I'll try to show you at least one word problem by the end of this lesson, but for now, the biggest question we should ask is this. If we're given a system of just two linear equations, how would we find the solution? See, in what I just did with you, I actually gave you the solution and we just checked to make sure it was a solution. I'd like to now know how we find the solution if the only thing we're given is the set of linear equations. By the way, before we go anywhere, systems of linear equations can be bigger than just two equations. You could have 3 equations or 4 equations. We're just going to focus on systems of 2 linear equations here in this lesson. Now, in this lesson, I'm going to show you 2 specialized techniques for solving systems of linear equations. They're called solving by graphing and solving by substitution. And I want to start with solving by graphing. You can probably imagine that graphs are going to come into play here. So here's a question. From a graphing perspective, what does a solution of the system y equals 2x minus 5 and y equals x minus 2 look like? I mean, what does it mean to be a solution if you're thinking about it in the context of the graphs? Well, such a solution needs to be a point on each of the 2 lines, and it needs to be the same point on both lines. How can that happen? It happens if the point is an intersection point, a point where the 2 lines cross. So, let's solve this same system by graphing that I looked at earlier. The technique is actually pretty straightforward. You start by just graphing the 2 lines that you were given and finding the intersection point. So I've graphed the 2 lines for you in this figure, and now I see that the 2 lines actually do cross one another. Now, of course, we had to make sure we knew how to draw the 2 lines, but we've done that in previous lessons. So I've drawn them here for you, and now I want you to notice where the intersection point is located. The point where these 2 lines cross is exactly 3, 1. And of course the y-intercepts are -2 and -5. But I see from the sketch of this graph, or I should say the sketch of these 2 graphs, that the intersection point is 3, 1. As soon as I see that intersection point, that's the solution. And therefore, by graphing, if I draw the graph carefully on some graph paper, I can sometimes find that intersection point really accurately. And in this case, that's exactly what we did. Now, before we move on to the next example, let me make another comment. Notice something like graph paper is really like a must here. You could draw these graphs somewhat sloppily on a piece of blank paper, but if you really had to find that 3, 1, you'd have to really draw carefully. And what if you saw the intersection point, but you said it was 2, 1, or you said it was 3, 0.9 or something like that? That's not going to cut it. You've got to have more accuracy than that. So this graph paper isn't just a helpful thing, it's really a must in these examples. And let me also point out that it would probably be very smart to check your solutions after you've done them by graphing by plugging in the information into the equations just to make sure you got everything right. I think that would be very, very wise. Now, with that said, I'd like to move to another example, and I want to solve this system that I'm about to give you by graphing. So we're going to use our graph paper, and we're going to solve the system that way. The system is going to be y equals -2x plus 3 and y equals 3x minus 7. So before I draw the graphs, notice that we're guaranteed to find a solution based on the equations we were given. Now you might say to me, how in the world do you know that? Well, look at the slopes for just a second of the two lines that I gave you. One of the slopes is negative, and the other slope is positive. So if you just think about what the graphs are going to have to look like in general, one of the lines is going to have to go like this, and the other line is going to have to come up like this because the slopes have different signs. Well, the two lines will have to cross somewhere then. There's no way they can be parallel because one of them is going to be going up like this and the other one is going to be going down like this. So I don't know where that crossing point is going to be yet, and I certainly don't know at the angle at which the lines are going to cross one another, but I don't care about that. All I care about is where is that intersection point? And now I say we can actually find it. So what we want to do is draw the graphs of the two lines in question. And when you do that, you notice that both lines are in slope-intercept form, so you know where the intercepts of both lines are, and you can figure out another point on each line using the slope, and then you can just connect the dots to find your two lines. As soon as you've done that, you look for the intersection point between the two straight lines you've just drawn. And again, if you're fortunate, you'll be able to see what that point of intersection is. In this case, the numbers work out very well, and the solution appears to be at x equals 2 and y equals -1, down in the fourth quadrant. So I claim that my solution is 2, -1. Now, as I said a few minutes ago, I think it would be wise to actually check that that's the solution, now that we think that's what it is, by plugging in x equals 2 and y equals -1 into each of the two equations that we started with. So let's do that here. The first equation was y equals -2x plus 3. I'm going to plug in x equals 2 and y equals -1, and here's what I'll get. -1 equals -2 times 2 plus 3. That's saying the same thing as -1 equals -4 plus 3, and -4 plus 3 is -1. So I have the statement, -1 is -1. And of course that's true. Great. I'm not done though until I plug in the same information to the other equation and make sure I get a true statement there. So in that case, I'm going to plug in 2, -1 into the equation y equals 3x minus 7. And when I do that, I'm going to have -1 equals 3 times 2 minus 7. That's the same as -1 equals 6 minus 7, which is also -1 equals -1. So indeed, 2, -1 really is the exact solution of this system, and we found it by graphing. Now, I'd like to look at another example with graphing. I think it's very important that we practice what's going on as we solve these systems with graphing. So let's look at a slightly more complicated example. Let's look at this system of equations. 4x plus 2y equals 5, and 6x plus 3y equals 13. Now, we see here that the equations are definitely not in point-slope form or slope-intercept form. They're actually in something called standard form. They are definitely equations of lines, but in order to graph them, I'm going to suggest that we try to write them either in point-slope form or slope-intercept form. And of course, if we could write them in slope-intercept form, that would be the most helpful for trying to draw the graph, because once you know the intercept and you know the slope, you can draw it pretty quickly. So let's take these two equations, and before we do anything else, let's just rewrite them into slope-intercept form. So the first equation is 4x plus 2y equals 5, and I want to write it as y equals mx plus b. So the first thing I want to do is try to isolate that y, and I'm going to start by getting rid of the 4x. Now, to get rid of the 4x means I'm going to subtract 4x from both sides of the equation. When I subtract 4x from the left-hand side, it will cancel with the 4x that's already there, and I will just have 0 plus 2y, or 2y, on the left-hand side. The right-hand side already had a 5 in it. It now also gets a negative 4x, because if I subtract 4x from the left, I must subtract 4x from the right. And so my new equation looks like 2y equals negative 4x plus 5. I basically just subtracted 4x from the left to the right. Now I want y by itself, and there's that 2 there. I need to get rid of it. How do I get rid of that 2? Well, I can either divide by 2 or multiply by 1/2. It's the same thing. So let's just divide both sides by 2. And when I do, the 2 on the left-hand side will cancel, leaving me y, which is fabulous. And on the right-hand side, I'll have negative 4x divided by 2 plus 5 divided by 2. Negative 4x divided by 2 becomes negative 2x. 4 divided by 2 is 2. And of course, 5 divided by 2 is just 5 divided by 2, 5/2. There's nothing else I can do with that. So the first equation in the original system that we had is now written as y equals negative 2x plus 5/2. Please understand that is a different looking equation from what we were given, but it's the equation of the same line. Now, let's look at the second equation that we were given. 6x plus 3y equals 13. Again, I want to get it into slope-intercept form, so I want to make it look like y equals mx plus b. I want to remove that 6x from the left and get it over to the right-hand side. I do that by subtracting 6x from both sides, and I'll have 3y on the left equals negative 6x plus 13 on the right. Now I need to get rid of that 3 that's next to the y, and the way to do that is to divide both sides by 3. When I divide the 3y by 3, I just get 1y, or y. When I divide negative 6x by 3, I get negative 2x. And when I divide 13 by 3, well, I just get 13 divided by 3, or 13/3, which of course as a mixed number would be 4 1/3. So I can take my original system now and rewrite it so that both equations are in slope-intercept form. And here's what they look like. Y equals negative 2x plus 5/2, and y equals negative 2x plus 13 over 3. Now, what do you notice? Well, notice that both lines have the same slope. That negative 2 that's in front of the x in both lines is the slope of both lines. Notice that the two y-intercepts at the end of the two equations, they are different. And therefore, what do you have for these two lines? If you think about them graphically, they have the same slope and different y-intercepts. That means they are parallel. Now, what does that mean about finding a solution to this system of equations? If the two lines are parallel, will they ever cross? No, of course not. That's a property of parallel lines. And therefore, you will not have a solution to this system. Take a quick sketch, a quick look at a sketch of the graphs of these two lines. I've done it for you here quickly, and notice that's exactly what happens. You have these two parallel lines, they will never cross, and therefore this system has no solution. And it's important that we remember this now. If you're given a system of linear equations, you don't have to have a solution. It's okay if you don't. But you should make sure that you haven't made any mistakes in your arithmetic or your algebra before you come to the conclusion that you don't have a solution. Well, we've seen a few examples of solving a system by graphing. I think that's good. We've also talked a bit about the pros and cons. If you're a visual person and you like to see the mathematics and you like to look at graphs, then solving these systems by graphing is fabulous. One downside, though, is that the technique isn't very precise. For example, what if the solution of the system had been a point like 1/3, 7/5? Well, it might be pretty difficult to see that that's the exact point on the sketch of a graph, even if you use some graph paper and you're very, very meticulous and careful about how you draw the graphs. So that's a downside to solving these systems by graphing. If the solution is a bit messy, it may be hard to see it with the graphs. But there's another technique, thankfully, because otherwise we'd have some problems then. But we don't have problems because we can solve these systems of equations using what's known as substitution. And the idea behind solving by substitution is this. You substitute information from one of the equations that you were given into the other equation that you were given, and then you solve that new equation. The solution of the new equation is then the solution of the system. So we're going to substitute information from one equation into the other, and then we're going to work on that new equation to find our solution. So let me show you an example. It's a very nice way of solving these systems. Take the system 2x plus 3y equals 4 and negative 6x plus y equals -7. I want you to notice that solving this by graphing, it would require a bit of extra work. You'd have to rewrite the equations again, just as we did in the previous example, into something like slope-intercept form, and then you could sketch the graphs. Instead of doing that, I'd like us to use substitution, just for the practice of it. So notice that by adding 6x to both sides of the second equation, the equation would become y equals 6x minus 7. So just a little bit of algebra allows us to rewrite the second equation as y equals 6x minus 7. Now here's where the substitution comes in. That means that we can now replace the y in the first equation with the quantity 6x minus 7. So I can go back to the first equation and replace any y that I see in the first equation with 6x minus 7, because y equals 6x minus 7. And once I've completed that substitution, the first equation then becomes 2x plus 3 times 6x minus 7 equals 4. Notice that the 3 is multiplied with the whole quantity 6x minus 7, not just with the 6x. So you want some parentheses there around the 6x minus 7. Now, notice what we've done. The variable y is now gone. We have one equation that only has x's in it. So if we can now solve for x, we'll be well on our way to finding the solution of this system of equations. So let's go after this equation that we just wrote down and see if we can solve it for x. We have 2x plus 3 times 6x minus 7 equals 4. If we distribute that 3 into the 6x minus 7, we'll have 2x plus 3 times 6x minus 3 times 7. So I've put the 3 in with the 6x and the 3 with the 7. That's equal to 4 on the right-hand side. That's the same as 2x plus 18x minus 21 equals 4 when we start doing some of the arithmetic. 2x plus 18x is 20x minus 21 equals 4. And now adding that 21 over to the right-hand side, or adding 21 to both sides so that the minus 21 cancels on the left, you're going to have 20x equals 25. Can you get x by itself there? Can you isolate the x? Sure. Divide both sides now by 20, and you'll have x equals 25 divided by 20, and that reduces down to 5 divided by 4. Now, you're not done. That tells you the x value of your solution, but you need a y value. Remember that y is supposed to equal 6x minus 7? if you let x equal 5/4, which you just found a moment ago, in the equation y equals 6x minus 7, you can actually find y. If y is 6x minus 7 and x is 5/4, then y is 6 times 5/4 minus 7. Doing a little bit of canceling between the 6 and the 4, that's the same as saying y is 3 times 5/2 minus 7, or 15/2 minus 7, or 15/2 minus 14/2, if you rewrite 7 as 14/2, and 15 minus 14 is 1. So 15/2 minus 14/2 is 1/2. What's the point? Well, the point is that the solution of your system is now known. It's x equals 5/4 and y equals 1/2. Or to write it more concisely, it's just the point 5/4, comma 1/2. As I commented earlier, it might have been hard to see that point if we had used solving by graphing. But we didn't use solving by graphing. We used this new technique called substitution, and we were able to see that this was the point. Now we could check it if we wanted by plugging in 5/4 and 1/2 into the two original equations. Let's do it very, very quickly. The first original equation was 2x plus 3y equals 4. We're going to let x be 5/4 and y equal 1/2. And when we simplify, we'll have 5/2 plus 3/2 equals 4, or 8/2 equals 4, or 4 equals 4. And that, of course, is true. In the second equation, we had negative 6x plus y equals negative 7. Again, letting x equal 5/4 and y equals 1/2, you're going to have negative 6 times 5/4 plus 1/2 equals negative 7. Simplifying that a bit, you'll have negative 3 times 5/2 plus 1/2 equals negative 7. Negative 15/2 plus 1/2 equals negative 7. And negative 15/2 plus 1/2 is the same as negative 14/2. Negative 14/2 really is negative 7. So negative 7 is negative 7 is the statement that comes out, and that's true. Now, I'd like to transition just a bit into a word problem which can be solved by building a system of linear equations and then solving the system. So we're going to apply now this idea of a system of linear equations to a word problem, just to get a feel for how to translate the English into one of these systems of linear equations. So let's say a farmer grows both corn and wheat on his 500-acre farm. So he's got a total of 500 acres. He wants to plant 100 more acres of corn than of wheat. And the question is, how many acres of each should he then plant? Now, you might actually be able to just take out a piece of paper and scribble down some ideas, and before you know it, you'll have your answer. That's not really my point in doing this example. I want us to translate it into a system of linear equations first, and then see if we can work through the algebra to find the solution. You never know how complicated these kinds of questions can get, so I don't want us to fall into the trap of just thinking, well, let me try scribbling some numbers and see if it all works out. Let's rely on the algebra to help us. So the information in the problem tells us what the equations of the system should be. Before we go to any equations, let's write our variables down. We do it all the time. I'm going to let C equal the number of acres of corn to plant. That's why I chose C for corn. And I'm going to let W be the number of acres of wheat to plant. And now let's try to take from the English phrases what our equations ought to be. Well, the total number of acres that the farmer has is 500. So W plus C needs to equal 500. Remember, W was the number of acres of wheat to plant, and C was the number of acres of corn to plant. We're assuming the farmer's going to plant all of his acres, so W plus C is going to be 500. That's an equation. That's one of the equations in our system. Secondly, we're told that the number of acres of corn is supposed to be 100 more than the number of acres of wheat. So what does that mean about the relationship between C and W? Well, C is supposed to be 100 more than W. And in some of our previous work in translating like this, that means that C needs to be 100 plus W, or you could write it as W plus 100. The point is, C needs to be 100 bigger than W. Well, we now have our system of equations. It's going to be W plus C equals 500 and C equals 100 plus W. And now we are set up to actually do substitution in order to solve this system of equations. Why is that? Because I know that C is exactly 100 plus W. So if I go back to the first equation that we wrote down, W plus C equals 500, I can replace the C there by 100 plus W. And when I do that, the first equation goes from W plus C equals 500 to W plus 100 plus W equals 500. I've now substituted for the C. And now I only have W's and numbers, which means I can find W now if I just do some algebra. So here we go. W plus 100 plus W is 500. I can put those two W's together now by addition, and I get 2W plus 100 equals 500. We're on our way. That means if I subtract 100 from both sides of my equation, I can start to isolate that W. If I subtract 100 from both sides, the 100 on the left will cancel, and I'll be left with 2W on the left equals 500 minus 100 on the right, and that's, of course, 400. So my equation is now 2W equals 400. Well, if 2W equals 400, W equals 200 simply by dividing by 2 on both sides of the equation. So W is 200. Am I done? No, I'm almost done. I'm at least halfway there. I now need to find out C. Well, if W is 200 and C was 100 plus W, then C is 100 plus 200, which is 300. Now, we've gotten some numbers, but we should never stop in a word problem when you just get numbers at the end of the page. You should make sure you understand exactly what these numbers actually mean. W equals 200 means the farmer needs to plant 200 acres of wheat, and C equals 300 means the farmer needs to plant 300 acres of corn. Now, let me make a quick comment about solving by substitution before we close out our lesson. The technique goes really well when one of the equations can be easily solved for one of the variables. For example, in the problem I just did, the second equation already tells you that C is exactly 100 plus W. In other words, we already knew how to replace the C by another quantity. But what if the original system had been much more complicated? For example, what if it had been 3C plus 5W equals 250 and 4C plus 10W equals 1,750? Solving by substitution here would not be real friendly, okay? It can be done, but it's not the easiest thing to do because neither of the two equations looks like it's easy to isolate one of the variables, to get one of the variables by itself. And of course, solving by graphing, as I've already pointed out, has even more problems to it, especially when it comes to trying to see accurately how you're going to find your solution. So what are we going to do? It sounds like there's a lot of problems here. Well, I'll tell you in just a second. Today we started talking about systems of linear equations, sets of two or more linear equations that are linked together somehow. And we talked about how to find the solutions of these systems, and we did a lot of examples using graphing as well as using the technique called substitution. But as I just pointed out, there may be problems with each of these two techniques. So next time, we'll learn another technique for solving even more complicated systems of linear equations. It has a name. It's called solving a system by elimination. And we'll discuss that technique in the next lesson. And I'll see you then. In the last lesson, we looked closely at solving systems of linear equations by graphing and by substitution. And although those two methods are really useful in some circumstances, they aren't always flexible enough to handle more complicated systems. So in this lesson, I'm going to introduce another method to handle systems of linear equations which are a little more complicated. It's called solving by elimination. Now, in fact, solving by elimination can also be used to solve the kinds of systems we saw in the previous lesson. But today I want to show you some pretty complicated examples to see how the technique is used. So, what's the idea behind solving by elimination? Well, it's pretty basic, actually. It boils down to three math facts. And here are those three facts. First of all, if A equals B and C equals D, then A plus C equals B plus D. In other words, if you have two equalities and you add the left-hand sides of both and you add the right-hand sides of both, then those two sums must also be equal. So A equals B and C equals D implies that A plus C equals B plus D. Similarly, if A equals B and C equals D, then A minus C equals B minus D. In other words, I can subtract the two left-hand sides from one another, and I can subtract the two right-hand sides from one another, and I'll have a new equation which is still true. And the third math fact, which is very important in this lesson, is if A equals B, and you multiply both sides of that equation by another number, say C, then CA equals CB. So those three math facts are going to actually prove to be the foundation for solving systems by elimination. They might not look like they're much, and they might not look like they're going to help, but they really will be handy as we start to talk about solving by elimination. So let me start with an example of a system of linear equations that I want to solve, and let's just talk it through as we go. Here's the system. Solve 2x minus 3y equals 12 and 6x plus 3y equals 60. Now, we should talk for just a moment about what happens if I were to just add the two left-hand sides. I mean, you might be saying, well, why'd you think of that? Well, let me show you why I thought of it so that in a moment, when we do other examples, you'll think of these ideas as well. Just take the two left-hand sides for just a moment and add those two left-hand sides. What do you get? Well, you have 2x minus 3y, that's the first left-hand side, plus 6x plus 3y. And that's going to give you 8x, of course. The 2x and the 6x can be added together. They are like terms, like we've seen before. So that's 8x. Minus 3y plus 3y gives you 0y. And so that means that the left-hand side actually simplifies when you add 2x minus 3y to 6x plus 3y. It simplifies to just 8x. Okay, plus 0y, but I'm not going to think about plus 0y. It's just 8x. And now something very, very significant just happened. We have eliminated the variable y from the left-hand sides of those equations. And the elimination of y is exactly why we call this method of solution the system, solving systems by elimination. So if we add the left-hand sides like that, we would need to add the right-hand sides as well, and then one of our math facts that I mentioned a moment ago would help us. So let's go back to the original equations now, and let me walk us through how the system could actually be solved with elimination. We had 2x minus 3y equals 12, and we had 6x plus 3y equals 60. If I add the left-hand sides together and I add the right-hand sides together, I'll have a new equality. The left-hand sides add together to give me 8x. That's what I was just saying a few moments ago. The right-hand sides, 12 plus 60, will give me 72. Remember, if you're going to add the left-hand sides, you need to add the right-hand sides as well. You would never want to add the lefts and maybe subtract the right-hand sides. That would not work. So you would then have 8x equals 72. Can you solve that for x? Well, that's just a one-step equation. We've seen how to solve those a few lessons ago. To solve 8x equals 72 for x, you just divide both sides by 8. The 8x will have cancellation with the 8 in the denominator, and you'll just have x. 72 divided by 8 on the right-hand side will equal 9, again due to some cancellation. So look what just happened. We took this system of linear equations, and all of a sudden we know that part of the solution is x equals 9. But we still need to find y. How would we find the value of y at this point if we know that x equals 9? Well, just go back to either one of the original equations, plug in 9 for x, and solve for y. So for example, let's go back to 2x minus 3y equals 12, and plug in 9 for x, and let's see what happens. If you plug in 9 for x, you're going to get 2 times 9 minus 3y equals 12. 2 times 9 is 18, so the left-hand side is 18 minus 3y, and the right-hand side is 12. Now you want to isolate the 3y. In fact, you want to isolate the y in a moment. How do you isolate that y? Well, you need to get rid of the 18. To get rid of that 18, you subtract 18 from both sides of the equation. That's perfectly legal to do. 18 minus 18 on the left is going to be 0. So the left-hand side will become negative 3y. 12 minus 18 on the right-hand side is going to give you negative 6. 12 minus 18 is negative 6. So you now have negative 3y equals negative 6. You want to isolate the y, so you divide by negative 3. That leaves you just y on the left. On the right, you'll have negative 6 divided by negative 3. And when you divide two negative numbers, you get a positive number back. And then, of course, 6 divided by 3 is 2. So y equals 2 is part of your solution. Remember, x equals 9 was also part of your solution. And therefore, the point, the ordered pair that is the solution, is 9, 2. 9 for x and 2 for y. Now, we should always check our answers. I've been saying that to you from the time we started these lessons together. We should check, 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 because you never know if we've made a mistake here and there. And so let's now check that this is a solution. The way we do that is to plug 9 and 2 in for x and y in both of the equations. Let's do it very quickly. 2x minus 3y equals 12 was the first of the original equations we had. 9 for x and 2 for y gives us 2 times 9 minus 3 times 2 equals 12. That's 18 minus 6 equals 12, which is 12 equals 12. And that's definitely true. Now the second equation we had was 6x plus 3y equals 60. Again, I need to see if x equals 9 and y equals 2 will satisfy that equality. We'll make a new true statement. So I'm going to have 6 times 9 plus 3 times 2 equal to 60. 6 times 9, 54. I hope you have those multiplications memorized. 6 times 9 is 54. 3 times 2 is 6. 54 plus 6 really is 60. And therefore, that's a true statement as well. And since that ordered pair, 9, 2, solved both of those equations, we say that it's a solution of the system. So, I want to move to another example now. Notice what we did, though, by solving by elimination. We were trying to get rid of one of the variables in some legal fashion. So, let's go to a second system now, and let's see if we can figure out how to do the same sort of technique. Here's the new system. 5s plus 4t equals 27, and 3s plus 4t equals 31. Well, in the previous example, do you remember what I did? I added the two left-hand sides. Let's try that here. Maybe it works again. So I'm going to take the 5s plus 4t, and I'm going to add it to 3s plus 4t. And what do I get? I get 8s plus 8t. Now, let me ask you a question. Did we accomplish our goal? Well, what was our goal? Our goal was to get rid of one of the variables. Did we get rid of one of the variables? The answer is no. And that's a signal when you're doing solving by elimination that what you've done is not the thing to do because it didn't take you towards the solution. It actually made the problem just as problematic, just as ugly, if you will, as it was before. So let's go back to the original equations and ask ourselves, what could we do instead of adding the two left-hand sides in order to cancel out or eliminate one of the variables? Well, notice that there's a 4t in both of the left-hand sides. That means if I subtracted one of the equations from the other and used my second math fact from the beginning of this lesson, I could get rid of the 4t. By the way, it doesn't matter which one you subtract from the other. You could subtract the first one from the second, or you could subtract the second one from the first. In this case, I'm going to go ahead and subtract out the second one in this problem. So let's go back to my original set of equations. 5s plus 4t equals 27. And 3s plus 4t equals 31. And now I want to subtract out the second equation. If I'm going to subtract the left-hand side of it, I need to subtract out the right as well. What is that new equation going to look like? It's going to look like negative the quantity 3s plus 4t equals negative 31. Well, before you do any of the subtraction, you should distribute that minus sign that's on the left-hand side. And if you put that minus sign that's in front of the 3s plus 4t into those parentheses, you'll have negative 3s minus 4t equals negative 31. So you now have two new equations. 5s plus 4t equals 27, and negative 3s minus 4t equals negative 31. And now you basically just add those two. In essence, by multiplying by a negative and adding, it's the same as subtracting. And when you do that, you'll have 5s minus 3s, which is 2s, equals negative 4 on the right-hand side. What happened to the t's? Well, 4t minus 4t is 0t, and so I'm not going to write it down. So I now have 2s equals negative 4. Again, let me point out that you had to subtract both the left-hand side and the right-hand side of the second equation. Some students will fall into the trap of forgetting to subtract out the right-hand side. Make sure you put that minus sign on both sides of that second equation. And secondly, a lot of students miss putting that minus sign in front of the 4t. Remember, we had to distribute that minus sign into the parentheses, and some students will distribute the minus sign in front of the first part, but they'll forget to distribute it in front of the second part, and that's a very common mistake as well. Now, what have we done? I now have 2s equals negative 4, so I have eliminated the variable t, and that was very, very important. Once I have 2s equals negative 4, I can divide both sides by 2, and when I do that, I get s equals negative 2. But you're not done. You still need to find the value of t, which is part of the solution. So if I substitute s equals negative 2 back into either of the two equations we started with, I should be able to find t. In fact, I will be able to find t. So just for fun, I'm going to use the second of the original equations to find that value of t. We could use the first if you want, but I'd like to let the second equation have a little fun as well. So here we go. 3s plus 4t equals 31. I know that s has to be negative 2, so I'm going to replace the s by negative 2. And I'll have 3 times negative 2 plus 4t equals 31. 3 times negative 2 is negative 6, and then plus 4t equals 31. And now if I take that negative 6 and add 6 to it, and add 6 to the right-hand side, remember, if you add to one side of an equation, you must add the same amount to the other. You will cancel the negative 6 from the left, because negative 6 plus 6 is 0. And on the right, you'll have 31 plus 6 is 37. So your new equation will be 4t equals 37. Dividing both sides of that by 4 will give you t equals 37 divided by 4. And therefore, you know your full solution now. S is negative 2, and t is 37 over 4. Or to put it in an ordered pair, it's just negative 2 comma 37 over 4. Notice that solving this system by graphing would have been difficult. We learned about solving by graphing in the previous lesson, but if you had tried to identify 37 over 4 in the sketch of one of these lines, it would have been very, very difficult to do. So this solving by elimination, I think, was a better way to do it here than by graphing. Now, let's check the solution to make sure we're correct. I know I talk to you about this all the time. You're probably tired of me saying it, but it's very, very important that we do it. We go back to our original equations and we plug in this information to make sure it really is a solution. So we have 5s plus 4t equals 27. That means 5 times negative 2 plus 4 times 37 over 4 needs to be 27, since I'm using my solution information. 5 times negative 2 is negative 10. 4 times 37 over 4 is going to be 37, because the 4's will cancel each other. And you'll have negative 10 plus 37 equals 27. And of course, that just says 27 equals 27, and you're good to go. Let's look at the second equation quickly. You have 3s plus 4t equals 31. Plugging in s equals negative 2 and t equals 37 over 4 gives you 3 times negative 2 plus 4 times 37 over 4 equals 31. That's the same as negative 6 plus 37 again equals 31. And negative 6 plus 37 really is 31. So 31 equals 31, and that guarantees now that we have a solution to the system of equations with which we started. Now, let's move to another example that I think looks like it's going to cause more trouble at first, but I'm going to show you a technique for getting past that trouble. Here's the example. I want you to solve the system negative 2x plus 15y equals negative 32 and 7x minus 5y equals 17. Well, let's try to use the techniques we've already seen in the previous examples just to see if they work. Let's add the two equations together. When you add those two left-hand sides, you're going to get 5x plus 10y. The 5x comes from 7x minus 2x, basically, and the 10y comes from 15y minus 5y. Did we accomplish our goal? In other words, did we eliminate a variable? Answer, no. Okay, maybe we could try subtracting both of the equations from one another. Again, keeping in mind, if you subtract, say, the second equation, you've got to make sure you distribute the minus sign. When you do that, and you subtract the second equation from the first, you'll get negative 9x plus 20y equals negative 49. Have you eliminated a variable there? No. So neither of these techniques is working right now. What do? Just quit? No. Let's go back to the start of this lesson when I said that there were 3 math facts. We used the first one and the second one already, but we didn't use the third. Let's use it now. The third fact was that if A equals B, then C times A equals C times B. So why don't we go back to the equations we started with and multiply one of the equations by something to help us? Remember, if you multiply the left-hand side, you must multiply the right-hand side by the same amount. Look at that second equation and multiply it by 3. What would we have as our system then? Well, our system would be negative 2x plus 15y equals negative 32, and now I'm multiplying the second equation by 3. It's going to become 21x minus 15y equals 51. Remember, I have to multiply every term in that equation, both on the left and the right, by 3. And look at the y's now. If you were to add these two equations together, the y's will disappear. They will be eliminated. Remember, that's the name of this technique. So I'm going to add these new equations together, and when I do so, the x's survive. Do you see how many x's will be there? It'll be 19x plus 0y, so I'm going to ignore that, equals, what's the right-hand side? The constants add together to give you 19. And now the new equation is 19x equals 19. Well, what's going to solve that? X equals 1, of course, because 19 times 1 is 19. So x equals 1 is part of my solution. But it's not the whole solution. I still need to find y. So I go back to one of my original equations, I plug in x equals 1, and I try to find the y. Here we go. Negative 2x plus 15y equals negative 32. That was one of my original equations. Plug in x equals 1. The first term then is just negative 2 times 1, which is negative 2. So I have negative 2 plus 15y equals negative 32. I want to get the y by itself. So I add 2 to both sides. The negative 2 plus 2 cancel. I'll be left with 15y on the left by itself. When I add 2 to the right-hand side, I get negative 32 plus 2, which is negative 30. So my new equation is 15y equals negative 30. Dividing both sides of that equation by 15 gets the y by itself, and the right-hand side is negative 30 over 15, which is negative 2. And my final solution then is x equals 1, y equals negative 2, or just the ordered pair 1, negative 2. Well, I keep talking to you about having to check our solutions, and I know that it's very, very important. But in this example, I'm going to go ahead and pass on that. I'm going to let you do the check of the solution of this system of equations, because I think you can do that on your own at this point. We've done several of these together. I'll let you go ahead and do it in this case. Now, I'd like to move on then to a word problem, and just to see how these systems of equations can actually be used in order to solve what sounds like at least a real-world situation. So here's the example I want to give you. A photographer offers 2 packages for photographs to the students at a school. The first package includes 20 wallet-sized photos and 1 8x10 photo, and the total package is $30. The second package, which is different, it includes 10 wallet-sized photos and 3 8x10 photos for $40. Using a system of equations, let's determine the cost of each type of photo. That is, how much does one wallet size cost and how much does one 8x10 cost? Okay, that's the problem. Well, we really need to identify our variables. I've been saying that all course long. Let's do it again here. We have 2 variables to try to pick out. I'm going to let W equal the cost of a wallet-sized photo, and I'm going to let X equal the cost of an 8x10 photo. Now you might say, where'd you get those? Well, the last sentence in the problem said, figure out how much one wallet-sized photo costs and how much one 8x10 photo costs. Those are the 2 variables I just named. You could have called them other letters. I'm going to call them W for wallet and then X for an 8x10. I couldn't really think of a good letter there. So those are my 2 variables, W and X. Now, I need some information from the other parts of the English in that problem to help me get 2 equations. Well, the first package cost basically will translate into the following equation. 20W plus 1X equals $30. Now, where did I get that? Well, remember, the first package was 20 wallet-sized photos plus 1 8x10 is going to cost $30. That's where 20W plus 1X equals 30 comes from. The second equation from the same part of the problem tells me that 10W plus 3X equals $40. 10W stands for the cost of 10 wallet-sized photos, and 3X stands for the cost of 3 8x10 photos. So I now have 2 equations. 20W plus X equals 30, and 10W plus 3X equals 40. Now I'd like to solve that. I'd like to find W and X based on that system. Well, how am I going to do it? Well, I'm going to use elimination. And in particular, I want to eliminate one of the variables. I'm going to choose to multiply the top equation by -3 and then add them. By the way, before we do that, you might say, why don't you multiply the second equation by -2 and then eliminate the W's? That would have worked. You can do that. We'll get the same solutions either way, but I'm just going to pick to multiply the first equation by -3 and eliminate the x's. There's nothing special about eliminating the x compared to the w, so we're good to go. When I multiply that first equation by -3, I'm going to have -3 times the quantity 20w plus x equals -3 times 30. I must multiply on both sides by the same amount. I then need to distribute that -3 very carefully, especially on the left-hand side, so that I don't miss that little x that's inside the parentheses. When I distribute that negative 3 in the first equation, it becomes negative 60w minus 3x equals negative 90 on the right-hand side. Negative 3 times 30 is negative 90. So the first equation has been transformed into negative 60w minus 3x equals negative 90. The second equation hasn't been moved at all. It's 10w plus 3x equals 40. Do you see now that if I add those two new equations that the x's will cancel, x will be eliminated? That's exactly what I'm going to do. So when I add those two, what do I get? Well, negative 60w plus 10w is negative 50w. That's the left-hand side. The x's have gone away. And the right-hand side is negative 90 plus 40, which is negative 50. Well, negative 50w equals negative 50 means w equals 1. If you don't just see that automatically, divide both sides by negative 50, and you'll get w equals 1. Translation, each wallet-sized photo basically costs $1 by itself. Now I want to go find x. I go back to one of my equations in the original system. In this case, I'm going to go to the second equation. Doesn't matter which one. And I'm going to plug in 1 for w, because w equals 1, and I'm going to solve for x. So I have 10w plus 3x equals 40, which means I have 10 times 1 plus 3x equals 40. 10 times 1 is 10. So I have 10 plus 3x equals 40. Subtracting 10 from both sides of the equation gives me 3x on the left equals 30 on the right, because 40 minus 10 is 30. And if I divide by 3 on both sides of 3x equals 30, I'll be left with x equals 10. Remember that x was the cost of each 8 by 10 photo. So x equals 10 means that each 8 by 10 photo cost $10. And remember, each wallet-sized photo was going to cost $1. Again, I'm going to leave it to you to check that this is the solution. It can be done. It won't be complicated, but for a matter of time, I'd like to move forward and let you go ahead and check that solution on your own. Okay, I want to look at one last example that seems to defy all the tricks we've used so far, and I just want to make sure that we see this kind of an example because you might see it in your future math work. So here's the example. I want to solve 15x plus 3y equals 9 and 10x plus 7y equals negative 4. I want you to notice that adding the equations is not going to eliminate anything, subtracting the equations isn't going to eliminate one of the variables, and it doesn't appear that there's an obvious choice for a number to multiply one of the equations by in order to eliminate one of the variables. So what am I going to do? I mean, it seems like we can't really do a whole lot. Well, here's what we're going to do. I'm going to choose to multiply the first equation by negative 10 and the second equation by 15. You might say, wait a minute, are you allowed to do that? In fact, I am. I can multiply one of the equations by something and multiply the second one by something else. I'm not bound to just multiply one of the equations by something. If I multiply the first equation by negative 10 and the second equation by 15, and I add, I will then eliminate one of the variables. Do you see which one it is? I'm going to eliminate the x. Now, I could choose differently. I could go back to the original set of equations, and I could multiply the first equation by negative 7 and the second equation by 3. If I multiplied the first equation by negative 7 and the second by 3, when I add, do you see what gets eliminated? The y variable gets eliminated. And I'm going to go ahead and approach it that way right now. So let's multiply the first equation by negative 7 and the second equation by 3. Remember, I have to distribute, so I have to be very careful as I do this. But once I've distributed the negative 7 and the 3 through those two equations, I'll be left with the following. Negative 105x minus 21y equals negative 63, and 30x plus 21y equals negative 12. Now there's a lot of arithmetic there. The biggest number we see is the 105. It comes from 15 times 7, and it's negative because it was negative 7 times positive 15. Now take those two new equations and add them, and you see that the y's will disappear, and you'll be left with negative 75x equals negative 75. The y is gone, and x is simply equal to 1. X equals 1 is part of my solution, and now I go back to one of the original equations to find y. Well, 15x plus 3y was 9, so 15 times 1 plus 3y is 9. That means 15 plus 3y is 9, or 3y equals negative 6 if you just subtract 15 from both sides. Dividing by 3 gives you y equals negative 2, and that means that the solution to this system of equations is 1 comma negative 2. Well, today we've solved lots of different systems of linear equations which would not have really been easily solved with either graphing or substitution. But thanks to this technique of eliminating one of the variables, we see that we can solve a really large number of different types of systems of linear equations. In our next lesson, I'm going to shift gears a bit and talk about linear inequalities, which are mathematical sentences where the equal sign has been replaced by a less than sign or a greater than sign. There are some really interesting twists to these kinds of problems, so I look forward to talking with you about them then. Sometimes mathematical situations arise where we aren't worried about whether certain quantities are actually equal to one another. Instead, we just want to know that one quantity is maybe less than or greater than the other. For example, if we have an expression for the cost for our business and another expression for revenue or income for our business, we'd like to know the circumstances under which the cost expression will be less than the revenue expression. In other words, we'd like to make a profit. So we'd like to see mathematical situations where we're not worried about things being equal, just whether one thing is larger than or smaller than another. And this leads us to the topic of solving linear inequalities. A linear inequality provides an algebraic way to identify a part of the xy plane, or the Cartesian coordinate plane, whose boundary is a straight line. For example, if we wanted to discuss the part of the xy plane where the points satisfy y greater than 0, then we'd be talking about all of the points in quadrants 1 and 2. We'd also be talking about the boundary line because y equals 0 or the x-axis are the same thing. But if you're only looking at y greater than 0, strictly greater than 0, then you only care about quadrants 1 and 2. Before we jump into these linear inequalities, which cut the plane into two regions, I'd like to talk for a moment about some basic properties of inequalities. And I'd like to discuss inequalities on just the number line by itself, not the Cartesian plane, but just the one-dimensional number line. It's really important to remember some basic facts about inequalities. So let's start with the following. First, let's let A, B, and C just be three variables that represent some numbers, real numbers. And then we know the following. If A is less than B, then A plus C is less than B plus C. In other words, if you have one number that's already less than another and you add the same amount to both sides or the same amount to both numbers, then the inequality stays the same. Why is that actually true? Well, you can think about it on the number line. If A is less than B, that means that A would be to the left of B on that number line. If you then add the same quantity, say C, to A, you'll shift A by C units to the right. But by doing that, when you add C to B, you would shift B by the same amount. So on the number line, if A is here and B is to its right, adding C to both of them simply shifts them together. So if A was to the left of B before, then A plus C would still be to the left of B plus C. And that means that if A is less than B, then A plus C would be less than B plus C. So adding the same amount to an inequality doesn't change the sign. So for example, we know that 5 is less than 8. That's pretty common knowledge. That means that if you added 4 to both sides of 5 is less than 8, you'd get 5 plus 4, which is 9, is less than 8 plus 4, which is 12. That's just a small numerical example of the rule I was telling you a few moments ago. By the way, that same property is also true if A is less than or equal to B, not just strictly less than. In other words, if A is less than or equal to B, and you add C to both sides of that inequality, you'll have the statement A plus C is less than or equal to B plus C. That would be another rule that you could state. A similar statement can be true when the inequality symbol is a greater than symbol, and also when it's greater than or equal to. In other words, here's the point. If you have an inequality written down and you add the same amount to both sides of that inequality, then the inequality sign doesn't change. That's the important property we need to keep in mind. Similarly, if you have an inequality written down, whether it's with a less than symbol or a less than or equal to symbol or a greater than symbol or a greater than or equal to symbol, and you subtract the same amount from both sides, then the inequality stays the same. The reasoning there is the same kind of reasoning as we had before. If A is less than B on the number line, and you subtract C from both sides, then the numbers just get shifted, but they get shifted together. And that means if A was less than B to begin with, and you subtract C from both of them, then A minus C will still be less than B minus C. So subtracting from both sides of an inequality keeps the inequality symbol the same, whether you start with a less than or equal to, or a greater than or equal to. So for example, you know 5 is less than 8. We also know then that 3 is less than 6 because 5 minus 2 is less than 8 minus 2. So addition and subtraction don't really do much to inequalities. They don't change the inequality symbol. But what about multiplication and division? Well, it's a very, very different story. Consider, for example, that 5 is less than 8. You already knew that. What if I multiply both sides of the inequality, 5 is less than 8, by the same number, let's say 2? Then I'll have 5 times 2 is less than 8 times 2, or 10 is less than 16. Is 10 less than 16? Yes, it is. So that's a good thing. The 2, but multiplication by 2, didn't change the inequality. Now, what if I take 5 is less than 8, and I multiply both sides of that by -3? Then I'm going to have the statement -15 is less than -24. That's actually not correct. In fact, -15 is bigger than -24. And you might be saying, how in the world could that be? Well, here's how. Take your number line again, put the 0 somewhere in the middle, and now ask yourself, where is -15 and where is -24? -15 is 15 units to the left of your 0, so it's here. And -24 would be -24 units to the left of 0, so it would be even farther out. Now, which number's to the right and which number's to the left? Well, -15 would have been here and -24 would have been farther over to the left. And that means that the -24 is actually less than -15, or -15 is greater than -24. So notice what would have happened then. We started with 5 is less than 8, and when we multiplied by -3, we got -15 is greater than -24. And that little example leads us to a very big and very important math fact. And here's what it is. If you start with A is less than B, and C is a positive number, and you multiply both sides of the inequality by C, then the inequality doesn't change. You're left with AC is less than BC. But if A is less than B and C is a negative number, and you multiply both sides by that C, then the inequality sign must change. So if A had started out less than B, then AC needs to be greater than BC. And this property is true whether you're using a less than symbol or a greater than symbol, a less than or equal to, or a greater than or equal to. All of those are going to have this same property. Multiplication by a negative number switches the inequality. A similar statement can be made when you divide by numbers as well with inequalities. Here's what that statement is. If you have an inequality and you divide by a positive number, then the inequality doesn't change. So if you start with A is less than B and you divide by a positive number C, then A divided by C will still be less than B divided by C. But if you start with A is less than B and C is a negative number and you divide by that C, then A over C becomes bigger than B over C. So when it comes to multiplying or dividing an inequality, you must know what the sign of the numbers are, because if you multiply or divide by a negative number, the inequality is going to switch. That doesn't matter when you're adding and subtracting. When you add and subtract to an inequality, the inequality symbol just sits there. But when you multiply or divide, you must know whether you are multiplying or dividing by a positive number or a negative number. Okay, that's a quick review of some of the arithmetic facts that have inequalities in them. And they're very, very important. And we're going to use them as we walk through the rest of this lesson together. With those done, I'd like to turn our attention now to graphing inequalities just on the number line. We're going to do an example or two of that very quickly. So for example, let's say we wanted to graph the inequality x is less than or equal to 3 just on the number line. What do we do? You've probably done some of these in the past, but let's just make sure we're on the same page together. If you want to graph x is less than or equal to 3 just on the number line, you draw your horizontal line or number line, you label some of the points. You better label 3 because it's an important one. Maybe you label 0 as well. You draw a dot at 3 and you fill in that dot, and then you somehow shade the portion of the number line to the left of 3. Why to the left of 3? Because you're trying to show all the points that are less than or equal to 3. Once you've done that, several things ought to be noticed. First of all, by doing this problem, you have split or separated the number line into two different pieces. You've grabbed the parts that are less than or equal to 3, and you've also distinguished the parts that are greater than 3. You've got the piece you shaded and the piece you didn't. Okay? That's one comment to make. The second comment to make is, if the inequality had been x is strictly less than 3 instead of x is less than or equal to 3, you would have used an open circle to mark the point at 3. You would not have shaded it in, because 3 is not included in the set of numbers which satisfy x is less than 3. 3 is not less than 3. So these two comments are going to come into play when we start talking about linear inequalities in the plane in just a second. Well, with all of this as background, I do want to go now to some linear inequalities in the Cartesian plane, or the xy plane. So the idea is going to be, we're going to be handed an inequality which is going to have a line as its boundary in the xy plane, and we're going to want to know which part of the Cartesian plane do we shade in. Just like a moment ago, we took our number line in one dimension and we shaded in one part of it and left the other part alone. So let's look at the following example. I want us to graph the solution set of the linear inequality y is less than 2x plus 1. Now, before we go anywhere, let's make sure we understand exactly what I just told you to do. Graph the solution set of the linear inequality y is less than 2x plus 1. There are lots of solutions to y is less than 2x plus 1. In fact, there are infinitely many different pairs for x and y that you could plug in so that the y was less than 2x plus 1. So I'm looking for all of those pairs inside the Cartesian plane. To start the problem, I'm going to first sketch the graph of y equals 2x plus 1, not y is less than 2x plus 1. What can I do with that line? Well, that line, of course, is just a straight line because y equals 2x plus 1 is written in slope-intercept form, that line serves as a boundary, a very natural boundary, for the region of the xy plane which does represent the set of solutions for the inequality. So when I draw that line, I'm going to do it in a dashed fashion, not as a connected line, if you will, but in a dashed form. Why am I going to do it dashed? Well, because the points on the line, y equals 2x plus 1, are not part of the solution set for y is strictly less than 2x plus 1. And now here's the analogy with the open circle on the number line from a few moments ago. Remember, on the number line, when you're just dealing with one-dimensional problems on that number line, you use an open circle to show that that number is not part of the solution set. When my line in 2 dimensions is not part of the solution set, I'm going to draw it in a dashed fashion so that I remind myself that the points on the line are not part of the solution. And they're not going to be part of the solution exactly when the original problem started out with a strictly less than or a strictly greater than. And now the question is, and this is the whole question for the rest of the example, which 2 regions of the xy plane do I want to shade in? In other words, the solutions of y is less than 2x plus 1 are all going to be either on one side of the line we just drew, or they're going to be on the other side. So I want to pick which of those 2. It's a 50-50 problem, okay? You just have to pick which of the 2 to shade in. In this case, we want y is less than 2x plus 1. And because of that, I'm going to choose to shade in the part of the plane which is below the line. And I'm choosing that because I want the y's to be less than as opposed to greater than. And so I shade in that whole region of the xy plane. All of the points in that region are solutions of the inequality. Now, before we go on though, you know me, I always want us to check our answers. So we should do that here. Well, here's how you would check your answer very, very quickly just to see if it's plausible. Every point in the region you've shaded is supposed to satisfy the inequality. Pick a point in that region and just see if it actually works. Notice that the origin is in the region you've shaded. That's the point 0, 0. That means that 0, 0 must be in the solution set of the inequality. So let's plug in 0 for x and 0 for y in the original inequality and see if we get a true statement. Y is less than 2x plus 1 is going to become 0 is less than 2 times 0 plus 1 when we plug in 0, 0. The left-hand side, of course, is 0. Then I have less than 0 plus 1 because 2 times 0 is 0. And 0 plus 1 is 1. So I have the statement 0 is less than 1. Now that's not an equality statement, but it is a mathematical statement. 0 is less than 1. Is that a true statement? Yes, it is. And because that's a true statement, I'm confident that 0, 0 is part of my answer set. And because 0, 0 is in the region that we shaded, I say we did it right, and I say we move forward. So let's move forward to another example. Let's graph the solution set of the linear inequality 4x plus 8y is greater than or equal to 10. So to start this problem, I need to figure out the boundary edge, which is the straight line defined by 4x plus 8y equals 10. This is the standard form of the equation of this line, and once I can figure out where that line is, I can plot it, and then I know that all of my solutions live on either one side or the other side of that line. So let's take 4x plus 8y equals 10 and rewrite it in slope-intercept form just so we can plot it quickly. 4x plus 8y equals 10. Subtract the 4x to the right-hand side and you'll have 8y equals negative 4x plus 10. Now, you can divide both sides by 8, and you'll have y, because the 8's cancel, equals negative 4x over 8 plus 10 over 8. Or you'll have y equals negative 1/2 x, because 4 over 8 is 1/2, plus 5 over 4, because 10 over 8 reduces to 5 over 4, or 5/4. And now I know what my boundary line is for the solution set here. It has a slope of -1/2, and it has a y-intercept of 5/4. Notice also that the original problem had a greater than or equal to symbol rather than just a strict greater than symbol. And because of that, I'm going to draw in my line in a solid way, not in the dashed way, but solidly. And so let's draw that line in now. You need to do that on some graph paper if you have it. And once you've drawn in that line, you have now defined two very natural regions of the xy plane. One of them is sort of above that line, the other one is below. The question is, which set of points, the ones above the line or the ones below the line, are going to satisfy the original inequality? Well, I want the ones where y is greater than or equal to -1/2 x plus 5/4. So I'm going to choose the region that is above because I want the y's to be greater than or equal to this line, and therefore the y's need to get big. So I'm done. Well, again, I should really check my answers. So we should pick a point that's in the region that you've shaded, and let's see if it actually makes the inequality true. Notice that the origin now is not in my solution set. I've shaded away from the origin, so I need to pick another point. Well, why not a point on the y-axis, which is above the y-intercept of the boundary line? Something like, how about 0,3? 0,3 is in the set. Is it really going to make the original inequality true? Let's check. The original inequality was 4x plus 8y is greater than or equal to 10. X equals 0, y equals 3 gives me 4 times 0 plus 8 times 3 is greater than or equal to 10. That says 0 plus 24 is greater than or equal to 10, or 24 is greater than or equal to 10. Now, is 24 greater than or equal to 10? If one of us had $24 and the other of us had $10, I think the one with 24 would have more money. So indeed, 24 is greater than or equal to 10. It's a true statement, and therefore the point we chose really is in the solution set. Now, there was nothing special about 0,3. We could have actually picked any point that was in the shaded area. But in our case, it was very helpful to pick it because one of the values inside the ordered pair was 0. And that 0 kind of simplified our arithmetic. And that's why I chose that one. Now, I want to move to another example that might be a bit confusing at first. My goal in showing it to you is to try to get over that confusion so that if you see such a problem again later on, like in the guidebook, you won't be bothered by it. So here's the example. Graph the solution set in the Cartesian plane of the linear inequality x is greater than 5. Now, why do I say this is confusing? Well, notice that you only see one variable in the inequality. X is greater than 5. There are no y's. So you might think I'm just talking about doing a problem on the number line, like I did a few minutes ago with you. But I said in the problem that I wanted you to graph the solution set in the Cartesian plane. And that means that you need to be working in the two-dimensional space of the Cartesian plane, not just the number line. Well, what do? Well, once you know that that's what you're supposed to be doing, working in the Cartesian plane, you do this problem just like you do all the other problems. You need to find the boundary line which splits the Cartesian plane into two pieces and then figure out which side of the plane to keep. So, what's our boundary line? Well, in this case, it's going to be x equals 5. Okay, what kind of line do you have if the equation is x equals 5 and there's no y term? Do you remember? Well, when you have just x equals a number, you always have a vertical line. Think about it. What kind of points are on the line x equals 5? Well, 5, 0, 5, 7, 5, 11, and so on. And all of those points are on a vertical line where the x equals 5. So, once you know that your boundary line is just this vertical line at x equals 5, now you just need to ask yourself, which part of the Cartesian plane are you going to keep? Well, the original inequality was x needed to be just strictly greater than 5. So I need to pick all the points in the Cartesian plane where x is bigger than 5. And that means I'm going to choose all the points that are to the right of this vertical line, x equals 5. And once I've done that, I'm going to shade that part of the plane in, and I'll be done. Okay, now, after I've completed that example, I need to ask myself, does that answer actually make sense? In other words, do I want all of these parts, or all these points, I should say, from quadrants 1 and 4? Well, all of those points have an x value greater than 5. So, indeed, you've got the right ones, and so you're good to go. Now, I'd like to move on to a word problem that demonstrates how you might want to look at a linear inequality to solve the problem. Here's the word problem. Your business sells 2 types of sneakers. For simplicity, let's just say one type is black and the other type is white. The profit on the black sneakers is $12 per pair, and the profit on the white sneakers is $8 per pair. How many pairs of sneakers must your company sell to make a profit of at least $400? That's the problem. One of the features of this question is the presence of the phrase at least. I wanted to know that the profit would be at least $400. And that's a hint that this is not a question about an equality, it's a question about an inequality. So let's proceed with that in mind, and let's see if we can write down the right mathematical expression to take care of the problem. First, what do we do in these kinds of situations? We define the variables. So let's do it real simply. Let's let x be the number of pairs of black sneakers, and let's let y be the number of pairs of white sneakers that we sell. That's simple. Now, what is our inequality? Well, based on that information about the profits, $12 on one type of shoe and $8 on another type of shoe, we know that in order to make at least a $400 profit, we need to write down this equation. 12 times x, or 12 times the number of black sneakers sold, plus 8 times the number of pairs of white sneakers sold is at least, or greater than or equal to, 400. Notice that we used greater than or equal to instead of strictly greater. If the problem had asked for the profit to be more than 400, then I would have used strictly greater. But since it said at least 400, I used greater than or equal to. That's a real key in this example. So I'm just trying to solve now the inequality 12x plus 8y is greater than or equal to 400. I do it the same way I did all the other examples so far. I'm going to look at the boundary line. 12x plus 8y equals 400, and I'm going to see where that line is located in the Cartesian plane. To do that, I'm going to write the equation in slope-intercept form. That way I can plot it pretty quickly. So I've got 12x plus 8y equals 400. I subtract the 12x over to the right-hand side. We've done a lot of this together, so we move that 12x over to the right and it becomes negative 12x. And so I have 8y equals negative 12x plus 400. And now what do I want to do? I want to isolate that y. And the way I do that is to divide by 8. If you divide the left by 8, you must divide the right by 8. And you'll be left with y equals negative 12x over 8 plus 400 over 8. And if you simplify those fractions a little bit, you'll see that that's the same as y equals negative 3/2 x plus 50. Now, that equation is in slope-intercept form, and you've seen equations like that quite a bit in your previous lessons. So you should now be able to plot that line using a solid line because my inequality here is greater than or equal to and not just greater. So pull out a piece of graph paper and give yourself some units, and once you've done that on the x and the y coordinates, you can plot this line. Now, that line cuts the xy plane into 2 pieces. There's a piece sort of below it and there's a piece sort of above it. And the question is, which one do you want? Well, The question really asked, how many pairs of sneakers must the company sell to make a profit of at least $400? There are lots of different ways the company could make at least $400. You could sell 0 pairs of one type, the X type, and you could sell 50 pairs of the Y, and you would end up with a profit of $408. Or you could sell 100 of the first type and 0 of the second type, and you'd end up with a profit of $1,200. And there are lots of other ways to answer the question. But it's okay to have lots of different answers. So what I really want to know is, what are all of the answers in this case? Which part of the plane do I actually shade? All right? So I go back to this region and I ask myself, which one do I want to shade? Well, I want to shade the one where the values are greater than or equal to. In that case, I'm going to shade the part that is above the line. And so that's going to give me the solutions for this inequality. But let's not get lazy. If you look at that region for just a second, there are lots of points there where things don't make a whole lot of sense compared to the problem. For example, the point x equals -5 and y equals 100 is actually in the solution set. Just go plug in x equals -5 and y equals 100 into the original inequality. But that answer doesn't make any sense. How could you sell -5 pairs of black sneakers? You would definitely never want to go to your boss and say, hey boss, let's sell a negative number of pairs of sneakers. So you need to be sure to remember the context of any word problem you do before you give the final answer to that word problem. Well, today we've talked about the idea of linear inequalities, which are a lot like linear equations, but with an equal sign being replaced by some sort of inequality sign. We've graphed the solutions of these linear inequalities, and we also saw how such inequalities might come up in a word problem. Next time we're going to turn a pretty significant corner, and we're going to begin talking about something called quadratic polynomials. These are expressions like 3x squared plus 7x plus 2. Notice that without the 3x squared, you would just have 7x plus 2, and that would be linear. We've studied those for a lot of lessons. But with the 3x squared thrown in, we have a totally different kind of expression in so many ways. So next time, we'll begin talking about these quadratic polynomials. I'll see you then.